Mars is our closest planetary neighbor, our best shot at creating a second Earth, but it's also an unforgiving, frozen wasteland where nothing we need to survive exists naturally. Scientists, engineers, and dreamers alike have been working through the problems, coming up with ideas that range from the painfully slow and methodical to the downright extreme. From thickening the atmosphere to melting the ice caps, from introducing microbial life to dropping asteroids filled with water onto the surface. There are no shortage of ideas, but the real question is, can any of them actually work? So settle in, get comfortable, and let's take a journey through the science, the challenges, and the mind-bending possibilities of what it would really take to terraform Mars. Imagine standing on the surface of a planet where the sky isn't blue but a muted, dusty orange, where the air is too thin to breathe, where the cold seeps into everything, and where, despite all of this, humanity dreams of making a second home. The idea of terraforming, the process of altering a planet's environment to make it more Earth-like, has been floating around in scientific discussions and science fiction stories for decades, and at the heart of it all is Mars, the one planet in our solar system that seems both impossibly hostile and tantalizingly within reach. It's not just about curiosity or exploration. There's something deeply human about looking at a barren wasteland and imagining what could be, about taking an uninhabitable rock and bending it to our will, turning it into a place where future generations could one day walk without a spacesuit, build cities, grow crops, and watch a sunrise that doesn't mean immediate death if they step outside. It's the ultimate challenge, one that stretches across centuries of human ambition, technology, and survival instincts. The idea of terraforming Mars isn't just a wild fantasy cooked up by sci-fi writers looking for an interesting backdrop for space operas. There are real, practical reasons to consider it. Earth, for all its beauty and life-supporting qualities, isn't exactly the safest long-term bet. Whether it's the slow but inevitable march of climate change, the unpredictable nature of cosmic disasters like asteroid impacts, or even the possibility of humanity outgrowing its own cradle, staying confined to a single planet is like keeping all your money in one bank account with no backup plan. If something happens to Earth, that's it. Game over. Mars, despite its barren landscape, represents a kind of insurance policy for our species, a place where humans could, theoretically, establish a second home. But beyond the survival argument, there's also the undeniable lure of scientific discovery, the idea that by understanding how to manipulate and reshape an entire planet, we're not just learning how to extend our reach in the universe. We're unlocking knowledge about our own world, about climate systems, about ecosystems, about the very fabric of what makes a planet habitable. And then, of course, there's the simple, undeniable fact that expansion is built into human nature. Every frontier we've ever encountered, we've pushed past, settled, adapted to, and transformed. Mars is just the next step in a process that has been playing out for thousands of years. Science fiction has long been obsessed with the idea of Mars, sometimes painting it as a dusty wasteland where lone explorers fight for survival, sometimes turning it into a thriving colony where humanity has built a new civilization among the red dunes. The reality, though, is far less dramatic but infinitely more complicated. Unlike the sleek, terraformed utopias of movies, Mars is a place where even the smallest attempt to create a habitable environment would be an uphill battle against the sheer physics of the planet itself. The thin atmosphere, composed mostly of carbon dioxide, doesn't offer much in the way of protection from radiation or help in maintaining surface temperatures that aren't, on average, colder than Antarctica. The dust storms that sweep across the planet aren't just inconvenient. They can last for months and block out the sun, which would be a serious problem for any colony relying on solar power. There's no liquid water on the surface, at least not in any useful amount, and the low gravity could have long-term effects on human biology that we don't fully understand. Every single aspect of Mars that makes it fascinating also makes it a nightmare to work with, a place where even the most basic aspects of survival would have to be artificially engineered. Despite all of that, Mars isn't just some distant dream that scientists speculate about in conference rooms. Right now, we're actively working toward understanding it better, laying the groundwork for future missions that could eventually lead to terraforming efforts. Rovers like Perseverance and Curiosity are already crawling across the Martian surface, analyzing soil, searching for signs of past microbial life, and testing technologies that might one day help sustain human life. Experiments like MOXIE, which is converting Mars' carbon dioxide-heavy atmosphere into small amounts of breathable oxygen, are tiny but crucial steps towards solving the puzzle of long-term survival on another planet. Space agencies and private companies are all racing toward the goal of a human presence on Mars, not because it's easy, but because the question of whether we can do it, and whether we should, goes beyond just space exploration. It's a test of what's possible, of how far our species can push beyond the limits of our own world. The journey toward terraforming Mars is not something that will happen overnight or even within the next few generations. But it's a concept that forces us to think beyond the immediate future, to imagine a reality where humans aren't bound to one fragile rock spinning in space, but are instead architects of entire worlds. In this discussion, there's no single answer, no clear path forward, just an ongoing conversation about whether it's possible, whether it's ethical, and whether, one day, someone will stand on Mars and not think of it as a hostile alien landscape, but as home. 1. The history of terraforming ideas. The idea of reshaping a world, of bending an entire planet to human will, did not arise suddenly in the modern age. It has lingered in the human mind for centuries, hidden in myths of lost paradises, whispered in ancient tales of gods and titans remaking the land, buried within the dreams of those who saw the world not as it was but as it could be. Yet, it was only when humanity began to understand the true nature of planetary environments, when telescopes revealed alien landscapes and scientific reasoning replaced mere imagination, that the notion of terraforming took its first real steps into something tangible. Even before the word itself existed, long before engineers and physicists sought to unravel the logistics of such a grand undertaking, there were thinkers who pondered what it would mean to take a lifeless or inhospitable place and transform it into something familiar, something Earth-like, something capable of sustaining human life. As the Age of Enlightenment dawned, the scientific method began peeling away the mysteries of the cosmos, and with it came a deeper understanding of celestial bodies beyond Earth. By the 18th and 19th centuries, astronomers speculated about the nature of the Moon, Mars, and Venus, though their ideas were often shaped as much by hopeful conjecture as by empirical evidence. Some believed that if these worlds were not already inhabited, they could be made suitable for habitation. The idea was still crude, lacking the technological framework to make it realistic, but it reflected a growing belief that planetary environments were not fixed, that they could be studied, altered, even controlled. Writers, both scientific and fictional, played with these ideas, crafting visions of alien worlds where human ingenuity overcame the barriers of nature itself. By the late 19th and early 20th centuries, scientific advancements began providing a clearer picture of other planets, and the idea of terraforming, though not yet named, took a more structured form. Astronomers like Percival Lowell mapped out intricate canal systems on Mars, convinced they were the work of an intelligent civilization struggling to distribute its dwindling water supply. Though these observations turned out to be mistaken, they fueled a powerful idea. If life could exist on Mars, or if Mars had once been habitable, could it not be restored? Could humanity, with its growing command over chemistry, biology, and engineering, breathe new life into a dying world? The thought was intoxicating, and it would not fade easily. It was in the 1920s and 1930s that the first serious scientific discussions of altering planetary environments began to emerge. The Russian biochemist Alexander Oparin, famous for his theories on the origin of life, suggested that life itself might be capable of transforming a planet's atmosphere, a thought that aligned with the growing realization that Earth's biosphere played an active role in maintaining its own habitability. Meanwhile, another Russian, the aeronautical engineer Konstantin Tsiolkovsky, often regarded as one of the fathers of astronautics, dreamed of space colonies and planetary engineering. He envisioned not just human expansion into the cosmos, but the deliberate modification of celestial bodies to suit human needs. To him, space was not an empty void, but a new frontier, one that could be molded with the right application of science and willpower. As the decades progressed, the conversation became more grounded in scientific possibility. In the 1950s, the term terraforming itself was coined by the American science fiction writer Jack Williamson, who used it in a story to describe the transformation of Mars into a livable world. Though fiction, the word captured something real, something that scientists had already begun to theorize about in earnest. The planetary scientist Carl Sagan, one of the most influential figures in the study of extraterrestrial environments, proposed in the early 1960s that Venus, with its thick atmosphere of carbon dioxide, might be cooled and altered by introducing genetically engineered algae that could absorb the greenhouse gases and gradually shift the planet's climate. It was an ambitious idea, and while it eventually proved impractical given the hostile conditions of Venus, it marked one of the first concrete attempts to devise a method for planetary transformation based on scientific principles rather than mere speculation. By the time the space age truly began, and robotic probes sent back images of barren, windswept Martian deserts and crushing Venusian storms, the idea of terraforming had moved beyond a distant dream into a subject of serious academic discussion. The early proposals were often simplistic, reflecting the limited understanding of planetary atmospheres at the time. Some suggested detonating nuclear weapons at the poles of Mars to release trapped carbon dioxide and create a thicker atmosphere. Others imagined giant space mirrors concentrating sunlight onto a frozen world, slowly warming it until liquid water could return. These ideas were bold, but they were also crude, the work of minds still feeling their way through the immense complexities of planetary systems. What mattered, though, was not whether these early concepts were viable, but that they were being considered at all. For the first time in history, humanity was seriously discussing the possibility of reshaping an entire world, of taking the raw material of nature and bending it toward a human purpose. The dream of terraforming was no longer just the realm of visionaries and dreamers. It had become a question of science, of physics, of engineering, of patience. And in that shift, in that moment where speculation became calculation, the idea solidified into something greater. It was no longer a question of whether humanity would attempt to alter other worlds. It was a question of when and how and what it would mean when the day finally came. As the idea of reshaping entire worlds moved from vague scientific musings to concrete discussions, it found fertile ground in the realm of fiction, where constraints of technology and feasibility could be set aside in favor of grand narratives. Writers had always speculated about humanity's place beyond Earth, but once the notion of altering planets took hold in scientific circles, it became an irresistible subject for storytellers. Fiction had the freedom to imagine what scientists could not yet achieve, to push past the limitations of reality and explore what it would mean, ethically, emotionally, even philosophically, for humans to carve out new homes among the stars. It was not just about the mechanics of planetary engineering, but about the kind of people who would dare to undertake it, about the triumphs and failures that would shape their journeys, and about the unintended consequences of bending nature to human will. Ray Bradbury was among the first to capture this tension with unsettling beauty. His collection, The Martian Chronicles, published in 1950, did not dwell on the technical details of terraforming, but instead on what it meant for human beings to impose themselves on an alien world. The stories painted a picture of Mars not as a barren wasteland waiting to be remade, but as a place with its own quiet history, its own ghostly remnants of life, and its own resistance to human interference. The settlers who arrived believed they were taming a dead planet, but instead, they found themselves haunted by what they destroyed in the process. Bradbury's Mars was not merely a backdrop for exploration. It was a reflection of humanity's tendency to consume, to conquer, and to justify its expansion under the guise of necessity. Even without describing the process of planetary engineering in detail, he captured something fundamental about it: the arrogance, the nostalgia for Earth even as it was abandoned, and the question of whether a world truly belonged to those who altered it. As science fiction matured, the theme of terraforming became more deeply intertwined with ideas of survival and transformation. Arthur C. Clarke and Isaac Asimov, both fascinated by the idea of planetary engineering, treated it as an extension of human progress, a natural step in humanity's evolution beyond Earth. Clarke's The Sands of Mars, written in 1951, envisioned a slow, deliberate process of warming the planet by triggering volcanic activity, while Asimov's stories often touched on vast projects that reshaped planets, sometimes subtly, sometimes with force. In these works, terraforming was not merely a technological challenge, but a statement of human persistence, a belief that no environment was truly inhospitable if intelligence and effort were applied with enough patience. These authors did not question whether humanity had the right to remake other worlds. They assumed it was inevitable. Then came the works that questioned the morality of it, that asked whether transforming a planet was an act of creation or destruction. Frank Herbert Stone, published in 1965, introduced a world where ecological balance was fragile, where every attempt to control nature had consequences. Though Arrakis was not terraformed in the traditional sense, its story revolved around the relationship between humans and their environment, about how altering a planet to suit human needs could unravel the very systems that made it unique. Later, Ursula K. Le Guin explored similar themes, imagining societies that adapted to harsh worlds rather than reshaping them to resemble Earth. These were not stories of triumphant engineers sculpting planets to their will, but of cultures learning to live with what already existed, of humility rather than domination. By the late 20th century, terraforming had become more than just a backdrop for stories. It had become a subject of deep thematic exploration. Kim Stanley Robinson's Mars trilogy, beginning with Red Mars in 1992, remains one of the most detailed and realistic depictions of planetary transformation ever written. Unlike earlier works, which treated terraforming as a distant possibility or a completed process, Robinson placed his characters in the middle of it, showing the slow, contentious struggle between those who sought to preserve Mars as it was and those who believed in remaking it for human habitation. It was not just a technical challenge, but a political and philosophical one, with debates over ethics, environmental responsibility, and the very meaning of home woven into every stage of the process. The characters were not just scientists and engineers, but revolutionaries, opportunists, visionaries, and those who simply wanted a place to belong. The books did not offer easy answers, only the reality that changing a world meant changing the people who lived on it as well. As film and television took up the subject, terraforming was often depicted with the spectacle and immediacy that the medium demanded. Hollywood, bound by the need for visual storytelling, rarely had the patience for slow, methodical planetary engineering. Instead, it leaned toward dramatic, rapid transformations. Terraforming at the push of a button, the release of a gas, or the detonation of a bomb. Films like Total Recall, 1990, imagined Mars suddenly gaining a breathable atmosphere through a forgotten alien device, while Interstellar, 2014, sidestepped the issue altogether by focusing on planets that were already marginally habitable, suggesting that the search for a new home might be easier than reshaping a dead world. The Martian, 2015, though rooted in scientific realism, still presented Mars as a temporary challenge rather than a permanent one, with survival dependent on ingenuity rather than planetary transformation. The deeper questions of terraforming, the decades, centuries, or even millennia it would take, the moral dilemmas involved, were often left in the background, if addressed at all. Yet, even when simplified, these fictional depictions reflected the same core fascination that had always driven the idea forward. Whether seen as a symbol of progress, a cautionary tale, or an impossible dream, terraforming remained a powerful narrative force. It was never just about technology. It was about ambition, about the human need to push beyond what is known, about the way people confront the unfamiliar by making it familiar. And beneath all the stories, from Bradbury's melancholic settlers to Hollywood's grand spectacles, one question lingered. If humanity ever truly succeeds in remaking another world, will it still feel like home? While fiction embraced the limitless possibilities of terraforming, painting vivid pictures of human colonies thriving on distant worlds, the scientific reality was far less forgiving. The early theories, fueled by optimism and a rapidly expanding understanding of planetary science, often overlooked the sheer complexity of altering an entire world. In those first bold proposals, the belief was that planetary environments could be manipulated with broad, sweeping changes. The scale of the challenge, however, was far greater than many had initially imagined, and as more was learned about the conditions of planets like Mars and Venus, the limitations of these early ideas became increasingly apparent. There was a time when Mars was thought to be a world not unlike Earth, merely colder and drier, but with the potential for life lurking just beneath its surface. Some believed that by thickening its atmosphere, trapping more heat, and restoring liquid water, it could be made habitable within a relatively short span of time. The concept of releasing carbon dioxide from the polar caps or igniting chemical reactions in the soil to generate greenhouse gases seemed within reach, at least in theory. But the more detailed the study of Mars became, the more obstacles emerged. The thin atmosphere, which was barely capable of retaining heat, meant that even if a thicker blanket of gases were created, it would slowly dissipate into space due to the planet's weak gravity and lack of a protective magnetic field. Water, once thought to be locked away in vast underground reserves, appeared to be scarcer than hoped, and even if the planet were warmed, there was no guarantee that liquid water would remain stable under such a fragile atmospheric envelope. The first proposals, daring as they were, had underestimated just how deeply inhospitable Mars truly was. Venus, on the other hand, seemed like a world in reverse. Too thick an atmosphere, too much heat, an overwhelming runaway greenhouse effect that made any dreams of cooling it down seem insurmountable. The idea of using algae or other biological agents to convert carbon dioxide into breathable oxygen was based on the success of Earth's own early life forms in shaping the planet's atmosphere over billions of years. But Venus was not Earth, and the conditions on its surface, where temperatures could melt lead and pressures crushed anything that attempted to land, made it clear that no simple biological solution would work. The thick clouds of sulfuric acid in the absence of a stable water cycle rendered even the most hopeful proposals infeasible. It was not merely a matter of adjusting chemical balances. Venus was a world that had locked itself into a state of extreme hostility, and reversing that process, if possible at all, would require intervention on a scale far beyond anything humanity was capable of. Even the more radical ideas, like detonating nuclear weapons to release trapped gases or constructing giant orbital mirrors to redirect sunlight, suffered from the same fundamental problem. There was no clear way to make these changes permanent. The forces that had shaped Mars and Venus into the worlds they were had been working for billions of years, sculpting them through geological processes, atmospheric loss, and solar radiation. Overcoming those forces would not be as simple as triggering a chain reaction or planting the right kind of life. It would require an understanding of planetary evolution that scientists were only beginning to grasp. The more the idea of terraforming was studied, the more it became clear that these early proposals had been guided by an understandable but overly simplistic belief that planets were malleable in the way that landscapes on Earth were. Still, these first attempts to grapple with the problem were not in vain. They forced scientists to ask difficult questions about what truly made a planet habitable, about the delicate balance of atmospheric gases, magnetic fields, solar energy, and biological interactions that sustained life on Earth. They illuminated the barriers that would need to be overcome and paved the way for more refined theories that took into account not just the immediate changes required, but the long-term stability of any transformed environment. The failure of these early ideas was not a sign that terraforming was impossible, but rather a reflection of how little was known at the time. Each flawed proposal was a step toward a more complete understanding, a slow unraveling of the complexities that defined what it meant to reshape a world. The dream of terraforming remained, but it had to be tempered by the weight of reality, by the recognition that the universe did not yield so easily to human ambition. 2. The current state of Mars. The realization that planets could not be reshaped as easily as once imagined led to a deeper, more sobering understanding of Mars itself. A world that, despite its haunting resemblance to Earth, remains deeply alien in its nature. The more closely it has been studied, the clearer it has become that the thin, fragile veil of its atmosphere is not merely an obstacle to be overcome, but a defining feature of a planet that has been shaped by forces far beyond human control. The Martian sky, tinged with dust and illuminated by a weakened sun, tells the story of a world that lost its ability to hold on to warmth, a place where the struggle between atmospheric escape and gravitational weakness has played out over billions of years, leaving behind an environment that is both starkly beautiful and brutally uninhabitable. The air on Mars is not just thin. It is practically non-existent in comparison to Earth's. With an atmospheric pressure less than 1% of what humans are accustomed to, standing on the Martian surface without protection would be no different than standing in the vacuum of space. What little atmosphere remains is overwhelmingly carbon dioxide, nearly 95% of it, with only traces of nitrogen and argon filling out the rest. Oxygen, the very element that sustains life on Earth, is present in amounts so negligible that it might as well not be there at all. Breathing on Mars is impossible not just because of the lack of oxygen, but because there is barely anything to breathe in the first place. The air is too thin to carry sound in the way it does on Earth, making the planet eerily silent, where even the strongest gusts of wind are nothing more than a whisper compared to the storms of Earth. Despite its reputation as a desert planet, Mars is not merely cold. It is a world locked in an endless deep freeze. The average surface temperature hovers around -80 degrees Fahrenheit, but it can plunge far lower, especially at night when the lack of a thick atmosphere allows heat to radiate away into space unchecked. In the warmest regions and during the peak of summer, temperatures may briefly rise above freezing, but it is never enough to sustain liquid water for more than fleeting moments. The cold is relentless, seeping into every exposed surface, turning even the most optimistic visions of terraforming into a battle against physics itself. The freezing temperatures, combined with the thin atmosphere, mean that any exposed water would either freeze solid or sublimate directly into vapor, escaping into the sky where it would be lost forever. Dust dominates the climate of Mars in ways that are difficult to comprehend on Earth. The planet's dry, barren surface is constantly shaped by fine particles of iron-rich dust, lifted and carried by weak but persistent winds that can give rise to immense storms capable of engulfing the entire planet. These storms can last for weeks or even months, blocking out sunlight and plunging temperatures even lower, a reminder that even in its stillness, Mars is not a dead world. It is a place of quiet, unforgiving change. The thin atmosphere does little to protect against the cosmic radiation that bathes the surface, meaning that any future explorers or settlers would be exposed to levels of radiation far beyond what is considered safe on Earth. Without a magnetic field to shield it, Mars is vulnerable to the relentless bombardment of solar particles, further stripping away what little atmosphere it still clings to. Yet, despite all of this, there is something about Mars that continues to draw the human imagination. The dry riverbeds, the ice locked away in the polar caps, the fleeting traces of methane detected in the atmosphere. All of it hints at a past that was once different, a time when Mars might have been a place of running water, of a thicker sky, of conditions that could have once supported life. But whatever warmth and habitability it once had, it has long since faded, leaving behind a planet that stands as both a promise of what could be and a warning of what happens when a world loses its ability to sustain itself. The more is learned about its current state, the clearer it becomes that Mars is not simply waiting to be reshaped. It is a world that has settled into a reality that may never be undone. Mars, in its stillness and desolation, holds onto an environment that is as hostile as it is mesmerizing, a landscape carved by forces that have long since stripped it of any hope for natural habitability. The surface, covered in iron-rich dust and ancient rock formations, is a place where temperatures swing violently between extremes, where storms rage with deceptive gentleness, and where the very air is saturated with radiation that no living thing from Earth could endure for long. It is a world that has never known the comfort of a breathable atmosphere, where the cold is not just an inconvenience, but a force that dictates every aspect of its barren existence. The temperatures that grip Mars are not uniform, shifting depending on the time of day, location, and season, but they all share one thing in common: an unrelenting frigidity that makes even the coldest places on Earth seem mild by comparison. The planet's distance from the sun is not the only reason for this deep chill. Its thin atmosphere offers almost no insulation, allowing whatever heat reaches the surface to escape back into space with little resistance. In the daytime near the equator, temperatures can briefly climb just above freezing, but as soon as the sun sets, the warmth vanishes into the void and the land plunges into an abyss of cold. At night, temperatures can drop to -100 degrees Fahrenheit or lower. Even in the warmer regions and near the poles, the cold is so severe that carbon dioxide in the atmosphere freezes into ice, forming a seasonal layer that expands and contracts as the planet shifts through its elongated orbit. There is no reprieve, no gradual warmth returning with the dawn, only the constant cycle of heat loss, a reminder that Mars has long since lost the ability to hold onto the energy it receives. The dust that coats the surface is more than just a feature of the landscape. It is an ever-present force that shapes the Martian climate in ways both subtle and overwhelming. Made of fine, iron oxide particles, the dust is what gives Mars its signature reddish hue, but it is also what fills the thin air, lifted by winds that, despite their weakness, are capable of carrying it across the entire planet. On a small scale, it forms swirling dust devils that dance across the plains, carving faint trails into the ground before vanishing into nothingness. On a larger scale, it gives rise to storms that can blanket entire regions, obscuring the sun for days or weeks. And sometimes, in the right conditions, these storms grow into something far more formidable. Planet-wide tempests that last for months, churning dust into the atmosphere until Mars becomes nothing more than a swirling, opaque sphere from orbit. Unlike Earth's storms, which bring violent winds and torrents of rain, Martian storms are quiet and insidious, their winds weakened by the thin atmosphere, but still capable of lifting vast amounts of dust into the sky. The particles, once airborne, absorb and scatter sunlight, disrupting temperatures and altering the already delicate balance of the planet's weather patterns. When one of these storms engulfs the planet, the already feeble sunlight is reduced to an orange haze, the temperature shifts unpredictably, and the dust lingers long after the winds have died down. For any potential human presence on Mars, these storms would not bring destruction in the way hurricanes or typhoons do on Earth, but they would bring an unsettling, suffocating darkness, an eerie reminder of how different this world truly is. Even in the moments of stillness, when the air is clear and the surface lies quiet beneath the distant sun, there is another threat that Mars offers with relentless consistency. Radiation, the unseen force that seeps through the atmosphere, unimpeded by the protective barriers that make Earth a cradle for life. Without a magnetic field to deflect the charged particles streaming from the sun, and with only the thinnest layer of gases to absorb cosmic rays from deep space, the surface of Mars is bathed in radiation at levels that would be intolerable for long-term human exposure. It is not just a distant concern, but an immediate, unavoidable danger, an invisible force that bombards the ground with energies that, over time, could damage cells, alter DNA, and increase the risks of cancer and other long-term health effects. Unlike Earth, where the atmosphere and magnetic field work in tandem to shield life from such harm, Mars offers no such protection. Any future explorers or settlers would not merely have to survive the cold or endure the dust. They would have to find ways to shield themselves from an environment that is fundamentally hostile to biological existence. Mars, as it exists now, is not merely an empty world. It is a world shaped by extremes, by forces that have stripped it down to its most unforgiving state. It is a place where cold seeps into every exposed surface, where storms do not rage with fury but with quiet persistence, and where an unseen cosmic barrage continues without pause. It is a reminder that while Mars may once have been different, it is now a world that has settled into a state of perpetual hostility, a place that will never be welcoming on its own. The challenge of reaching it, surviving on it, and perhaps one day transforming it will not be a battle against a single obstacle, but against an entire planet that has spent billions of years resisting habitability. Even in the midst of its desolation, Mars holds onto a past written in the language of water, an element that once shaped its surface with rivers, lakes, and possibly vast oceans, only to retreat into hiding as the planet's atmosphere thinned and its ability to sustain warmth faded away. The evidence is everywhere, etched into dry riverbeds that snake across the landscape, in the layered sediments of ancient lake basins, and in the mineral deposits that only form in the presence of liquid water. But in its present state, Mars is a place where water exists not as flowing streams or rolling waves, but as ice locked within the polar caps, as hidden reservoirs buried beneath layers of dust and rock, and in rare, fleeting moments, as briny liquid that may still lurk beneath its frozen surface. At the poles, the Martian ice caps stand as the most visible and undeniable remnants of the planet's water-rich past, vast frozen expanses made up of layers of water ice mixed with dust and, during the winter, covered in a thin coating of frozen carbon dioxide. These caps grow and shrink with the changing seasons, expanding as the temperatures plunge and retreating slightly when the planet tilts closer to the sun. Unlike Earth's polar regions, where thick glaciers stretch across entire continents, The Martian ice caps are relatively thin in comparison, but they still contain an astonishing amount of frozen water. Enough that, if melted, it could cover the entire planet in a shallow ocean. The layers within them tell a story of climate shifts stretching back millions of years, each one a marker of changing atmospheric conditions, of dust storms that once darkened the skies, and of a planet that was slowly losing its grip on the ability to sustain warmth. Beyond the polar regions, water remains hidden beneath the surface, locked away in underground reservoirs that have remained untouched for eons. Radar scans from orbiting spacecraft have detected vast deposits of ice buried beneath layers of rock and dust, stretching across the mid-latitudes, concealed just beneath the surface. Some of these reservoirs likely represent the remnants of ancient glaciers, frozen in place long after the planet's climate turned hostile, preserved beneath insulating layers of debris that protect them from sublimating into the thin Martian air. The existence of these buried ice sheets presents an intriguing possibility, not just for understanding Mars's history, but for the future of human exploration. If accessible, these ice deposits could be one of the most valuable resources for any future missions, a potential source of drinking water, breathable oxygen, and even rocket fuel, extracted and broken down into its elemental components. But reaching them, extracting them, and using them would be another challenge entirely, one that would require navigating an environment where any exposed water quickly vanishes into vapor, where the simple act of melting ice would be a delicate balance between preservation and loss. And then there is the possibility, still debated but deeply tantalizing, that liquid water may yet persist beneath the surface, hidden in the depths where heat from the planet's interior might keep it from freezing solid. The most striking hint of this came from radar observations beneath the southern polar ice cap, where reflections suggested the presence of a lake-like body of liquid water buried beneath more than a kilometer of ice. The idea is a staggering one. A hidden Martian lake, possibly briny, existing in the cold darkness beneath layers of frozen carbon dioxide and water ice, a world within a world where conditions might still support the chemistry of life. If confirmed, it would not only reshape our understanding of Mars's potential for habitability, but would also suggest that, even in the most extreme environments, water finds a way to persist, defying the relentless grip of the Martian cold. But the nature of this supposed lake remains uncertain. Some scientists argue that the radar signals might be the result of something else, perhaps a layer of salty sediments rather than a body of water, while others continue to explore the possibility that Mars, in its hidden depths, still holds on to the last vestiges of a time when liquid water was not just a possibility, but a defining feature of the planet's landscape. Even if liquid water does exist beneath the surface, it would be unlike any lake or sea found on Earth. The pressures are low, the temperatures bitterly cold, and any liquid would have to be infused with salts that lower its freezing point to allow it to remain in a fluid state. It would be an alien environment, an isolated world buried beneath ice and rock, untouched by sunlight, governed by forces that have shaped Mars for billions of years. If life ever existed on the planet, such hidden reservoirs might be one of the last places where it could still cling to existence, protected from the deadly radiation that batters the surface, sustained by chemistry rather than sunlight. But whether Mars still holds onto liquid water or whether it has long since lost the last traces of it remains an open question, one that continues to drive exploration as rovers and orbiters search for more clues, as scientists debate the data, and as the dream of one day uncovering the truth beneath the planet's frozen surface continues to linger. 3. The fundamental challenges of terraforming Mars. Imagine stepping onto the surface of Mars, the dusty red landscape stretching endlessly in every direction, an alien world that holds both promise and peril in equal measure. The air around you is deathly silent, not because Mars is a quiet place, but because there is almost no air at all. Without the comfort of a sealed suit, the very first thing you would notice is the way your body responds to the near vacuum. Your breath would be stolen away in an instant, your lungs unable to grasp onto anything that resembles breathable air. Within seconds, the moisture in your eyes and mouth would start to boil away, not from heat, but from the sheer lack of atmospheric pressure holding your bodily fluids in check. Blood vessels near the surface of your skin would rupture, swelling your body grotesquely as your own biology betrays you in an environment it was never meant to withstand. It would be a swift, merciless demise, a reminder that Mars, in its current state, is a world that rejects human life at the most fundamental level. Unlike Earth, where the thick, protective embrace of our atmosphere shields us from cosmic radiation and provides a stable pressure for our bodies to function, Mars exists in a state of barren hostility. The air pressure on the surface is less than 1% of what we experience on Earth, so thin that even if the composition were suddenly altered to include oxygen, it still wouldn't be enough to sustain human respiration. Every breath would be as futile as inhaling in the vacuum of space, the oxygen simply unable to reach your bloodstream in a way that could keep you alive. The lack of atmospheric pressure also means that water, the most essential ingredient for life as we know it, can't exist in liquid form under normal conditions. Any exposed water would either freeze solid or instantly vaporize, vanishing into the thin air in a cruel paradox of abundance and inaccessibility. Ice exists in the polar caps. Water may still be hidden beneath the surface, but without a thick enough atmosphere to trap heat and maintain pressure, Mars remains an arid wasteland where liquid water is a fleeting impossibility. Even if humanity found a way to introduce breathable gases into the Martian sky, it would be an uphill battle against physics itself. A thicker atmosphere requires a way to trap and maintain gases, but Mars, with its weak gravity and lack of a global magnetic field, struggles to hold onto anything lighter than the heaviest molecules. Over millions of years, solar wind has stripped away much of what once might have existed, carving away at the planet's ability to sustain an environment that could nurture life. Without a magnetic field like Earth's to act as a protective barrier, any attempt to terraform Mars would be met with the relentless assault of charged particles from the sun, slowly eroding whatever fragile atmosphere we could hope to build. To make Mars a place where humans could one day walk unprotected, breathe freely, and see liquid water flow across its surface, we would need to fight against planetary forces that have been shaping its landscape for billions of years. It isn't just about adding air. It's about keeping it there, preventing it from slipping away into the vacuum of space, and finding a way to make a dead world feel alive again. But even if Mars somehow held on to a thicker atmosphere, even if the air was dense enough to press against your skin and allow your lungs to function without the suffocating grasp of a vacuum, the danger wouldn't end there. The sky above would still be an open battleground, a place where invisible threats rain down without mercy, unhindered by the protective shield that Earth's magnetic field so effortlessly provides. On Mars, there is no such shield. The planet's core, once a churning furnace of molten metal generating a vast and powerful magnetic field, has long since cooled and quieted, leaving behind only weak, fragmented remnants of what was once a force capable of deflecting deadly cosmic radiation. What remains is a world exposed, a planet where the atmosphere is stripped away molecule by molecule and where every surface is bombarded by radiation from deep space and the violent emissions of the sun itself. Standing unprotected on the Martian surface, you wouldn't feel the radiation tearing through you, but the effects would be slow and insidious, unraveling you from the inside out. High-energy particles from the sun, known as solar wind, would slice through your cells, damaging DNA with every passing moment, increasing the risk of cancer, organ failure, and neurological deterioration. Beyond the solar radiation, there's something even more unforgiving. Cosmic rays, born from the explosions of distant stars, moving through the universe at near-light speeds. These are not just particles, they are fragments of destruction, so energetic that no natural biological defense can fully withstand their assault. On Earth, the magnetic field bends them away, forcing them to spiral along safe pathways, rarely reaching the surface in significant amounts. On Mars, they strike unchallenged, embedding themselves in everything they touch, from the dust-covered rocks to the fragile human bodies that dare to exist in such a place. Shelter, in a world like this, becomes more than just a way to escape the cold or the harsh winds that occasionally sweep across the barren landscape. It becomes a necessity for survival at a genetic level. The safest place would not be under the open sky, but buried beneath layers of rock and soil, deep enough to let Mars itself absorb the worst of the radiation before it reaches living tissue. The idea of walking freely on the surface, basking in the sight of an alien horizon, becomes a dangerous luxury, one that could only be afforded in brief moments before retreating into the safety of subterranean habitats or shielded enclosures. Terraforming would not only require thickening the atmosphere, but somehow finding a way to recreate the magnetic field that once protected Mars from becoming the desolate place it is today. Without that, any progress made in making the planet more Earth-like would always be temporary, always vulnerable to the unrelenting forces of space. Even if Mars could one day be given a second chance, it would still have to fight against a universe that never stopped trying to strip it bare. Even if a way were found to shield Mars from the unrelenting assault of cosmic radiation, even if humans could carve out protected spaces beneath the surface or build artificial magnetic fields to hold back the invisible forces that seek to unravel them, there would still be another challenge lurking in the thin, frigid air. A planet without warmth is just another graveyard, and on Mars, warmth is in short supply. The cold is not just an inconvenience, it is an ever-present force, woven into the very fabric of the planet itself, seeping into every rock, every grain of dust, and every molecule of air. Unlike Earth, where greenhouse gases like carbon dioxide and methane trap the sun's energy, holding it close and allowing the planet to remain temperate, Mars lacks the ability to retain heat. The sunlight that reaches the surface is weak, diluted by distance, and what little warmth does arrive is quickly lost to the emptiness of space, slipping away without resistance. The planet's atmosphere, already too thin to support life as we know it, is also critically lacking in the greenhouse gases that would be necessary to build and sustain a stable climate. There is carbon dioxide on Mars, locked away in the polar ice caps and scattered in trace amounts throughout the air, but nowhere near enough to create the kind of runaway warming effect that would be needed to transform the planet into something habitable. On Earth, the balance of carbon dioxide is delicate, a system constantly in motion as oceans, plants, and the atmosphere work together to regulate temperature and maintain the fragile equilibrium that allows life to thrive. Mars has no such system. The cycle was broken long ago, if it ever existed at all, leaving behind a world that cannot easily be coaxed into warmth. A slight increase in pressure, a whisper of warmth, but nothing close to the transformation that would be needed. The problem is not just a lack of carbon dioxide, but the absence of a mechanism to keep it in circulation, to replenish it over time and prevent it from being lost. On Earth, volcanic activity constantly replenishes the atmosphere, spewing greenhouse gases into the air and fueling the planet's long-term climate stability. Mars, with its largely dead interior, has no such luxury. Without a way to continuously produce and maintain greenhouse gases, any attempt to warm the planet would be temporary at best, a brief experiment in climate control that would eventually collapse under the weight of its own limitations. The idea of warming Mars has often been imagined as a matter of simply adding heat, as if lighting a fire in a cold room and waiting for the temperature to rise. But the reality is far more complex. It is not just about generating warmth. It is about trapping it, holding it in place, ensuring that every bit of energy gained is not lost again the moment the sun dips below the horizon. Without a working greenhouse effect, Mars will always remain a world of ice and shadow, a place where warmth is fleeting and where every attempt to create a habitable environment is constantly undone by the relentless pull of space. Even if humanity were to one day find a way to breathe life into the planet, to build an atmosphere thick enough to support water and air, the battle would not be over. The real challenge is not just in creating warmth, but in making sure it lasts. But even if Mars could somehow be warmed, even if the air could be thickened and the surface coaxed into holding on to its heat, there would still be another fundamental problem lurking beneath the rust-colored dust. A living planet is not just defined by its ability to support life on the surface. It is shaped, molded, and sustained by the ceaseless movement of its own interior. On Earth, the ground beneath our feet is never truly still. Tectonic plates shift and collide, mountains rise, valleys form, and volcanoes breathe gases into the air, replenishing the atmosphere and feeding the cycles that make life possible. It is this constant activity that allows carbon to move between the land, the air, and the oceans, preventing the planet from slipping into a permanent and irreversible stagnation. Mars, by contrast, is a world that has largely fallen silent, its once active core having cooled to the point where the very processes that shape and sustain a planet have slowed to a near standstill. Without plate tectonics, there is nothing to recycle atmospheric gases, no mechanism to bury and release carbon dioxide over geological timescales, no slow but steady process to refresh the Martian air. The volcanoes that once towered over the landscape, including Olympus Mons, the largest in the solar system, stand as relics of a time when Mars was still alive in a way that it no longer is. Their eruptions, which might have once poured greenhouse gases into the sky, have long since ceased, leaving behind only frozen wastelands of solid rock. The planet's surface, stripped of these fundamental forces, has become a place where nothing new is created, where erosion is driven not by flowing water or shifting plates but by the slow, grinding influence of wind and dust storms that have scoured the landscape for millions of years. This inactivity is not just a geological curiosity. It is a roadblock for any attempt to make Mars a home. A world that does not change is a world that cannot heal itself, that cannot replenish what is lost over time. On Earth, volcanic eruptions and deep-sea vents release vital chemicals into the air and oceans, sustaining the cycles that regulate climate and atmospheric balance. Mars has no such process. Even if humans managed to engineer an atmosphere, it would be like building a sandcastle against the tide, constantly eroded by the forces of space without any internal system to maintain it. The planet's lack of geological movement means that its surface is littered with craters that have remained unchanged for millions of years, scars of impacts that on Earth would have long since been erased by the shifting of continents and the slow renewal of land. The very stillness of Mars is what makes it so difficult to transform. A world that does not move is a world that does not adapt, and without the ability to regulate itself, any changes made to the Martian climate would be temporary, vulnerable to collapse at the slightest disturbance. Earth's surface is dynamic, constantly shifting in ways that allow life to flourish, but Mars has long since frozen in time, locked in a state of dormancy that offers no easy path forward. Even if humanity could breathe warmth and air into the planet, it would still remain fragile, forever at risk of slipping back into the cold, lifeless silence that has defined it for so long. 4. Terraforming methods, slow versus rapid approaches. But even if Mars remains frozen in geological stillness, even if its surface no longer shifts and its core no longer churns, the possibility of change has not been entirely abandoned. The idea of making Mars into something more than a barren wasteland, of transforming it into a world where life could one day thrive, has been imagined in two vastly different ways. One that seeks to force change through rapid intervention, bending the planet to human needs as quickly as possible, and another that relies on time itself, allowing slow but steady processes to take hold over centuries, perhaps even millennia. The latter, known as natural evolutionary terraforming, does not fight against Mars' limitations, but rather attempts to work with them, nudging the planet along a path that could, in the distant future, lead to a more habitable world. This approach begins not with grand engineering projects, but with the smallest of interventions, introducing microorganisms capable of surviving in Mars' harsh environment, ones that could slowly alter the chemical makeup of the soil and atmosphere over time. Extremophiles, bacteria that can endure extreme conditions on Earth, might be the first to take root, feeding on minerals, releasing gases, and beginning the long process of building a foundation for something greater. Over thousands of years, these microbes could thicken the atmosphere molecule by molecule, generating small amounts of oxygen and helping to stabilize the planet's surface against erosion. If given enough time, Mars would not be terraformed through brute force, but rather through the same slow evolutionary processes that shaped Earth's own biosphere over billions of years. Ice at the poles and beneath the surface would gradually melt, not through artificial heating, but through the accumulation of greenhouse gases over centuries, allowing liquid water to exist once again in small, transient pockets. The Martian air, still thin and unbreathable, would slowly become denser, trapping just enough heat to extend the planet's warmth beyond the brief reach of the sun's rays. Plants, engineered to survive in low-pressure, high-radiation environments, could be introduced in later stages, releasing oxygen and helping to create a self-sustaining cycle. This would not be a process that unfolds in a single lifetime, nor even in the span of human history as it is currently measured. It would be a patient effort, one that does not seek immediate results but instead lays the groundwork for a world that future generations might one day inherit. The challenge, however, is that such a method offers no guarantees, only a possibility shaped by time and the unpredictable forces of planetary change. Unlike Earth, where life emerged within a complex and dynamic system, Mars offers only a fraction of those conditions, and there is no certainty that a slow transformation would ever fully take hold. Without a magnetic field to hold the atmosphere in place, without active geological cycles to replenish lost gases, the planet could always remain on the brink, requiring constant intervention to maintain whatever fragile progress had been made. It is a method built on patience, on the hope that with enough time, a lifeless world might one day learn to breathe on its own. Whether humanity would be willing to wait that long, to invest in a process that may not bear fruit for thousands of years, remains an open question. Yet the idea of waiting millennia for Mars to transform itself, of relying on slow biological processes that may never fully take hold, is a vision that does not align with the urgency of human ambition. The alternative, one that disregards the natural evolutionary path in favor of direct intervention, relies not on time, but on sheer engineering force, bending Mars to fit human needs through methods that are as bold as they are daunting. Instead of coaxing the planet to change through slow microbial influence, engineering-based terraforming seeks to alter the Martian environment on a far shorter timescale, using large-scale technologies to force a shift in temperature, pressure, and atmospheric composition. It is an approach built on control, one that does not wait for nature to act, but instead takes the responsibility of reshaping a world into human hands. The first step would be to thicken the atmosphere, creating conditions where liquid water could exist on the surface without instantly evaporating. One proposed method involves releasing massive quantities of greenhouse gases, carbon dioxide, methane, or even artificial compounds designed to trap heat more effectively, into the sky, triggering a runaway warming effect. Factories, either robotic or manned, could be deployed across the Martian surface, slowly pumping out these gases in a deliberate effort to create an insulating layer around the planet. Some theories suggest redirecting asteroids rich in volatile compounds and crashing them into Mars, releasing carbon dioxide and water vapor in a single, dramatic burst. Others consider detonating nuclear devices beneath the planet's polar ice caps, instantly sublimating the frozen carbon dioxide and thickening the atmosphere through brute force. The methods vary, but the goal remains the same: accelerate a process that would otherwise take millennia, forcing Mars into a new climate cycle within a fraction of that time. Even if the atmosphere could be made thicker, there would still be the problem of oxygen. The Martian air, even if warmed, would still be unbreathable, composed primarily of carbon dioxide. To counter this, genetically engineered algae and plants could be introduced in vast artificial greenhouse structures, designed not only to survive, but to rapidly convert CO2 into oxygen at an accelerated rate. Some proposals go even further, suggesting that vast orbital mirrors could be deployed in space, reflecting sunlight onto the surface to create targeted warming zones. Or that large-scale electrical discharges could be used to break down CO2 and release oxygen into the air. The sheer scale of such interventions is staggering, requiring technological advancements that do not yet exist, and resources that would make even the most ambitious space projects of today seem trivial by comparison. The challenge with engineering-based terraforming is not only its feasibility, but its sustainability. Mars, even if transformed by human hands, is still fundamentally hostile, with no internal mechanisms to maintain its new state. Unlike Earth, which naturally regulates its climate through volcanic activity, ocean currents, and a dynamic atmosphere, Mars would require constant intervention to prevent its atmosphere from being stripped away by solar winds, to keep its newly formed climate from slipping back into its cold, barren past. The question is not just whether humans could terraform Mars in a short amount of time, but whether they could maintain it indefinitely, ensuring that the changes forced upon the planet do not unravel the moment human effort is withdrawn. It is a battle against entropy, against a planet that, left to its own devices, would always try to return to what it was before. But even with all the force that engineering can exert on Mars, even with all the ingenuity poured into reshaping its surface and atmosphere, there is still the reality that brute technological intervention alone may not be enough to sustain a living world. The idea of completely forcing Mars into habitability through sheer mechanical effort demands not only unimaginable resources, but an ongoing struggle against the planet's natural tendency to revert to its frozen, airless state. On the other hand, relying solely on natural evolutionary processes, waiting for microbes and plants to alter the environment over thousands of years, offers no certainty that the transformation will ever fully take hold. The limitations of both approaches have led to the idea that perhaps the best path forward is not a choice between nature or technology, but a fusion of both. An approach that strategically employs engineering to create the initial conditions necessary for life, then allows biology to take over, developing a self-sustaining ecosystem that can gradually evolve into something more stable over time. Instead of attempting to manufacture an entire atmosphere at once, hybrid terraforming methods would begin with targeted interventions, using controlled greenhouse gas releases to start warming the surface, while simultaneously seeding the planet with microbes designed to accelerate the process. Robotic systems could generate artificial heat, melting buried ice reserves, and creating pockets of liquid water where early microbial life could begin to establish itself. Engineered extremophiles, bacteria designed to endure Mars radiation, low pressure, and toxic soil, could be released in phases, feeding on minerals, producing small amounts of oxygen, and even altering the regolith to make it more hospitable for future plant growth. Over time, as atmospheric density increases, more complex life forms could be introduced, each step reinforcing the next in a carefully guided but largely autonomous process. In orbit, massive reflective mirrors could be positioned to direct sunlight onto select regions, providing warmth to areas where biological growth is most likely to succeed. Meanwhile, underground habitats shielded from cosmic radiation could serve as controlled test environments where small-scale ecological systems are established before being expanded to the surface. This gradual approach would avoid the overwhelming logistical challenges of fully terraforming the planet in a single effort, while ensuring that once life does take hold, it does so in a way that is sustainable rather than requiring constant human intervention. The advantage of a hybrid approach is that it acknowledges Mars' resistance to change while still taking decisive action to overcome its most immediate obstacles. Rather than attempting to transform the planet in one sweeping motion or waiting passively for natural processes to work on their own, this method strikes a balance between control and adaptation, using technology to set the foundation while allowing biological systems to evolve in ways that cannot always be precisely engineered. It is a long-term strategy, but not an endless one that aims to create an environment that, given enough time, may one day be capable of maintaining itself, where the planet is no longer an artificial construct of human engineering, but a place that can support life on its own. Whether Mars will ever reach that point remains uncertain, but if humanity does one day choose to reshape an entire world, it may find that the key lies not in forcing change or waiting for it, but in guiding it along a path that neither nature nor technology could achieve alone. 5. Modifying Mars' atmosphere. Mars, a cold and barren world, lacks the thick, life-supporting atmosphere that makes Earth so uniquely hospitable. Its air is thin, composed mostly of carbon dioxide, and unable to trap heat effectively, leaving the planet's surface exposed to harsh radiation and frigid temperatures. If humans ever hope to establish a long-term presence on Mars, one of the first challenges will be to modify its atmosphere, thickening it enough to make survival more feasible. This isn't simply a question of comfort, it's about necessity, about the possibility of walking on another world without being confined within a pressurized suit, about breathing with ease, or at the very least, making the environment more forgiving to human life and plant growth. Some of the most ambitious minds have contemplated ways to achieve this, ranging from releasing greenhouse gases to trigger a warming effect to mining the planet's frozen reservoirs of carbon dioxide and water. The idea is simple enough. If the atmosphere were denser, it would trap more heat, reduce the deadly radiation levels, and make it easier to maintain liquid water on the surface. But the methods are anything but simple. Some propose detonating nuclear devices at Mars' polar caps to release the trapped CO2, an idea that sounds like it belongs more in science fiction than in reality, yet is grounded in the fundamental principle of rapid atmospheric thickening. Others suggest giant orbital mirrors that could reflect additional sunlight onto the surface, artificially jump-starting a warming cycle that could cause sublimation of the existing ice. Even the introduction of engineered microbes, capable of metabolizing Martian materials and releasing gases, has been seriously discussed, a scenario in which the smallest forms of life would become the architects of a world's transformation. Yet, despite the theoretical possibilities, reality is unyielding. Mars' gravity is weak, only about 38% of Earth's, meaning that any added atmosphere would be vulnerable to being stripped away by the relentless solar wind. Without a strong magnetic field, like the one that shields Earth, the same forces that left Mars in its current state would continue to chip away at any progress made. The efforts to thicken the air would not just need to be immense but also sustained, requiring continuous replenishment of lost gases. This raises the question of whether the project is even viable in the long term, or if any attempt to terraform Mars would be an endless uphill battle against the laws of nature. For those who dream of making Mars a second home, the challenges are daunting, but that has never stopped human ambition before. The same species that built cities from deserts, that navigated vast oceans before truly understanding what lay beyond, that launched itself beyond Earth's atmosphere when such a thing was once thought impossible, would not be deterred by the cold silence of the red planet. There would be those who argue that the task is insurmountable, that Mars will never be anything more than a harsh, unyielding world where humans will always be visitors rather than residents. But then there would be those who look at the dust-covered landscape, the thin whisper of an atmosphere, the ice locked beneath the surface, and see the possibility of something more. The reality of the challenge may be immense, but the history of human progress has always been a story of reshaping the impossible into something tangible. Whether Mars will ever have an atmosphere thick enough to sustain an unprotected breath remains uncertain, but if there is one thing that can be predicted, it is that people will try, and they will keep trying, because that is what they have always done. Even if the challenge of thickening Mars' atmosphere seems immense, one of the most immediate and tangible sources of atmospheric gas already exists, locked away in the planet's polar ice caps. Unlike Earth's poles, where ice is mostly water, Mars' polar regions contain vast reserves of frozen carbon dioxide, a resource that, if released, could provide the first step toward a denser, more heat-trapping atmosphere. This is not just a theoretical curiosity, it is a possibility that has been considered by those who dream of transforming Mars from a barren wasteland into a place where human life can exist beyond the confines of a sealed habitat. The question is not just whether it can be done, but how, and at what cost. The simplest approach would be to accelerate the natural sublimation process, allowing the frozen CO2 to turn directly into gas and mix into the thin Martian air. Given enough time and heat, this would happen on its own during seasonal changes, as the ice naturally recedes in the Martian summer. But waiting for nature to take its course is not an option when the goal is to reshape an entire world. Some have imagined using large-scale mirrors, positioned in orbit, to focus sunlight onto the poles, intensifying the heat and forcing the ice to sublimate faster. Others have suggested scattering dark dust over the ice, reducing its ability to reflect sunlight and causing it to absorb more heat, a method that would mimic how dust storms on Mars can temporarily alter its temperature. But the more extreme ideas involve brute force, detonating nuclear devices to rapidly release the trapped CO2 in an explosion of energy, an idea that carries with it all the ethical and logistical concerns that come with using such destructive power on another world. Even if the gas were successfully released, it would not immediately turn Mars into a place where humans could survive without assistance. The increase in atmospheric pressure would be minimal at first, nowhere near enough to eliminate the need for pressure suits or allow liquid water to remain stable for long periods. But it could be a start, a shift in the balance that makes future efforts more viable. The problem, however, is that Mars has no way to hold onto an atmosphere indefinitely. Without a strong magnetic field, the same forces that stripped the planet's air away in the distant past would still be at work, slowly eroding any progress made. Releasing the trapped CO2 might be a way to push Mars toward a more habitable state, but it would not be a permanent solution unless followed by continuous efforts to replenish what is lost. And yet, Even with all these obstacles, the thought of standing on Mars and watching as the ice recedes, as the sky thickens ever so slightly, as the cold, lifeless air begins to shift towards something more recognizable, is not easily dismissed. It is not just about science or survival. It is about the deeply human need to reshape the environment, to take a world as it is and imagine what it could be. Those who look at the frozen CO2 trapped in the Martian ice do not see just a chemical compound locked away in the permafrost. They see a key, a possibility, a reminder that even the most unwelcoming landscapes can be altered with enough determination. Whether this approach will ever be used remains uncertain, but the idea that Mars is not beyond change is enough to keep the dream alive. Releasing the carbon dioxide trapped in Mars' polar ice caps might offer a temporary boost to the planet's atmosphere, but the limitations are clear. Mars simply doesn't have enough stored resources to sustain a significant and lasting transformation. If the goal is to create an environment where human presence is something more than a struggle against an unforgiving world, then relying solely on what Mars already has may not be enough. That realization leads to a far more ambitious possibility, one that would stretch human ingenuity beyond anything attempted before, importing volatiles from elsewhere, drawing upon the reservoirs of ice and gas locked within asteroids and the icy moons of the outer solar system. It is an idea that sounds almost like an act of defiance, as if humanity were attempting to rewrite the natural order of planets, pulling resources across the void of space to reshape a world according to its own design. The solar system is filled with raw materials that could, in theory, be redirected to Mars, bringing with them the building blocks of a thicker atmosphere. Water ice, ammonia, methane, all substances that could contribute to a warming effect and help trap heat once released into the Martian air, exist in abundance beyond the inner planets. The icy bodies of the Kuiper Belt, the rings of Saturn, the frozen surfaces of Europa and Enceladus, and the countless comets that drift through space all hold immense reservoirs of these volatiles, waiting in a state of deep freeze. Even closer, the asteroid belt between Mars and Jupiter contains water-rich bodies that could serve as stepping stones in the effort to terraform Mars. The challenge, of course, is not in identifying these resources, but in finding a way to move them across millions of kilometers of space and deliver them in a way that actually benefits the planet rather than simply creating chaos. There are those who imagine using carefully controlled impacts, steering icy asteroids or small moons into a calculated descent toward Mars, allowing them to crash into the surface and release their stored gases in a burst of heat and energy. It would be a process unlike anything seen before, a deliberate reshaping of a planet through celestial bombardment, with each impact thickening the air just a little more. But the risks are obvious. Miscalculations could lead to devastation rather than transformation, and even if everything went according to plan, the logistics of capturing and guiding these objects would be daunting beyond measure. Other proposals involve a slower, more controlled process, where ice is extracted in space, transported in smaller quantities, and gradually released into the Martian environment through processing stations or orbital dispersal systems. This approach would avoid the destructive force of direct impacts, but would require an infrastructure so advanced that it exists, for now, only in speculation. Yet for all its complexity, the idea is not entirely without precedent. Humans have already landed probes on comets, extracted samples from asteroids, and sent missions to some of the most distant objects in the solar system. The next logical step is not just to visit these worlds but to use them, to see them not as distant curiosities but as resources waiting to be tapped. If there is anything that history has shown, it is that when faced with the choice between adaptation and stagnation, humanity has always found a way to reach for what lies beyond, even when the odds seem insurmountable. Importing volatiles from the depths of space may seem like an impossible feat now, but if there is a future where people walk freely on Mars, where the sky holds enough density to scatter sunlight into softer hues, where the cold does not bite as deeply, it may be because someone, somewhere, decided that waiting for Mars to change on its own was never an option. 6. Increasing temperature on Mars. Bringing in volatiles from asteroids and icy moons could provide the raw materials needed to build a thicker atmosphere, but without warmth to keep those gases from freezing back into the surface, Mars would remain a cold and desolate world. The planet orbits farther from the Sun than Earth, receiving only about half the sunlight, and without a sufficient atmospheric layer to trap heat, what little energy reaches the surface is quickly lost to space. Without a way to raise the temperature, efforts to terraform Mars would be futile, like trying to light a fire in a windstorm. Since the planet itself lacks the geological activity to generate its own heat on a large scale, the only option is to look outward, to capture more of the Sun's energy and redirect it toward Mars in a way that forces the planet's climate to shift. The idea of using giant space mirrors to reflect sunlight onto the Martian surface is as ambitious as it is deceptively simple. In theory, massive orbital reflectors could be positioned at just the right distance to increase the amount of solar radiation reaching the planet, warming the atmosphere and triggering the sublimation of frozen CO2 from the poles. Unlike other strategies that require transporting or manufacturing new materials, this method relies on existing energy. Sunlight that is already traveling through space, just not in a way that benefits Mars. The scale of such a project, however, is nearly unimaginable. To make a significant impact, the mirrors would need to be kilometers across, made from ultra-thin reflective materials capable of surviving in space without tearing apart under micrometeorite impacts or radiation exposure. These structures would have to be deployed in precise orbits, angled to direct heat toward the planet's coldest regions, all while remaining stable enough to resist the gravitational forces of Mars and the Sun. But the technical challenges pale in comparison to the logistical ones. Launching such enormous structures from Earth would be prohibitively expensive, requiring either a space-based manufacturing industry or the ability to construct them from resources mined on the Moon or asteroids. Then comes the question of control. How to adjust the reflectors over time, how to prevent them from drifting off course, how to maintain them against the wear and tear of space. Even if those problems were solved, the ethical debate would remain. Changing the climate of an entire planet, even one as inhospitable as Mars, is an irreversible act. Something that could have unforeseen consequences not just for any future human settlers, but for whatever microscopic life might still linger beneath the surface. Yet despite the difficulties, the sheer audacity of the idea is a reflection of something deeply human. The refusal to accept limitations, the belief that the universe is not something to be observed from a distance, but shaped and engaged with. To someone standing on the surface of Mars, watching as the thin atmosphere shifts ever so slightly, as frost vanishes a little faster, as the air begins to hold just a fraction more heat, the presence of those distant mirrors in the sky would be more than just engineering marvels. They would be symbols of intent, proof that even on a world as cold and lifeless as Mars, warmth could be brought where none existed before, not by accident, but by the deliberate force of human will. Reflecting sunlight onto Mars with enormous space mirrors offers a gradual, controlled way to introduce warmth. But for those who see time as a constraint rather than a luxury, there are far more direct methods to accelerate the process. Instead of patiently redirecting energy from the Sun, some have imagined a solution that is more violent, more immediate. One that forces Mars into a new thermal state not through subtlety, but through sheer force. The concept is both simple and audacious. Redirect asteroids into controlled impacts, using their immense kinetic energy to generate heat, release trapped gases, and trigger large-scale environmental shifts that would otherwise take centuries. It is an idea that demands a level of precision bordering on the impossible, a delicate balance between destruction and transformation, where one miscalculation could spell disaster rather than progress. Asteroids travel through space at incredible speeds, and when one collides with a planet, the energy released is nothing short of cataclysmic. Even a relatively small asteroid, just a few hundred meters across, striking Mars at tens of kilometers per second, would unleash an explosion equivalent to thousands of nuclear bombs, carving out massive craters and sending shockwaves through the thin Martian air. But beyond the immediate destruction, the heat from such an impact would vaporize surface materials, releasing carbon dioxide, water vapor, and other gases trapped in the regolith, feeding the atmosphere with compounds that could thicken it over time. If enough asteroids were carefully directed to strike targeted locations, particularly the polar ice caps or regions rich in buried volatiles, the resulting heat could melt ice, produce temporary lakes, and set off a chain reaction of greenhouse effects that might tip Mars toward a more temperate state. The challenge, of course, is in the word controlled. Unlike space mirrors, which can be adjusted, repositioned, or deactivated, an asteroid impact is irreversible. Once set in motion, there is no second chance to correct an error. A miscalculated trajectory could send an asteroid crashing into a human settlement or a critical scientific outpost. A strike too powerful in the wrong location could send debris into orbit, creating a planetary ring of destruction that threatens future missions. There is also the question of scale. How many asteroids would be needed, and over what time frame? If only a handful of impacts are engineered, the heat generated might dissipate too quickly to make a lasting difference, while too many could destabilize the surface and turn Mars into a world battered by its own forced evolution. Yet the idea remains, not just as a theoretical exercise, but as a reflection of humanity's willingness to take risks in pursuit of something greater. The very notion of altering an entire planet with calculated asteroid strikes is both terrifying and awe-inspiring, a vision of a future where celestial bodies are not just obstacles to be avoided, but tools to be wielded. If such a plan were ever carried out, the moment of impact would be unlike anything seen before. An eruption of fire and dust, a wound carved into the Martian landscape with purpose rather than chance, a moment when Mars itself is forced to change, not by the slow workings of nature, but by the hands of those who refuse to wait. Slamming asteroids into the Martian surface would undoubtedly inject heat and release trapped gases, but the chaos of such an approach makes it difficult to sustain long-term control over the planet's climate. There is a raw, primal force in harnessing impacts, but precision is sacrificed for power, and if Mars is to be transformed in a way that allows stability, the process needs more than just bursts of violent energy. The atmosphere, once thickened, must also be maintained, and that means trapping heat efficiently rather than relying solely on temporary pulses of warmth. The natural Martian air is thin and composed mostly of carbon dioxide, which provides some greenhouse effect, but it is not nearly enough to prevent the cold from reclaiming any temporary gains. If Mars refuses to hold onto heat naturally, then the only choice left is to manufacture it artificially, filling the atmosphere with greenhouse gases tailored for the task of warming the planet. Unlike the sudden devastation of asteroid impacts, artificial greenhouse gas production is a methodical, controlled effort, one that mirrors how humans, perhaps unintentionally, have already reshaped Earth's climate. By introducing potent greenhouse gases such as perfluorocarbons, methane, or other synthetic compounds that trap heat far more effectively than carbon dioxide, Mars could be coaxed into a gradual and sustained warming process. These gases would linger in the atmosphere for decades or even centuries, ensuring that any heat introduced to the planet, whether from redirected sunlight, natural geological processes, or even industrial activity, remains trapped rather than dissipating into space. The trick, however, is creating enough of them in an environment where there is no existing industry, no biosphere to cycle gases naturally, and no easy way to replenish what is lost. One possibility is constructing large-scale chemical production facilities, either on the surface or in orbit, designed to manufacture greenhouse gases directly from Martian resources. Using elements extracted from the regolith, carbon locked in the soil, and hydrogen sourced from water ice, machines could synthesize powerful atmospheric compounds and release them in controlled amounts, steadily shifting the balance of heat retention. The process would not happen overnight. It could take centuries to fully saturate the air. But unlike asteroid impacts or mirror arrays, it would provide a predictable and adjustable pathway to warming the planet. Some have even imagined using automated factories, powered by nuclear energy or solar arrays, churning out greenhouse gases without human intervention, allowing Mars to slowly transform itself while its first settlers focus on survival. There is, of course, a haunting irony in using artificial greenhouse gases to terraform Mars when the same process has driven climate instability on Earth. On one planet, the excess release of heat-trapping compounds threatens to upend ecosystems and force desperate adaptation, while on another, those same gases could be the key to making the world habitable in the first place. On Mars, every molecule introduced into the sky would be part of a deliberate plan, carefully measured, adjusted, and controlled to prevent runaway effects. It is a slow but relentless process, one that requires patience, precision, and an acceptance that transforming a planet is not about forcing immediate change, but about setting something in motion that may only reach its full potential long after those who began it are gone. 7. Enhancing Mars' magnetic protection. Mars, that distant, rust-colored world, has long captured our imagination as humanity's potential second home. Yet, beneath its cold, barren surface lies a profound and often overlooked obstacle: its lack of a global magnetic field. It's strange to think that something invisible, something we can't touch or see, holds the key to turning this desolate planet into a thriving, habitable world. But when you look closer, it makes sense. On Earth, our magnetic field acts like an ancient, silent guardian, shielding us from the relentless bombardment of solar wind and cosmic radiation. Without it, the atmosphere would be stripped away, molecule by molecule, until the sky itself would vanish into the void. This is precisely what happened to Mars billions of years ago. In the distant past, Mars is believed to have had a thicker atmosphere, perhaps even flowing rivers and shallow seas. But as the planet's internal dynamo, its molten core, began to cool and solidify, the magnetic field that once protected it faded. With nothing to shield the planet from the sun's high-energy particles, the Martian atmosphere was slowly eroded, bleeding off into space. What remained was a thin, fragile layer of carbon dioxide, barely enough to whisper against the planet's surface, and certainly not enough to trap heat or sustain liquid water. It's eerie to imagine that Mars wasn't always this quiet, this empty. It once breathed with storms and rivers, with skies that might have been streaked with clouds. But when its magnetic heart stopped beating, the planet slowly suffocated. If humanity ever hopes to terraform Mars, to warm its surface, melt its polar ice caps, and awaken ancient riverbeds, we would need to reignite that protective shield. Otherwise, any atmosphere we attempt to create would be stripped away, just as it was before. Without a magnetic field, Mars is like a body without skin, vulnerable to the harsh radiation that floods through space. Every molecule of oxygen we release, every drop of water that evaporates, would simply be swept away by the solar wind. The idea of artificially generating a magnetic field for an entire planet seems almost like science fiction, but scientists are already beginning to explore possibilities. One proposal involves placing a powerful magnetic shield at the Mars-Sun Lagrange point, a region of gravitational balance between the two celestial bodies. From this position, a magnetic shield could deflect the solar wind before it ever reaches the planet, mimicking the protective bubble that Earth's magnetic field naturally provides. Another, more speculative idea involves attempting to restart the molten flow of Mars' core itself, though the scale of such an endeavor would be almost godlike. Yet, there's something deeply human about this ambition. We've always been creatures who refuse to accept the limits placed upon us. We build bridges across impossible chasms, harness fire to keep the darkness at bay, and now, we dream of reigniting the magnetic heart of a distant world. Perhaps it's not just about survival or scientific achievement. There's something almost poetic in the idea of reviving a dead world, breathing life back into a planet that was abandoned by nature itself. But the challenge is immense. Without magnetic protection, not only would the atmosphere be stripped away, but future Martian settlers would be constantly exposed to dangerous levels of cosmic radiation. This radiation penetrates deep into human tissue, damaging cells and DNA, slowly unraveling the very fabric of life. It's a silent, invisible threat, one that makes long-term survival on the Martian surface nearly impossible without massive underground shelters or heavy radiation shielding. And yet, the thought of standing beneath a Martian sky, watching clouds drift across a pale, orange horizon, is enough to drive humanity to try. Because in the end, this isn't just about colonizing another world. It's about transforming something lifeless into something living. It's about creating a future where humanity isn't bound to one fragile world, where we can reach across the cold void of space and touch the face of a world that has been waiting for billions of years to be awakened. To give Mars a magnetic field is to give it protection, yes, but it's also to give it a second chance. A chance to hold onto an atmosphere, to cradle oceans and rivers, to shelter forests and cities. And in doing so, perhaps we would be giving ourselves a second chance as well. proving that we are not merely creatures bound by gravity and circumstance, but beings capable of shaping entire worlds, of bringing warmth to the cold and light to the void. But even if we understand why Mars lost its atmosphere, the question remains, how do we shield the planet from that fate again? How do we stand between Mars and the relentless solar wind when the planet itself lacks the strength to protect itself? It's almost strange, this idea of humanity stepping in to do what nature can no longer do. Like cradling a fragile world in our hands, shielding it from the very cosmos that stripped it bare. And yet, the solutions being proposed feel less like science fiction and more like an eerie extension of our own technological evolution. One of the most promising concepts involves creating an artificial magnetic shield, an electromagnetic barrier positioned at a critical point in space known as the Mars-Sun Lagrange point, where the gravitational forces between the Sun and Mars are balanced. If we could position a massive magnetic field generator here, it could create a protective bubble, deflecting the solar wind before it ever reaches Mars. In a way, it's almost like giving Mars its own miniature magnetosphere, not by reigniting its core, but by placing a kind of invisible guardian between it and the Sun. It's fascinating, isn't it? The idea that something as intangible as magnetic force could stand against the raw violence of solar radiation. But there's something deeply human about this approach. It's not brute force. We're not trying to terraform Mars with fire and machinery, but with an understanding of invisible forces that have shaped planets and stars since the dawn of the universe. By harnessing electromagnetic fields, we wouldn't be fighting against the laws of nature. We'd be working with them. In a sense, we'd be bending space itself to protect Mars, creating a safe haven where an atmosphere could once again thicken, where water could flow without being ripped apart molecule by molecule. Another idea that pushes the boundary of imagination is the concept of space-based magnetic generators. Essentially a fleet of massive satellites or stations orbiting Mars, each emitting powerful magnetic fields that collectively form a protective shield around the planet. This approach feels more fragmented, more like weaving a net in space to catch the solar wind before it can reach the surface. Yet, there's something poetic about that too. A network of human-made machines, quietly humming with magnetic energy, slowly restoring what Mars lost billions of years ago. The beauty of these solutions lies in their elegance. They don't require us to drill into Mars' core or shatter its crust. They don't demand we force the planet to become something it's not. Instead, they allow Mars to be Mars, while we simply shield it from the forces that stripped it bare. And in doing so, we give it time. Time to hold on to heat, time to let the ice melt, time for ancient riverbeds to flow again. But these ideas aren't without challenges. The energy required to generate a magnetic field powerful enough to shield an entire planet is staggering. The engineering required to build and maintain these systems in the harsh environment of space pushes the limits of our current technology. And there's the question of permanence. Would these artificial shields need to remain active for centuries, or could they trigger a chain reaction that allows Mars' atmosphere to stabilize on its own? Yet, when you step back and look at the vastness of what we're attempting, the struggle feels almost inevitable. Humanity has always reached for things that seem beyond our grasp. We built cathedrals to touch the sky. We split the atom to understand the very essence of matter. And now, we dream of wrapping an entire planet in invisible magnetic threads, shielding it from the ancient winds of a dying star. In the end, the solutions we're exploring aren't just about science or technology. They're about something deeper. They're about reclaiming a world that was lost to time. About stepping into the role of protector, not conqueror. About giving Mars back what it lost, so that one day, beneath a thicker sky and a warmer sun, future generations could walk along the shores of ancient seas that we helped awaken. Not by brute force, but by understanding the delicate balance between magnetism, atmosphere, and life itself. 8. Introducing greenhouse gases. But shielding Mars from the solar wind is only part of the puzzle. Protection alone isn't enough to breathe warmth back into this frozen world. Even with a magnetic shield in place, the Martian atmosphere is still too thin, too fragile to trap heat. The planet's surface, exposed to the cold vacuum of space, loses what little warmth it receives from the sun almost instantly. It's a world where ice never melts, where ancient riverbeds remain dry and lifeless. And this is where the idea of introducing greenhouse gases comes in. Not to poison a world, as we've done on Earth, but to awaken one. It feels almost strange, doesn't it? On Earth, we fear these gases, these invisible pollutants that trap heat and destabilize our climate. And yet, on Mars, they could be the key to survival. Perfluorocarbons, or PFCs, are one of the most promising options. These are synthetic gases engineered by humans, with an extraordinary ability to trap heat. They linger in the atmosphere for centuries, absorbing infrared radiation and slowly warming the planet's surface. The irony is almost unsettling. On Earth, they're considered harmful pollutants, but on Mars, they could act as silent architects of a future atmosphere. Imagine it. Massive factories or orbital stations releasing these gases into the thin Martian air, not in reckless excess, but with careful precision. Over decades, these invisible molecules would begin to thicken the atmosphere, allowing heat to build up and hold onto what little sunlight reaches the planet. The polar ice caps, rich in frozen carbon dioxide, would slowly begin to sublimate, releasing even more greenhouse gases into the air. It would be a slow, almost imperceptible transformation, a planet gradually breathing warmth back into itself after billions of years of silence. There's something deeply human about this approach. It's not about forcing Mars to become Earth. It's about nudging the planet in the right direction, coaxing it to awaken through the very forces that threaten us here on our own world. And yet, there's a strange elegance to the idea of using synthetic gases, creations of human industry, to undo the work of cosmic time. We would be tapping into the same forces that warmed Earth during its ancient epochs, only this time, with intention. But the process wouldn't be instant. It could take centuries for the atmosphere to reach a pressure thick enough to trap heat and allow liquid water to flow. And in that time, the planet would slowly transform. The ice would melt. Dust storms would become storms of rain. Valleys carved by ancient floods might once again echo with the sound of water rushing through stone. And all of it, triggered not by some grand act of nature, but by the deliberate release of invisible, heat-trapping gases. Of course, there's a delicate balance to this. Too much, too quickly, and we risk creating a toxic atmosphere, one where humans could never breathe without machines. Too little, and the planet remains trapped in its frozen slumber. And there's something unsettling about the permanence of these gases. PFCs linger for tens of thousands of years. Once released, they cannot simply be removed. We would be committing ourselves to reshaping an entire world, with consequences that future generations would have to live with. Yet, maybe that's part of the beauty of it. This wouldn't be about instant conquest or colonization. It would be an act of patience, of quiet engineering, where humanity's role is not that of a conqueror, but of a caretaker. A species that, for the first time in history, learns to warm a world not with fire and destruction, but with invisible molecules drifting in the air, slowly turning a barren sky into something that can hold clouds and storms and life itself. It's strange to think that the key to Mars' rebirth might lie in the very gases that threaten Earth. But maybe that's fitting. We've spent centuries bending the forces of nature to our will, often with destructive consequences. But here, on this distant, silent world, we have a chance to do something different. To use that same knowledge, that same power, not to destroy, but to create. To give Mars back the warmth it lost, and with it, the possibility of something new. But even if we manage to thicken the Martian atmosphere with artificial greenhouse gases, there's still something missing. Something ancient and raw that Earth has always possessed, but Mars lost long ago. Heat from within. A living, breathing planet is not warmed solely by the sun. Beneath Earth's surface, molten rock churns and shifts, driving plate tectonics, creating volcanic eruptions, and releasing vast amounts of carbon dioxide and water vapor into the atmosphere. This process has played a critical role in shaping Earth's climate for billions of years, slowly balancing the planet's temperature and keeping the air rich enough to support life. Mars, however, is silent. Its volcanic giants, like Olympus Mons, the largest volcano in the solar system, have been dormant for millions of years. The planet's core has cooled, its geological pulse nearly extinguished. And yet, some scientists wonder, what if we could wake that ancient fire once more? It sounds almost absurd, the idea of humans reaching deep into the Martian crust, not to mine or extract, but to trigger volcanic eruptions on purpose. But beneath the surface, there is still heat. Not enough to drive plate tectonics, but perhaps enough to be coaxed, slowly and carefully, into awakening. The goal wouldn't be to create chaos or destruction, as volcanic eruptions on Earth often do, but to release gases trapped beneath the surface. Carbon dioxide, water vapor, and other greenhouse compounds that could further thicken the atmosphere and accelerate the warming process. By doing so, we wouldn't simply be adding heat from the sun or synthetic gases from our factories. We'd be reigniting a process that Mars itself once relied on, a slow, geological breathing that could feed the atmosphere from within. But how would we do it? One idea involves drilling deep into dormant volcanic chambers, injecting heat or even powerful explosives to destabilize the rock and trigger an eruption. It's the same principle that's been proposed here on Earth to release geothermal energy, but on Mars, the goal would be more ambitious, not just tapping into heat, but unleashing trapped gases that have been sealed beneath the surface for millions of years. Another possibility is targeting areas where magma may still exist closer to the surface, regions where ancient lava flows hint at more recent activity. By creating fractures in the crust, we could allow that molten rock to rise, releasing not only heat but vast clouds of carbon dioxide that would slowly blanket the planet. The scale of this idea is almost terrifying. To awaken the ancient heart of a planet is to play with forces that shaped entire worlds. And there's no guarantee that we could control it. A single eruption might release gas and heat, but too much activity could destabilize the fragile Martian crust, unleashing dust storms and seismic tremors that would make the planet even more hostile. And yet, there's something undeniably human about this ambition. We've always been drawn to fire, to the idea that we can shape the world not through brute strength, but by understanding the hidden forces beneath the surface. It's the same drive that led us to harness nuclear energy, to control fusion reactions, to split atoms. Only this time, we wouldn't be manipulating matter on a microscopic scale. We'd be reaching into the very bones of a planet, attempting to reignite the heat that once gave it life. What's haunting about this idea is that it feels like we'd be restoring something ancient, something Mars lost billions of years ago when its core cooled and its magnetic field faded. By triggering volcanic eruptions, we wouldn't be forcing the planet to become something unnatural. We'd be reminding it of what it once was. And in doing so, perhaps we'd be giving it the chance to breathe again, to warm itself from within, and to slowly awaken from the deep, geological slumber that has kept it cold and lifeless for so long. But it wouldn't be immediate. Even if we succeeded in triggering eruptions, the released gases would take decades, maybe centuries, to build up in the atmosphere. The surface would still be hostile, the air still too thin to breathe. Yet, in time, the skies would darken with volcanic ash, the polar ice would melt faster, and the atmosphere would begin to trap heat more effectively. The Martian soil, rich in ancient minerals, might begin to thaw, releasing frozen water and nutrients that could one day support microbial life, or even plants brought from Earth. It's a delicate balance, though. Too much volcanic activity, and Mars becomes a choking, ash-filled wasteland. Too little, and the effort is wasted, the gases dissipating into the thin sky before they can accumulate. Yet, this is what makes the idea so profoundly human. We aren't gods. We aren't terraformers on the scale of nature itself. We are creatures that understand just enough about the world to push it, ever so slightly, in the direction we need. To awaken a volcano is not to conquer a planet. It's to tap into something ancient and primal, to nudge a world that has been drifting through cold darkness for billions of years and remind it that warmth is still possible. That life, in some distant future, could once again rise from the dust. But even if we succeeded in awakening Martian volcanoes and releasing ancient gases trapped beneath the surface, that alone wouldn't be enough. The planet's thin atmosphere would still struggle to hold on to heat, and any warmth gained would eventually be lost to the cold vacuum of space. The real challenge lies in creating something that can sustain itself, a feedback loop that doesn't rely on constant human intervention, but one that allows Mars to begin heating itself from within. This is where the idea of triggering a self-sustaining greenhouse effect becomes almost hauntingly beautiful, because it's not about forcing Mars to become something it's not. It's about guiding it, ever so subtly, back toward a forgotten state of equilibrium. On Earth, the greenhouse effect is often seen as a destructive force, one that humanity has unwittingly amplified through industrial emissions. But in its natural form, it's the very mechanism that keeps our planet warm enough for life to exist. Carbon dioxide, methane, and water vapor trap heat from the sun, preventing it from escaping back into space. Without it, Earth would be a frozen, lifeless rock. Mars once had this too, billions of years ago when its atmosphere was thick and volcanic activity was constant. But when the planet lost its magnetic field, solar winds stripped away that protective layer, and with it, the delicate balance that allowed heat to accumulate. What we're attempting now is almost like lighting a fire in a world that has long forgotten what warmth feels like. Except the fire isn't made of flames, but of invisible gases drifting through the air. The key lies in triggering a chain reaction by releasing greenhouse gases, whether from artificial sources like perfluorocarbons or through volcanic activity. We begin to trap more heat. That heat, in turn, melts the polar ice caps, which are rich in frozen carbon dioxide. As the ice sublimates, even more CO2 is released into the atmosphere, thickening it further and accelerating the warming process. The more the planet warms, the more ice melts, and the more gases are released. It's a loop, a delicate but unstoppable cycle that, once set in motion, could continue for centuries without human intervention. What's unsettling, though, is how fragile this process would be in the beginning. Mars' atmosphere is so thin that any warmth gained would quickly radiate back into space if the greenhouse effect isn't strong enough to hold on to it. It's like trying to catch smoke in your hands. There's a moment where everything could slip through your fingers if you don't act fast enough. This is why the initial steps are so critical. Releasing powerful, long-lived gases like PFCs can create a temporary heat trap, giving the planet enough time to trigger its own natural feedback loop. It's almost as if we're giving Mars a spark and then stepping back to let the fire spread on its own. But what makes this idea feel so profoundly human is that we're not simply engineering a world from the outside. We're tapping into ancient forces that have already shaped planets and atmospheres across the universe. We're not inventing the greenhouse effect. We're reawakening it, guiding Mars back toward a forgotten path that it once walked billions of years ago. And once that cycle begins, there's no turning back. The ice melts, the atmosphere thickens, the surface warms, and slowly, the planet begins to breathe again. It wouldn't happen overnight. The process could take centuries, maybe even thousands of years. And during that time, Mars would remain a world of extremes. Violent dust storms, toxic air, and freezing temperatures. But beneath that chaos, something would be stirring. The soil would begin to thaw. Ancient riverbeds might fill with liquid water for the first time in eons. The sky, once thin and pale, would begin to darken with clouds. And perhaps, eventually, the planet would reach a point where plants could survive, feeding off the carbon dioxide in the air and releasing oxygen, pushing the atmosphere further towards something that could sustain life. What's haunting is that once this process begins, we wouldn't be able to stop it. It would be like waking something ancient and unstoppable. A slow, geological heartbeat that would continue long after we are gone. And maybe that's the most human thing of all. We wouldn't be conquering Mars. We'd be guiding it, nudging it back toward a state it was always meant to reach. Not for ourselves, but for future generations who might one day walk beneath Martian skies and feel the warmth of a world we helped awaken. 9. Water extraction and distribution. The idea of extracting water from the melting polar ice caps and distributing it to regions plagued by drought evokes a strange intersection between human ingenuity and desperation. It is a vision born not from triumph, but from the quiet terror that accompanies the slow unraveling of Earth's equilibrium. In the vast, desolate stretches of the Arctic and Antarctic, ancient glaciers fracture and weep into the sea, their crystalline bodies dissolving into the swelling oceans. To the eye of the scientist and the engineer, these melting giants are not merely symbols of planetary decay, but untapped reservoirs that could quench the thirst of parched landscapes and failing agricultural heartlands. Imagine the hands that would labor to harness this water, the towering vessels that would anchor themselves near the edges of these crumbling ice shelves, siphoning the meltwater into colossal containment systems. The sheer scale of such an operation would require not only advanced technology, but the relentless toil of countless individuals, operating in the shadow of an environment that feels almost otherworldly. The ice itself, ancient and pure, would be captured and redirected, flowing into vast pipelines that stretch across oceans and continents, weaving through underwater arteries and resurfacing in the desiccated soils of once fertile plains. Yet beneath the mechanics of this endeavor lies something more profound: the quiet suffering of communities whose wells have long run dry, whose crops wither beneath an unrelenting sun. The farmer who watches his fields crumble to dust, the mother who walks miles for a single vessel of water, the child whose future is bound to the whims of a changing climate. These are the human echoes that ripple through the vast infrastructure of water redistribution. There is a cruel irony in the idea that the collapse of polar ice, driven by human-induced warming, might become the very lifeline for those facing the consequences of that same warming. But this is not a simple equation of survival. The transportation of polar water would demand enormous energy, international cooperation, and geopolitical negotiation. Nations already embroiled in disputes over access to freshwater rivers and aquifers would be drawn into a web of power and control, where the flow of water becomes as strategically vital as oil or gas. Who controls the ice? Who owns the water that drips from the ancient glaciers, carved from a world before humanity's rise? And as the ice melts faster than we can capture it, would we be chasing an illusion, always one step behind the tide of destruction we have set into motion? There is something haunting about the thought of water traveling thousands of miles from the Arctic's dying realm to the cracked earth of a distant continent. It is as though the planet itself is bleeding, and we are desperately attempting to catch the lifeblood before it is lost to the sea. Yet, within this bleak vision, there is also a testament to human resilience. The refusal to simply accept collapse, the drive to engineer a future even from the ruins of a broken world. But as the ice flows southward, carrying with it the ancient memory of millennia past, one cannot help but wonder whether we are truly salvaging life, or merely prolonging the inevitable reckoning with our own nature. And so, as humanity contemplates the fleeting streams of polar meltwater, attention inevitably shifts downward, beneath the surface where ancient ice lies entombed, hidden from the sun's relentless gaze. Subsurface ice mining is not merely a technological ambition but a manifestation of necessity, born from the same desperation that drives us to chase the fading edges of polar ice. Here, in the depths of frozen Earth, beneath the permafrost and ancient glaciers, lies a world where water is locked away in crystalline slumber, untouched by the violent churn of oceans and the rising heat of the atmosphere. In this realm, the miner becomes an explorer, descending into the Earth's cold, forgotten veins to harvest ice that has endured for millennia. It is a haunting endeavor, one that echoes the age-old struggles of those who once delved into the earth for coal or precious metals. Except now, it is not wealth they seek, but the very essence of life. Imagine the solitary figure, encased in protective gear, operating heavy drilling equipment in the heart of the Arctic tundra or the Martian regolith, where subsurface ice promises survival for future colonies. The hum of the machinery vibrates through the frozen ground as drills pierce ancient layers of compacted ice, extracting cores that shimmer with a pale, ghostly light. A light that carries the memory of ancient atmospheres and forgotten ages. Yet, beneath the machinery and the engineering marvels lies the quiet vulnerability of those who depend on this effort. In remote regions where surface water has vanished, indigenous communities and isolated outposts look to these hidden reserves as their final hope. The miner who labors in the cold, carving tunnels into the icebound earth, knows that the water he extracts will flow through pipes and filtration systems to distant villages where children's lips crack from thirst and crops wither in barren soil. There is a strange intimacy in this act of retrieval, as if pulling life itself from the frozen bones of the planet. But this endeavor is not without consequence. The disturbance of ancient ice releases more than water. It unseals the trapped breath of ancient epochs, unlocking methane and carbon dioxide that have lain dormant for eons. In our quest to quench our thirst, we risk awakening new forces that further accelerate the planet's unraveling. It becomes a delicate dance between survival and self-destruction, where human hands reach into the past to salvage a future that grows increasingly fragile with each passing year. In the end, subsurface ice mining is not merely a technological pursuit but an existential struggle, one that reveals both the brilliance and the folly of humanity. We are creatures bound to a world we have altered beyond recognition, yet still driven by an insatiable will to survive. And as the drills bite deeper into the earth, carving pathways through ancient frost, one cannot help but feel the weight of time pressing against us, as if the ice itself remembers a world before our arrival and mourns the one we are leaving behind. Yet, when the Earth's depths and polar veins prove insufficient, the human gaze inevitably drifts upward beyond the fragile atmosphere, into the cold, infinite darkness where ancient celestial bodies drift in silent orbits. Water-rich asteroids, scattered across the asteroid belt and the distant reaches of the solar system, become not objects of idle curiosity, but lifelines suspended in the void. It is a vision that feels almost mythic, dragging fragments of primordial ice from the heavens to quench the thirst of a world that has long squandered its own resources. But this endeavor is no longer confined to the realm of speculative fiction. It is an ambition fueled by desperation and driven by the relentless ingenuity that defines the human spirit. Picture the pilot of a spacecraft, a solitary figure navigating the vast emptiness, guided by the distant shimmer of an ancient asteroid that has drifted untouched since the birth of the solar system. The asteroid itself, a jagged monolith of rock and ice, carries within it the frozen remains of ancient comets and interstellar dust, remnants of cosmic collisions that predate Earth's first oceans. The pilot's vessel, equipped with autonomous harpoons and gravitational anchors, latches onto the asteroid's surface, stabilizing the tumbling giant before redirecting its trajectory toward Earth's orbit. It is a delicate operation, one that requires precision and patience, for a single miscalculation could send the asteroid hurtling into the vastness of space, or worse, toward catastrophic collision with the planet it seeks to replenish. Yet behind this technological feat lies the quiet yearning of those who wait below. Farmers whose fields crack beneath relentless drought, communities where children carry empty vessels across sun-scorched terrain, and cities where reservoirs shrink to dust. For them, the arrival of an asteroid harvested from the heavens is not a symbol of conquest, but salvation. As the asteroid is carefully guided into Earth's gravitational embrace, robotic systems extract its frozen bounty, melting and purifying the ancient ice before channeling it into pipelines and aquifers that have long run dry. There is something both awe-inspiring and profoundly melancholic in this act, as if humanity, having drained the Earth of its lifeblood, must now reach beyond its cradle to survive. But the endeavor is fraught with peril. The manipulation of celestial bodies is an act that borders on hubris, for even the smallest miscalculation could unleash unimaginable devastation. And beyond the risks of collision and contamination lies a deeper question. What does it mean for a species to plunder the heavens in search of water when the very planet it calls home is hemorrhaging life due to its own reckless actions? In this pursuit, humanity becomes both creator and destroyer, reaching toward the ancient bones of the cosmos in a desperate bid to escape the consequences of its own making. Yet, in the pale light of the asteroid's descent, there is also a quiet testament to human resilience. A refusal to surrender to entropy, a relentless drive to carve existence from the void. And as the water flows from ancient ice into the veins of a dying world, one cannot help but wonder if, in this act of celestial harvesting, we are not merely quenching our thirst, but confronting the very fragility of what it means to endure in a universe that was never meant to sustain us. 10. Making Martian soil suitable for agriculture. And when the water flows not from Earth's veins nor from ancient celestial bodies, but from the ice trapped beneath the regolith of a distant world, the struggle becomes something altogether more primal. An effort not only to sustain life, but to create it where none has ever existed. The Martian soil, a barren and iron-oxidized canvas that stretches endlessly beneath a pale pink sky, holds within it both promise and peril. To the eye of the geologist, it is a mineral-rich tapestry formed over billions of years by volcanic activity and relentless dust storms. Yet, to the hands of the would-be farmer, it is an alien medium poisoned by toxic perchlorates and starved of the vital nutrients that cradle life on Earth. Imagine the colonist, encased in a pressurized habitat that hums softly against the relentless winds outside, kneeling over a tray filled with Martian regolith. His gloved hands sift through the fine, rust-colored dust, feeling the grit slip through his fingers, sterile and lifeless. The challenge is not merely to plant seeds and hope they grow, but to transform this ancient, inert material into something that can nourish roots, support microbial life, and cradle the fragile tendrils of sprouting vegetation. It begins with the removal of perchlorates, toxic compounds that would poison the cells of any earthborn plant. Through chemical washing or microbial treatment, the colonist slowly strips away these lethal elements, freeing the soil from its most immediate threat. Yet, what remains is still devoid of organic matter, lacking the rich humus and microbial ecosystems that breathe life into Earth's soil. Here, human ingenuity becomes the architect of fertility. Compost from human waste, decaying plant material, and specially engineered bacteria are introduced, slowly weaving life into the sterile Martian dust. The microbes, ancient allies from Earth, begin to break down minerals, releasing essential nutrients like nitrogen and phosphorus, while binding the loose regolith into a more stable, moisture-retaining structure. The colonist watches as the soil darkens, as the first fragile sprouts push upward toward the dim Martian sunlight, their roots stretching into the soil that was once lifeless rock. But beneath this triumph lies an ever-present fragility. The thin Martian atmosphere offers no protection from cosmic radiation, and the soil itself holds a cruel irony. An abundance of iron and magnesium, yet a scarcity of potassium and essential trace elements. With meticulous care, the colonist adjusts the nutrient balance, adding calcium to neutralize the acidic pH and supplementing missing elements through hydroponic solutions drawn from the ice below the surface. Every step is an act of delicate manipulation, an effort to mimic the ancient cycles of decay and renewal that Earth perfected over eons. And yet, there is something deeply human in this endeavor. It is not merely the pursuit of survival, but an act of defiance against the cold indifference of an alien world. To coax life from the dust of Mars is to bridge the chasm between Earth and the cosmos, to carry the memory of green fields and ancient forests into a world that has never known such things. The colonist, tending to fragile seedlings beneath the glass domes of a Martian greenhouse, is not just a farmer, but a pioneer, weaving Earth's legacy into the fabric of another planet. And as roots burrow into the transformed soil, as leaves unfurl toward the pale sun, one cannot help but feel that in this fragile act of cultivation, humanity is not merely surviving the void, but slowly, stubbornly, beginning to belong to it. And beneath the fragile roots that grasp at Martian soil, beneath the compost and the carefully balanced nutrients, lies something far older and more elusive. A silent force that has shaped the very foundation of life on Earth, and now holds the key to making barren worlds fertile. Bacteria and microorganisms, ancient and invisible architects of the Earth's crust, are the true alchemists of soil formation. Long before the first forests rose or the first creatures walked upon the land, microbial life thrived in the primordial Earth, breaking down rock, cycling nutrients, and weaving the intricate web of organic matter that would one day cradle towering trees and endless grasslands. Picture the microbial world, an ancient realm hidden from the naked eye, where colonies of bacteria cling to mineral surfaces and slowly secrete acids that dissolve rock into its elemental components. These microscopic chemists, through the slow and relentless process of weathering, unlock phosphorus, potassium, and calcium from stone, releasing them into the soil and making them available to plant roots. Cyanobacteria, some of the oldest life forms on the planet, capture sunlight and convert carbon dioxide into organic matter, while nitrogen-fixing bacteria draw enough nitrogen from the atmosphere and transform it into ammonia, nourishing plants and fueling entire ecosystems. But there is something more intimate at play here, a quiet partnership forged over billions of years. In the darkness of the soil, mycorrhizal fungi form intricate networks that extend from plant roots, reaching deep into the earth and extracting water and nutrients from distant mineral pockets. In return, plants offer sugars and carbon, feeding these fungal allies and sustaining the underground symbiosis. Bacteria and fungi break down decaying plant matter, transforming dead leaves and fallen branches into rich humus, the dark, fertile layer that gives soil its structure and life-giving power. Without these unseen beings, the Earth's surface would be little more than sterile dust, incapable of supporting the vast diversity of life that now thrives upon it. Yet, for all their power, these microorganisms are fragile, vulnerable to the disruptions of human industry and climate change. The heavy plow that turns the earth and exposes the delicate microbial world to the burning sun, the pesticides that poison the bacterial colonies, the acid rain that leaches nutrients from the soil. These are the wounds we inflict on the ancient web that sustains us. And as we look to distant worlds, to Martian soil and lunar dust, it is these humble organisms that will become our greatest allies, seeding life where none has ever taken root. There is something almost poetic in this, that the oldest and smallest beings on Earth hold the power to terraform alien landscapes and breathe fertility into the barren. The farmer who kneels in dark earth, feeling its richness between their fingers, is not merely tending to plants, but to an ancient lineage of microbial architects that have shaped the world from the shadows. And as humanity reaches further into the cosmos, it is these invisible companions that will quietly follow, carrying with them the memory of Earth and the promise of life in places that have never known the whisper of wind or the touch of rain. And so, with the silent labor of bacteria and fungi weaving life into the soil, the dream of Martian farming begins to shimmer on the distant horizon, not as an abstract vision, but as a fragile possibility tethered to human hands and ancient microbial wisdom. The barren plains of Mars, with their ochre dust and iron-laden regolith, seem hostile to life at first glance, a world where the atmosphere is thin, carbon dioxide-rich, and devoid of the gentle rains and organic decay that have shaped Earth's fertile landscapes. Yet, beneath the surface, within the dark cavities of pressurized greenhouses and bioengineered habitats, life could quietly take root, guided by human ingenuity and the resilience of microscopic life forms. Imagine the Martian farmer, a lone figure within the confines of a sealed habitat, tending to rows of crops that stretch toward artificial light. The soil beneath the plants, once sterile and toxic, has been carefully cleansed of perchlorates and enriched with compost derived from human waste and bioengineered microbes brought from Earth. Each handful of regolith, once lifeless, now teems with nitrogen-fixing bacteria, carbon-sequestering fungi, and decomposing microbes that slowly transform the ancient dust into something that can cradle roots and hold moisture. The farmer monitors the pH levels and nutrient balance with meticulous care, adding potassium and calcium to compensate for the mineral deficiencies of Martian soil, while carefully controlling the levels of carbon dioxide within the habitat to accelerate photosynthesis. But the struggle is not merely chemical. The thin Martian atmosphere allows cosmic radiation to seep through, threatening the fragile cellular structures of plants. Shielding the crops beneath layers of regolith or within underground chambers becomes necessary, while carefully calibrated LED lights mimic the wavelengths of sunlight that plants have evolved to crave. Water, extracted from subsurface ice or harvested from the planet's thin atmosphere, is rationed with precision, trickling through hydroponic systems that prevent evaporation in the dry, alien air. Every drop is precious, every leaf that unfurls a quiet triumph against the sterility of an ancient world. Yet, there is something deeply human in this act of cultivation, a stubborn refusal to accept the cold desolation of Mars as final. The farmer who kneels to inspect the first green shoot pushing through the Martian dust is not simply growing food. They are weaving Earth's biological legacy into the fabric of an alien world. And with each harvest, each bowl of leafy greens consumed beneath the pale light of a distant sun, humanity takes another step toward belonging to a world that has never known life. But the path is fraught with uncertainty. The closed-loop systems that recycle nutrients and water are delicate, vulnerable to mechanical failure or microbial imbalances that could collapse an entire ecosystem. The psychological toll of isolation and the sterile, unchanging Martian landscape weighs heavily on the human mind, threatening the spirit that sustains this fragile endeavor. Yet, in the quiet rhythm of planting and harvesting, in the humble act of coaxing life from dust, there lies an ancient connection to the earth that humanity carries with it across the void. And perhaps, in the dim light of a Martian greenhouse, where fragile roots stretch into soil shaped by human hands and microbial toil, there is a glimpse of something deeper. A quiet defiance against the cold indifference of the cosmos and a stubborn belief that life, once seeded, will always find a way to endure. 11. Introducing microbial life to Mars. Imagine standing on the barren, windswept surface of Mars, the ochre-colored dust stretching endlessly under a dim, rust-colored sky, the air around you thin and suffocating, utterly devoid of the oxygen you so effortlessly breathe on Earth. Every breath in a place like this must be extracted from carefully maintained supplies, a fragile tether to life in an environment wholly indifferent to human existence. But what if Mars could be changed? What if, instead of carrying oxygen with us in bulky tanks and struggling to maintain pressurized habitats, the planet itself could be nudged towards habitability, not through vast terraforming projects requiring centuries of engineering, but through something far more fundamental, something microscopic? Life itself? Scientists have long considered the idea of using bioengineered bacteria to do what Earth's earliest organisms once did: transform an inhospitable atmosphere into one capable of sustaining complex life. Long before plants covered the land, before animals swam through the seas, the Earth was just as unwelcoming as Mars is now. The atmosphere was choked with carbon dioxide, and oxygen, the very gas that fuels human existence, was nearly absent. But deep in the ancient oceans, primitive bacteria began a quiet revolution. They consumed sunlight and carbon dioxide, releasing oxygen as a byproduct, and over millions of years, they altered the composition of the air itself, paving the way for the explosion of life that would follow. This slow, relentless process, known as the Great Oxygenation Event, was not the result of intelligent planning or grand engineering, but of life simply existing and interacting with its environment. Now, as humanity gazes outward toward Mars, we find ourselves in a position strangely parallel to that of those ancient microbes, standing at the precipice of planetary transformation. The question is no longer whether life can change a world. We know it can, but whether we can guide and accelerate that process with intention. Scientists are exploring bioengineered bacteria, meticulously designed to survive the extreme conditions of Mars while performing the same function their ancient ancestors once did on Earth. These organisms would not only need to withstand harsh radiation and freezing temperatures, but also thrive in an atmosphere almost entirely composed of carbon dioxide, extracting what they need while releasing precious oxygen. To even consider such an endeavor, researchers must design microbes that can withstand conditions unlike anything found on Earth. The Martian soil is dry and laced with toxic perchlorates, which can be lethal to many forms of life. The air is thin, with less than 1% of Earth's atmospheric pressure, meaning that even if a microbe were to produce oxygen, it would dissipate almost immediately. And yet, there are extremophiles on Earth, bacteria that survive in the deepest, darkest corners of the planet, thriving in acidic lakes, frozen tundras, and scorching hydrothermal vents that hint at the resilience required. By modifying the genetic makeup of these hardy microbes, scientists can potentially create organisms suited to Mars, ones that can endure its extremes and begin the slow, methodical process of reshaping the atmosphere. But even with the most sophisticated bioengineering, there are limits. The process of atmospheric change is not something that happens overnight, or even in a human lifetime. The microbes would need not only to survive, but to multiply, forming self-sustaining colonies capable of continuing the work long after the initial experiment. It's not just a question of designing the right bacteria. It's a question of ensuring that once introduced, they don't simply vanish in the face of radiation, extreme cold, or lack of nutrients. Some propose building protective environments, small-scale experimental greenhouses on Mars where microbes could be nurtured and studied, their oxygen output measured, their survival rates analyzed, and their adaptability observed. If they can establish themselves in even the most controlled of environments, it could serve as the first small step towards something greater. Beyond the scientific challenges, there is an ethical dimension to all of this. Introducing life to Mars, even microbial life, would be a defining moment in humanity's interaction with the cosmos. Some argue that Mars should be preserved in its untouched state, a world untainted by earthly life until we are certain of what already exists there. Others believe that if we are to inhabit Mars, even in the distant future, we must take steps toward making it more hospitable, and that life, once introduced, has the right to thrive and evolve just as it did on Earth. There is also the lingering question of time. If we begin such a process, would we ever see its results, or would it be a gift to a future we will never witness? Despite the uncertainty, the idea remains an irresistible possibility. A world that is now sterile and silent could, over centuries, begin to carry the whispers of an atmosphere, the faintest breath of oxygen building slowly over time. The same mechanisms that once turned Earth from a lifeless rock into a thriving planet could be guided, shaped, and set into motion again, not through brute force but through the smallest of interventions. An experiment of patience, resilience, and the fundamental nature of life itself. If bioengineered microbes were the first whisper of life on Mars, the creation of a biologically active soil layer would be the first breath. A crucial step toward making the planet not just marginally more hospitable, but capable of sustaining life beyond the microscopic. While the introduction of oxygen-producing bacteria might alter the atmosphere over time, no human could survive in a world where the ground itself remains dead. Barren, lifeless dust incapable of supporting even the most primitive plant. A planet is not just its air, but its soil, and without the intricate, invisible network of life that makes Earth's land fertile, Mars would remain little more than a cold, unyielding desert, no matter how much oxygen eventually lingers in the thin sky above. On Earth, soil is not merely crushed rock. It is a living system, a delicate and deeply interwoven web of microorganisms, fungi, decomposing organic matter, and countless microscopic interactions that make it what it is. A handful of rich Earth soil contains more life than the entire surface of Mars, a teeming, breathing world beneath our feet that recycles nutrients, breaks down waste, and allows plants to take root. Without these unseen processes, plants would not simply struggle on Mars. They would fail entirely, unable to extract what they need from a ground that has never known life. If humans ever hope to establish anything more than a temporary presence, they must first build the foundation for life itself, not just in the air, but in the very dust they walk on. But Mars offers no easy starting point. Its regolith, though fine and powdery, is not soil in any meaningful sense. It is sterile, sharp-edged, and laced with toxic perchlorates, chemical compounds that interfere with biological processes and render the ground hostile to earthly life. It lacks the organic matter that makes terrestrial soil fertile, the decomposed remnants of past life that plants depend on to grow. The challenge, then, is not just introducing microbes, but engineering a process by which Martian dust can be transformed into something more, something that mimics the slow, complex evolution of Earth's soil, but on a timescale that is useful for human habitation. Some of the first steps may involve using bioengineered bacteria, not just for oxygen production, but for breaking down perchlorates and altering the chemical composition of the Martian regolith. Certain Earth bacteria are already capable of metabolizing these toxic compounds, and if modified for the conditions of Mars, they could begin the long process of detoxifying the ground, stripping it of its lethal properties and making it more chemically suitable for future biological activity. But soil is more than just chemistry. It is structure, it is texture, it is the balance of water retention and aeration that allows roots to spread and microbial life to flourish. Even with detoxified regolith, the ground would remain loose and unstable, unable to hold nutrients or sustain the intricate web of fungi and bacteria that give Earth's soil its richness. Fungi may hold part of the solution. On Earth, mycorrhizal fungi form vast underground networks, binding soil together, breaking down minerals, and forming symbiotic relationships with plant roots, exchanging nutrients in ways that are fundamental to the health of nearly every ecosystem. If these fungal networks could be introduced alongside bacteria, they might provide not just biological activity but structure, binding Martian dust into something that begins to resemble real soil. The challenge, of course, lies in keeping them alive in an environment where temperatures drop far below freezing, water is nearly non-existent, and radiation constantly bombards the surface. In controlled environments, sealed biodomes, experimental greenhouses, or artificially warmed underground chambers, these networks could be nurtured, their ability to survive tested, their growth carefully managed as they begin the slow process of transforming the dead ground beneath them. Organic matter presents yet another hurdle. On Earth, soil is enriched by the endless recycling of life and death. Fallen leaves, decaying plants, the slow breakdown of animal remains, all of it feeding back into the ground, nourishing what comes next. Mars has no such cycle, no history of life to leave behind the rich humus that makes Earth's soil so vibrant. If plants are to grow there, they must be given not just detoxified and structured soil, but nutrients, the elements they require to sustain themselves. This might mean the introduction of earth-based compost materials, the careful management of waste products from any human presence, or even the production of synthetic organic matter designed to mimic the natural decomposition that occurs effortlessly on our home planet. All of this, the bacteria, the fungi, the organic matter, would not be a single solution but a slow, deliberate process, each step building on the last, each experiment informing the next. The first successful efforts would be small, fragile ecosystems, patches of engineered soil carefully maintained within protective structures, observed as they developed the ability to sustain themselves. Over time, these patches could expand, tested in increasingly harsh conditions, exposed gradually to the Martian environment in a controlled manner, their survival shaping the approach for larger-scale projects. What this represents is not just an experiment in planetary science, but something deeply human, a reflection of our own history, our ability to cultivate and shape the world around us. Thousands of years ago, early humans took wild, untamed landscapes and bent them to agriculture, carving out fertile ground where none had existed before, learning through trial and error how to make the land support them. Now, as we look toward Mars, the challenge is both similar and entirely alien. We are no longer shaping an environment that has known life, altering an ecosystem that has already evolved, but building from nothing, creating a foundation for life where none has ever existed. It is not an overnight process, not an easy fix, not something that will be completed in a single generation. But if successful, it would be the first true sign that Mars is no longer just a place to visit, no longer just an outpost of survival, but something more, a world that, however slowly, is beginning to wake up. But shaping an environment, especially one as untouched as Mars, is never without consequence. If microbes are to be introduced to transform the soil, to alter the atmosphere, to create the first threads of a living system, then the question must also be asked: what happens when they do not behave as expected? Life, once set in motion, does not remain obedient to human intentions. It spreads, adapts, mutates, finds new niches where it was never meant to survive, and sometimes it does so in ways that are impossible to predict. The very process that makes microbial life such a powerful tool, its ability to multiply rapidly, to consume and alter its surroundings, to persist against odds that should have erased it, also makes it a risk unlike any other. Once it takes hold, there may be no way to take it back. On Earth, microbial life is balanced by an entire web of interactions. Predators that keep bacterial populations in check, environmental factors that limit growth, competing species that prevent any one form of life from overrunning the rest. But Mars, in its current state, has none of these checks and balances. If an introduced microbe finds a way to survive in that environment, if it thrives beyond the controlled enclosures where it was first tested, there is no natural force that will restrain it. A bacterium engineered to break down perchlorates and detoxify Martian soil could, in a worst-case scenario, continue breaking down other compounds in ways that were never intended, rendering the ground even more inhospitable rather than less. A microbe designed to produce oxygen might also consume critical resources in ways that disrupt future attempts at growth, outcompeting other life forms that are necessary for a stable system. Then there is the question of mutation. Even in controlled environments, microbes evolve. A slight shift in genetic expression, a minor adaptation to radiation exposure, an unexpected response to low gravity. Over time, the microbes that exist on Mars may not be the same as those that were first introduced. What begins as a carefully designed system could become something entirely unpredictable, not because of human error, but because life itself is not static. The very process of survival demands change, and on a planet where conditions are extreme, that change may happen in ways that scientists did not foresee. A microbe that was once harmless could develop new traits that allow it to spread uncontrollably, to consume resources vital for future settlers, or to create byproducts that interact with the Martian environment in dangerous ways. Beyond the physical risks, there is the unknown. What happens if microbial life introduced by humans encounters something that was already there? Mars has long been considered a barren world, and no evidence of native life has ever been confirmed, but the absence of proof is not proof of absence. If Mars does, in some deep underground reservoir or within protected layers of ice, harbor its own microbial ecosystems, then the introduction of Earth life could be catastrophic, not just for the survival of Martian microbes, if they exist, but for any attempt to understand them. A single, uncontrolled spread of Earth bacteria could obscure the evidence of an entirely separate origin of life, forever corrupting the search for something that might answer one of humanity's oldest questions. Are we alone? And if Martian life does exist, even in the most primitive form, then the danger shifts. An unknown microbial system, suddenly forced into competition with an invasive species from Earth, could respond in ways that no one can predict. It could die out, taking with it an evolutionary history unlike anything ever seen before. Or it could fight back, introducing biochemical interactions that humans have no immunity to, no understanding of, no way to anticipate until it is too late. Even in the best of cases, where no Martian life exists and introduced microbes behave exactly as expected, containment remains a challenge. Mars is not a controlled laboratory, and once something spreads beyond the limits of an artificial habitat, there is no way to fully control where it goes. Dust storms, shifting temperatures, unexpected chemical reactions in the soil. Any one of these could transport microbes far beyond their intended range, depositing them in places where they might survive in dormancy for years, waiting for the right conditions to reactivate. And once humans arrive in greater numbers, bringing their own microbiomes with them, the complexity of the situation only increases. The line between engineered and accidental contamination blurs, and the long-term effects of human microbe interactions on Mars become an open-ended question with no clear answer. The risks are not an argument against introducing microbial life, but they are a reminder of what is at stake. Mars, for all its potential, is not a second Earth. It is a world shaped by an entirely different history, an environment where even the smallest intervention can have consequences that ripple outward in ways no one can fully predict. And unlike the gradual shifts that took place on Earth over billions of years, where nature itself balanced and corrected its course through extinction and adaptation, Mars has no such safety net. Once change begins, it is irreversible. A decision made today will shape the planet for centuries, perhaps millennia. It is the weight of playing nature on a scale beyond anything humanity has ever attempted before, a responsibility not just to the future of Mars, but to the unknown possibilities it still holds. 12. Establishing a plant ecosystem. If microbial life is the first step in shaping Mars into something more than a lifeless world, then plants are the first sign that the transformation is taking hold, the visible, undeniable proof that biology is no longer a fragile experiment, but an active force. Yet life does not take root easily in a place where nothing has ever grown before. Even with bacteria breaking down toxic compounds in the regolith, even with fungal networks weaving the first threads of a living soil, even with the slow enrichment of organic material, the challenge of establishing a plant ecosystem on Mars is unlike anything ever attempted. It is not simply a matter of placing seeds in the ground and waiting for them to sprout. Every factor that makes life possible on Earth — temperature, atmospheric composition, radiation shielding, water availability, the very structure of the soil itself — must either be replicated artificially or overcome through biological resilience. And the question remains, even under the best conditions, which plants could survive? The answer is not straightforward, because survival depends not just on the plant's individual tolerance, but on how well it fits into a system. No single species, no matter how hardy, can form an ecosystem alone. The plants chosen for Mars must work together, supporting and reinforcing one another, cycling nutrients, stabilizing the soil, forming the foundation of a self-sustaining environment rather than a temporary greenhouse experiment. The first candidates are not the towering trees of Earth's forests or the delicate flowers of temperate meadows, but the toughest, most adaptable pioneers. Plants that have evolved to thrive in extreme conditions, to endure drought, to withstand radiation, to grow in nutrient-poor soils that offer little more than a harsh struggle for survival. Hardy, fast-growing plants like certain varieties of legumes could play a key role, not because they provide immediate sustenance, but because they fix nitrogen, enriching the developing soil in a way that benefits everything that follows. Earth's deserts provide another source of inspiration. Species like salt-tolerant succulents and deep-rooted shrubs, accustomed to surviving with minimal water, might offer clues to what could persist in controlled Martian environments. Lichens, which have already survived exposure to space and experiments, could be an even earlier form of plant-like colonization, capable of withstanding extreme radiation and growing directly on rock surfaces, slowly breaking them down into more soil-like material over time. Algae, though not technically plants, could become one of the first photosynthetic organisms introduced in large quantities, producing oxygen, absorbing carbon dioxide, and forming the basis of a more complex biological network. But none of these plants, no matter how well adapted, could survive unprotected on the Martian surface. The cold alone is enough to kill nearly any known species, with nighttime temperatures plunging to levels that freeze water instantly. Radiation, unfiltered by a thick atmosphere or protective magnetic field, would damage DNA, leading to mutations or outright destruction of delicate cellular structures. And the low atmospheric pressure ensures that any liquid water at the surface would either boil away or freeze into useless, inaccessible ice. For plants to survive, they must be given an environment that shields them from these extremes, at least in the early stages. This means controlled habitats, pressurized greenhouses, subterranean growing chambers, or artificially heated and insulated domes where conditions can be regulated to mimic the warm, stable climates that plants have evolved to expect. Even within these protective spaces, water remains one of the most significant challenges. Mars has water, locked in ice and possibly hidden beneath the surface, but accessing it in a way that supports plant growth is no simple task. Every drop must be carefully managed, recycled, and distributed efficiently, a delicate balance between providing enough moisture for survival and ensuring that no waste occurs in an environment where resources are finite. Hydroponic or aeroponic systems, which allow plants to grow without traditional soil by suspending their roots in nutrient-rich solutions or fine mist, could be one way to bypass the challenges of Martian regolith altogether, at least in the early phases. These systems would allow for precise control over nutrient intake and hydration, eliminating the uncertainties of soil development and providing a stable foundation for food production long before open-air planting on Mars is even a possibility. But the ultimate goal is not just to grow plants in isolated pockets of artificial stability. It is to build an ecosystem, a cycle of life that can sustain itself with minimal human intervention, a system where plants do not simply survive but flourish, adapting to their new world as life has always done. The first step is selecting species that can endure the transition, that can take root in a foreign world and slowly shape it into something familiar. And yet, for all the complexity, for all the obstacles that stand in the way, there is something deeply human in the act of planting the first seed. It is not just an experiment, not just a survival strategy. It is a statement of intent, a declaration that Mars is no longer a place where life is impossible, but a place where, if given the chance, it can begin to grow. But even with the toughest plants carefully chosen for their resilience, even with controlled habitats shielding them from the worst of Mars hostility, survival is still a matter of compromise. Adapting the environment just enough to make life possible while accepting that Earth-based organisms were never designed for this world. The reality is that plants, microbes, even humans themselves are the product of billions of years of evolution shaped by Earth's gravity, atmosphere, and chemistry. On Mars, where everything from radiation levels to soil composition presents an existential threat, adaptation must happen on a much shorter timescale. It is not enough to select species that already possess useful traits. To truly thrive, life may need to be re-engineered at its most fundamental level. Genetic modifications offer the possibility of pushing evolution forward, of giving Earth-based life forms a fighting chance on a planet that does not welcome them. For plants, this could mean altering their photosynthetic pathways to make better use of the limited light that reaches the Martian surface, modifying their root systems to extract nutrients from regolith that was never meant to support life, or engineering resistance to radiation so that their cells do not degrade under the unfiltered glare of the sun. Scientists might introduce genes from extremophiles, organisms on Earth that survive in conditions once thought impossible, into crops or pioneer plants, giving them the ability to tolerate freezing temperatures, endure prolonged drought, or synthesize protective compounds that shield against the relentless assault of cosmic rays. Microbes, too, could be altered, their genomes tweaked to make them more efficient at breaking down toxic compounds in the soil, to enhance their ability to fix nitrogen, or even to produce biopolymers that strengthen soil structure, preventing erosion and making future planting more stable. A bacterium designed to survive in Mars' low-pressure atmosphere could provide oxygen directly, not just for plants but for human colonists, forming an unseen but essential layer of support. Even fungi, which might play a key role in creating a biologically active soil layer, could be modified to decompose regolith into something closer to Earth's fertile ground, secreting enzymes that extract usable minerals while suppressing harmful chemical reactions that could disrupt fragile ecosystems. The question of genetic modification extends beyond plants and microbes. If humans are to live on Mars for extended periods, if they are to become something more than visitors in carefully controlled domes and pressurized suits, then their own biology may need to change. Even now, long-term space travel alters the human body in ways that are not yet fully understood. Bone density weakens, muscle mass deteriorates, immune systems behave unpredictably, and exposure to cosmic radiation increases the risk of cancer, genetic damage, and neurological effects that could take years to manifest. On Mars, where gravity is only a third of what the human body evolved to expect, where radiation exposure is constant, where even the air outside is unbreathable, the limits of human endurance will be tested in ways that no one has ever experienced before. Genetic modifications, if they are ever considered for humans, could offer solutions. Enhanced DNA repair mechanisms, borrowed from organisms that have evolved to withstand extreme radiation, might reduce the risk of long-term genetic damage. Alterations in bone metabolism could help prevent the loss of density that occurs in low gravity, allowing future generations born on Mars to develop stronger skeletal structures adapted to their environment. Even something as basic as oxygen efficiency, modifying red blood cells or respiratory enzymes to function better in lower oxygen conditions, could make survival easier, reducing reliance on artificial life support. These ideas remain theoretical, and the ethical questions surrounding human genetic modification are far from resolved. But they represent a potential future where adaptation is not just a matter of external technology, but of biological change at the most fundamental level. Yet for all its possibilities, genetic modification is not without risks. The very process of altering DNA can have unintended consequences, mutations that manifest in unpredictable ways, traits that behave differently in an alien environment than they would on Earth. A plant engineered for radiation resistance might become less efficient at photosynthesis, sacrificing growth for survival. A bacterium designed to terraform Martian soil might become too aggressive, disrupting delicate biochemical cycles instead of stabilizing them. Even in humans, the long-term effects of genetic alterations are unknown. What seems like an advantage in one generation might lead to unforeseen complications in the next. Evolution, when left to its natural course, operates over immense timescales, allowing countless variations to be tested, failures discarded, successful adaptations refined through the pressures of survival. Genetic engineering bypasses this slow, careful process, accelerating change in ways that are difficult to predict and impossible to undo. But despite the risks, despite the unknowns, the need for adaptation remains. Mars will not change itself to accommodate life from Earth. Life must change to meet the challenge of Mars. Whether through selective breeding, genetic engineering, or even more advanced forms of biological modification that have yet to be developed, the survival of plants, microbes, and eventually humans on an alien world will depend on finding ways to bridge the gap between what life has always been and what it must become. It is not just about making Mars habitable. It is about redefining what life itself can endure, about pushing the boundaries of biology to places it has never gone before. But even with plants genetically modified for resilience, even with microbial networks preparing the soil and atmospheric conditions slowly shifting towards something more hospitable, the question remains, where should life take root? The controlled environments of pressurized greenhouses offer stability, protection from the harsh Martian elements, and precise regulation of factors like temperature, humidity, and nutrient availability. Yet in the long run, an entirely closed system is not the end goal. For Mars to support a self-sustaining biosphere, plants must eventually grow beyond the confines of artificial structures, exposed to an environment that, even with intervention, will never be fully like Earth's. The transition between these two approaches, closed and open environment plant growth, is one of the most significant challenges in making Mars truly habitable. A closed environment ensures survival in a way that open planting cannot. Inside a greenhouse, plants are shielded from the extremes of Martian temperature, where daytime warmth gives way to brutal, freezing nights that no Earth-native species could withstand. They are protected from radiation, which otherwise seeps through the thin atmosphere, bombarding the surface with levels of exposure that would cripple biological processes over time. The pressure inside remains Earth-like, preventing the desiccation and structural damage that unprotected plants would suffer in the near vacuum of Mars' surface. Water is controlled, cycled, and reused efficiently, reducing loss and ensuring that every drop serves a purpose. Carbon dioxide levels can be adjusted, optimizing photosynthesis, allowing plants to grow faster and stronger than they ever could in the thin Martian air. In essence, these closed systems create small, artificial Earths, pockets of stability in a world that was never meant to sustain life. Yet for all their advantages, closed environments come with limitations. They are dependent on constant human or automated intervention, requiring power, maintenance, and resources that must either be transported from Earth or extracted and processed on Mars. If a system fails, if a seal breaks, if temperature controls malfunction, if a fungal infection spreads unchecked within the confined space, entire crops could be lost, and with them, a critical source of food, oxygen, and morale. Greenhouses must expand as populations grow, demanding new materials, new infrastructure, new solutions to scale production in a way that does not become an unsustainable burden. More importantly, a closed system is not an ecosystem, it is an engineered space, a carefully managed environment that, while functional, does not mirror the self-sustaining cycles of nature. The alternative is to move beyond controlled habitats to cultivate plants directly in the Martian landscape, using a combination of genetic modification, environmental engineering, and biological adaptation to create conditions where plants can survive in the open. This is not a process that can happen overnight. The Martian atmosphere is still too thin, too dry, too unfiltered to allow for unprotected growth. But if soil bacteria continue to break down toxic compounds, if microbes steadily enrich the regolith with organic material, if water ice can be accessed and distributed, if radiation-resistant plants can be developed, then the first steps toward an open environment biosphere may become possible. Early experiments might begin with hardier species, ones that do not require a fully Earth-like atmosphere but can persist under reduced pressure, higher carbon dioxide levels, and limited water availability. Gradual transformations. Introducing artificial windbreaks to prevent soil erosion, using chemically treated or biologically active layers of regolith to retain moisture, developing protective microbial films to shield plants from excessive radiation, could make survival increasingly viable. Over time, with continuous intervention and genetic refinement, open planting zones could expand, forming the basis for something far beyond isolated greenhouses, a true Martian ecosystem. The challenge is not just about survival but about autonomy. The more life can function without direct human input, the closer Mars comes to being a place where people are not just visitors but settlers. Where food production is not a precarious engineering feat but a natural process woven into the planet's evolving biosphere. The transition from closed to open growth is the transition from an artificial habitat to something more profound. A world where plants do not merely exist in controlled chambers but thrive under an alien sun, changing the landscape itself in ways that, for now, remain only a vision of what the future might hold. 13. Creating sustainable ecosystems. Creating sustainable ecosystems is one of humanity's most profound and ambitious endeavors, a challenge that intertwines scientific understanding with the deeply personal and emotional relationship humans have with the natural world. The idea of building a functional ecology, often referred to as the Biosphere Challenge, is rooted in our desire to not only mitigate the damage we've inflicted on the planet, but also to create self-sustaining environments that can support life, both for ourselves and for future generations. This concept is not purely theoretical. It has been attempted in controlled environments like Biosphere 2 in Arizona, where scientists sought to replicate Earth's complex ecological systems within a sealed structure. Yet, despite the meticulous planning and advanced technology, the experiment revealed just how intricate and delicate the balance of life truly is. The oxygen levels plummeted, certain species thrived while others withered, and the human participants faced unexpected psychological and physical challenges. These outcomes underscored a humbling reality. We are not separate from nature, but fundamentally intertwined with it in ways we barely understand. At the heart of this pursuit is a question that is both scientific and philosophical. Can we, as a species, step into the role of nature's architect without disrupting the very systems we aim to emulate? The complexity of an ecosystem lies not only in the obvious relationships between plants, animals, and microbes, but also in the invisible chemical cycles, the exchange of energy, and the subtle interdependencies that have evolved over billions of years. Attempting to replicate this in an artificial setting forces us to confront the limitations of human knowledge and the unintended consequences of our actions. Yet, there's something profoundly human about this struggle. It reflects our need to control, to create, and to survive. In a world facing climate change, deforestation, and biodiversity loss, building sustainable ecosystems is no longer just an experiment. It's a necessity for our own survival. What makes this endeavor even more compelling is the emotional and psychological dimension. People who dedicate their lives to ecological restoration or the design of self-sustaining habitats often speak of a profound sense of connection to the living world, a feeling of responsibility toward the fragile web of life that supports us. Indigenous communities, who have lived in harmony with their environments for millennia, understand this balance intuitively, while scientists and engineers approach it through data and observation. Yet, both are driven by the same underlying instinct: to protect and nurture the systems that sustain life. In the quest to create functional ecologies, we are not merely solving a scientific puzzle. We are confronting the consequences of centuries of exploitation and industrialization. We are grappling with our own vulnerability as a species that relies on clean air, fertile soil, and stable climates. And perhaps most importantly, we are being forced to reimagine our relationship with nature, not as masters or conquerors, but as humble participants in an ancient and intricate dance. The success of such efforts will not be measured solely by the survival of plants and animals within controlled environments, but by whether we, as humans, can change our mindset and recognize that the health of the planet is inseparable from our own well-being. This pursuit of creating sustainable ecosystems inevitably leads us to confront the delicate balance of Earth's atmospheric cycles. The intricate dance between carbon dioxide, oxygen, and nitrogen that makes life possible. It's easy to think of these elements as abstract chemical processes happening in the background of existence, but in reality, they are intimately tied to human activity and the way we have shaped the planet. When we burn fossil fuels, clear forests, and industrialize agriculture, we're not simply releasing carbon or disrupting nitrogen cycles. We're altering the very rhythm of life's breathing. The balance between CO2 and O2 is ancient and fragile, forged over billions of years through photosynthesis and respiration, a perfect exchange between plants and animals. Yet, human intervention has accelerated carbon emissions to such an extent that the natural world can no longer absorb it fast enough. The oceans, which act as massive carbon sinks, are acidifying, while forests that once pulled carbon from the air are being destroyed at an alarming rate. This imbalance is not just about rising temperatures or melting ice caps. It directly affects the air we breathe and the stability of the ecosystems that feed us. But perhaps the nitrogen cycle is even more revealing of humanity's impact. Nitrogen, essential for plant growth, once cycled naturally through the soil and atmosphere with the help of bacteria and decaying organic matter. With the invention of synthetic fertilizers, we broke that natural cycle, flooding the earth with nitrogen compounds that now run off into rivers and oceans, creating massive dead zones where life cannot survive. What's haunting about this is that it's not the result of greed or malice. It's driven by the human need to grow food, to feed billions of people. Yet, in our effort to control nature, we've disrupted a system that once functioned in perfect equilibrium. What makes this struggle deeply human is that the consequences of these imbalances are not felt equally. Communities living in industrial regions suffer from air pollution and respiratory diseases due to excessive CO2 emissions. Farmers in regions affected by soil degradation and nitrogen runoff watch their land become barren. Indigenous communities, who have lived in harmony with these cycles for generations, are witnessing their ecosystems collapse. And yet, the most unsettling aspect of all is that the air we breathe, the nutrients that sustain our crops, and the stability of our climate are all connected by invisible chemical processes that we barely understand. Processes we are now actively destabilizing. There's something profoundly humbling about realizing that the very act of breathing is part of this ancient cycle. That with every exhale, we release carbon dioxide that plants transform back into oxygen. And yet, through our actions, we've thrown this balance off course. The challenge we face now is not merely scientific or technological, it's existential. Can we learn to work with these cycles instead of against them? Can we restore carbon to the soil, protect the forests that produce oxygen, and rebuild natural nitrogen pathways through regenerative agriculture? These are not abstract questions for scientists and policymakers. They are questions that touch the lives of every person on this planet, whether we feel it yet or not. Because in the end, the atmosphere is not something separate from us. It is part of us, woven into every breath we take, every crop we harvest, and every drop of water that falls from the sky. And perhaps, in understanding that, we'll find a way to restore balance. Not out of fear, but out of the simple, human instinct to protect the world that keeps us alive. Understanding the delicate balance of Earth's atmospheric cycles inevitably leads to a more unsettling question. What happens when life is removed from those cycles entirely? This question becomes even more profound when we consider the possibility of animals thriving on Mars, a world stripped of the intricate web of interactions that sustain life here on Earth. The idea of animals living on Mars feels almost alien to us, not because it's scientifically impossible, but because life, in all its complexity, is so deeply rooted in Earth's biology. The air we breathe, the microbial soil beneath our feet, the warmth of the sun filtered through a protective atmosphere. Mars offers none of that. Its thin atmosphere is composed mostly of carbon dioxide, with barely a whisper of oxygen. The surface is bathed in radiation, the soil is laced with toxic perchlorates, and temperatures can plummet to levels colder than Antarctica's most brutal nights. But what makes this question deeply human is the fact that we're already trying. In our relentless curiosity and need to push beyond the limits of this planet, we've begun to design ecosystems that could sustain life in the most inhospitable environments. Scientists have experimented with extremophiles, microorganisms that can survive in extreme conditions, to understand how life might adapt to Martian soil. There are ongoing studies on genetically modifying plants to withstand lower atmospheric pressure and experiments on algae that could produce oxygen from CO2. But animals? That's a different challenge entirely. For an animal to survive on Mars, it would need more than just food and shelter. It would need an atmosphere that can sustain cellular respiration, a stable temperature range, and protection from cosmic radiation. Even the simple act of breathing becomes a monumental struggle in an environment where oxygen is nearly absent. Yet, life has a way of finding cracks in the impossible. On Earth, we've seen creatures thrive in deep-sea hydrothermal vents, where the pressure would crush most organisms, and in the Antarctic deserts, where temperatures never rise above freezing. Could certain species, perhaps insects or small reptiles, adapt to a Martian habitat if we provided them with an enclosed, oxygen-rich environment? Would their biology slowly shift over generations, evolving to require less oxygen or developing resistance to radiation? But perhaps the more unsettling question isn't whether animals could physically survive on Mars, but whether they would truly live. Animals, especially mammals, are deeply connected to their surroundings. The scent of the air, the texture of the earth, the rhythmic cycles of daylight and darkness. A fox in a Martian biodome, cut off from the sound of rustling leaves or the scent of prey in the wind, would be stripped of the very instincts that define it as an animal. Even if we recreated a miniature Earth within a Martian habitat, filled with grass, soil, and water, the absence of a living sky and the hum of a functioning ecosystem would create a world that feels hollow and sterile. And yet, This is where the human element becomes unavoidable. We are driven not just by logic, but by an almost primal need to push life outward, to plant seeds in barren soil and see what grows. Maybe the first animals to walk on Mars won't be there for survival, but as companions to human settlers who refuse to live without the sound of birdsong or the quiet companionship of a cat. And perhaps, over generations, life will begin to carve out new rhythms in the Martian dust, just as it once did on Earth billions of years ago. Not because the conditions are perfect, but because life, in its stubborn, fragile beauty, has always found a way. 14. Human habitats and settlement designs. If the idea of animals adapting to the barren landscapes of Mars feels distant and improbable, the question of how humans themselves might build lasting settlements there feels even more urgent. Because before we can dream of forests on Martian soil or creatures evolving to survive the thin atmosphere, we must first ask, where will we live? The debate between building underground colonies versus surface habitats is not just a technical question of engineering, but one that reflects something deeply human. Our instinct to seek shelter, not only from the elements, but from the vast and indifferent emptiness that lies beyond. On Earth, the sky has always been a symbol of openness, freedom, and possibility. But on Mars, that same sky would be a deadly expanse of radiation and thin, unbreathable air. The surface, while visually stunning with its rust-colored plains and towering canyons, is bathed in cosmic rays and solar radiation due to the planet's lack of a protective magnetic field. Living on the surface would mean relying on thick, shielded domes or heavily armored habitats, where every crack or malfunction could mean death. Yet, despite these dangers, there is something undeniably human about wanting to stand beneath an alien sky, to watch the pale Martian sun rise over the horizon and feel, in some strange way, part of this distant world. The alternative, building underground colonies, is far more practical. Beneath the surface, layers of Martian soil, known as regolith, could act as a natural shield against radiation. Tunneling into ancient lava tubes, remnants of Mars' volcanic past, would provide ready-made shelters that could be sealed and pressurized. The temperature would be more stable, and the thick walls would offer protection from micrometeorite impacts and dust storms that can rage for months. Yet, for all its practicality, living underground feels inherently isolating. Humans evolved under open skies, surrounded by light, movement, and the subtle sounds of wind and water. To spend months, even years, in dimly lit tunnels carved from rock would test not only the body but the mind. What makes this choice even more complex is that neither option is purely about survival. It's about how humans experience a place, how we adapt not just physically, but emotionally and psychologically. An underground colony might provide safety, but would it satisfy the human need for beauty and connection to the world beyond? A surface habitat might offer breathtaking views of the Martian landscape, but could we endure the constant threat of exposure and death just beyond the walls? And in the end, perhaps the true answer lies not in choosing one or the other, but in blending both. Building underground for safety and stability, while creating small, pressurized surface spaces where people can step out and experience the alien world they've come so far to reach. Because the truth is, humans are not machines that simply need air and water to survive. We are creatures of memory and emotion, shaped by the places we inhabit. And if we are to call Mars home, even in the smallest sense, we will have to build more than shelter. We will need spaces that remind us of Earth, places where light and sound and the presence of others make the emptiness feel less vast. And maybe, with time, the tunnels beneath the Martian surface will become not prisons, but sanctuaries. Places where life quietly takes root in the heart of a world that has been dead for billions of years. If building underground colonies offers protection and stability on Mars, while surface habitats satisfy the human need to experience the landscape, the concept of artificial domes and pressurized cities seems to exist somewhere between these extremes. It's an idea born not just from science fiction, but from a very human desire to reclaim control over an environment that was never meant to support life. The thought of vast, transparent domes rising from the Martian surface, filled with air, water, and vegetation, feels almost utopian. A fragile oasis surrounded by endless dust and rock. Yet, beneath that vision lies an immense engineering challenge and an even deeper psychological one. How do you recreate an entire world within a structure that must constantly fight against the vacuum of space? The atmosphere within these domes would need to be carefully regulated, balancing oxygen and carbon dioxide levels to sustain both plants and humans. Water would have to be cycled through closed-loop systems, and artificial lighting would need to mimic the natural rhythms of daylight and night to prevent the slow unraveling of the human mind that comes with living in constant artificial brightness. The structure itself would need to withstand not only internal pressure but the constant bombardment of micrometeorites and the corrosive nature of Martian dust, which clings to surfaces and wears down materials over time. And yet, despite these challenges, the idea of living within a pressurized city holds a strange allure. It offers something that underground colonies cannot: space, openness, and the illusion of freedom. Within the dome, people could walk beneath towering greenhouses, breathe air filled with the scent of plants and soil, and see the sky, even if that sky is distorted through layers of reinforced glass. But what makes this concept truly human is the fact that it's not just about survival. It's about creating beauty and comfort in a place that would otherwise be cold and lifeless. Imagine standing on the edge of a Martian dome at sunset, watching the pale, dusty horizon stretch out in the distance while inside, small gardens bloom and streams of recycled water flow through artificial canals. It's not Earth, and it never will be, but it's enough to remind us of what we've lost, and perhaps what we still carry with us. The real challenge of pressurized cities is not just technical, it's emotional. How do you build a world that feels alive when everything outside is silent and dead? How do you give people a sense of belonging in a place where they are, by definition, outsiders? And perhaps, more hauntingly, what happens when future generations are born beneath these domes, never having walked on Earth's soil or breathed its air? Will they feel trapped within these glass walls? Or will they look out at the red world beyond and feel a strange sense of ownership? Not as visitors, but as pioneers of a world that humanity has slowly begun to tame? In the end, artificial domes are not just shelters. They are symbols of defiance against a world that was never meant to support us. But they are also fragile, vulnerable to the smallest cracks, the slightest shifts in atmospheric pressure. And maybe that's what makes them feel so human. Because they, like us, are temporary. Small, imperfect structures fighting against an ancient and indifferent planet, trying to carve out a place where life can exist in a world that has known nothing but silence for billions of years. As the vision of artificial domes and pressurized cities takes shape, the question shifts from what kind of habitats we can build on Mars to what we will build them from. Transporting traditional building materials from Earth would be not only expensive, but logistically impossible on a large scale. This is where Martian regolith, the fine, dusty material that blankets the planet's surface, becomes more than just an obstacle to survival. It becomes a resource. The very soil that once seemed hostile and lifeless can be transformed into the foundation of future settlements through advanced 3D printing technology. What makes this idea so compelling is that it forces us to work with the planet rather than against it. Instead of relying on fragile, Earth-made structures, we begin to adapt to Mars itself, using what the planet already offers to create something entirely new. Martian regolith is rich in silicates and iron oxides, giving it a strength and durability that, when processed correctly, can rival concrete. By using 3D printing techniques, scientists have found ways to heat and compress this material into solid blocks, layer by layer, creating walls, shelters, and even entire structures. The beauty of this process lies in its simplicity. A robotic printer, controlled remotely or by AI, could slowly build habitats while human crews remain safely in orbit or within protected environments. With enough time, these machines could construct radiation-shielded shelters, tunnels, and even the foundations for future cities, all from the very dust that has covered the planet for billions of years. But what makes this idea truly human is the way it forces us to confront our own limitations. On Earth, we shape our environment to fit our needs. We cut down forests, dam rivers, and pour concrete over soil. On Mars, that approach would be impossible. We are fragile there, vulnerable to the thin atmosphere and the cold, and the planet itself is ancient and indifferent to our survival. So instead, we are learning to adapt, to mold the planet's raw materials into something protective and enduring. There's something strangely poetic about that, about turning dust, the same dust that whips through Martian storms and buries ancient craters into the walls that will shelter the first humans to call this world home. Yet, this process is not without its challenges. Martian regolith is toxic, laced with perchlorates that would be deadly if inhaled or absorbed through the skin. The fine particles can damage machinery and wear down surfaces over time. And the 3D printing process itself is slow and energy-intensive, requiring solar power or nuclear reactors to generate the heat needed to fuse the material. But this struggle is what makes it meaningful, because beneath the technical complexity is something deeply human, the need to create something lasting in a place where nothing has ever lived. The first walls built from Martian regolith will not be monuments to human triumph, but fragile, imperfect structures. Shelters against the vast and empty sky, built from the very dust that once seemed to symbolize the impossibility of life. And maybe, in that act of creation, we'll begin to feel something strange and unfamiliar. Not like visitors, not like explorers, but like settlers, slowly turning a dead world into something that can hold life. 15. Terraforming Mars, energy requirements. Terraforming Mars sounds like one of those grand sci-fi dreams where humanity waves a technological magic wand and turns a barren, freezing wasteland into a second Earth. But the brutal reality is that Mars is an absolute energy sink, a planet so hostile that just keeping a single outpost running is a logistical nightmare, let alone transforming an entire world. At the heart of this uphill battle is the question of energy, because without an absurd amount of it, nothing else even gets off the ground. You need energy to power atmospheric processors, to melt polar ice caps, to run massive factories that would have to churn out greenhouse gases at a rate that makes our worst industrial pollution look like child's play. Every step of making Mars even remotely habitable depends on an energy input so ridiculous that it's almost insulting to think about. And if that energy isn't coming from fossil fuels, which obviously don't exist there, then solar power seems like the next best thing, right? Except, well, Mars doesn't exactly roll out the red carpet for solar energy. First off, Mars is nearly 1.5 times farther from the Sun than Earth is, meaning the solar power available on the surface is already significantly weaker just due to sheer distance. The Sun appears smaller, the intensity drops, and right from the start, you're working with roughly half the solar energy that Earth gets. That's like starting a marathon with one leg in a cast. And it only gets worse because Mars is notorious for its dusty atmosphere. Unlike Earth, where clouds can be annoying but at least let some sunlight through, Mars has these colossal, months-long dust storms that can blanket the entire planet, turning everything into a rust-colored wasteland of darkness. Even when there isn't a planet-wide storm, the Martian air is always filled with fine dust that constantly reduces the efficiency of solar panels, scattering and absorbing sunlight like a cosmic-level prank designed to make sure your energy plans never quite work out the way you hoped. Then there's the temperature problem. Mars is cold, really cold, a place where nighttime temperatures can drop to minus 100 degrees Celsius, and that kind of extreme cold plays havoc with solar panels. Batteries don't hold charge as well in freezing conditions, materials become brittle, and efficiency drops just from sheer thermal stress. You could try to store solar energy during the day and use it at night, but Mars doesn't have the luxury of warm, consistent Earth-like nights. It has deep, bone-chilling freezes that demand even more energy just to keep systems from locking up entirely. And if you want to power something truly ambitious, say, a planetary-scale operation to release CO2 from the soil or create thick clouds of artificial greenhouse gases, you need an energy infrastructure that dwarfs anything we've ever built. Solar panels, even on the best days, just won't cut it for that level of demand. It's not that solar energy on Mars is useless. It's just frustratingly inefficient for anything beyond small-scale operations. Rovers and small research stations can make do, but if you're talking about reshaping an entire planet's climate, you're going to need power levels that make solar seem like a joke. Nuclear energy is the more realistic alternative, but even that has its own logistical problems, from mining fissile material to dealing with extreme radiation risks in an already deadly environment. The simple truth is that Mars doesn't care about our grand plans. It doesn't make things easy. It doesn't hand out free energy the way Earth does. If we want to terraform it, we're going to have to fight for every last watt of power And even then, we might just be fighting a losing battle against a planet that was never meant to be ours. And this is exactly where nuclear power forces its way into the conversation, not because it's perfect, but because every other option looks so hilariously inadequate that it becomes the only real contender left standing. If solar power on Mars is like trying to fill a swimming pool with a leaky bucket, nuclear is the equivalent of turning on a fire hose. An imperfect, dangerous, highly technical solution, but one that actually delivers the raw power needed to make anything resembling large-scale colonization, let alone terraforming, remotely feasible. Unlike solar, nuclear energy doesn't care if the sky is choked with dust, doesn't drop to a pathetic trickle when the sun sets, and doesn't throw a tantrum every time the Martian atmosphere decides to remind us that it's essentially an enormous, ever-present filter designed to keep useful energy away from the surface. Nuclear power just does what it does: generate an absurd amount of energy, reliably and relentlessly, for years on end. The idea is straightforward enough. Haul nuclear reactors to Mars, set them up in locations that won't cause catastrophic damage if something goes wrong, and let them churn out energy like self-contained mini-suns. But, as always, nothing about Mars is ever that easy. First, there's the sheer logistical nightmare of getting them there. A full-scale nuclear reactor is not something you casually toss into a rocket and launch without weeks of people nervously sweating over the fact that they're strapping a radiation-emitting metal behemoth to an explosion-powered tube aimed at the sky. Even if you get past that, there's the challenge of making reactors that are lightweight enough to be transported efficiently, but still powerful enough to be worth the effort. Traditional Earth-based nuclear reactors rely on large cooling systems that are utterly impractical on Mars, where liquid water doesn't just sit around waiting to be used as a heat sink. Instead, any reactor built for Mars has to be designed to work in a brutally thin, nearly non-existent atmosphere, where heat dissipation is a completely different game and engineering solutions have to be borderline genius just to stop the whole thing from overheating or shutting down. But assuming you solve all that, assuming you somehow land a set of compact, high-output fission reactors on the surface, get them running, and start generating power, then suddenly, for the first time, Mars becomes something more than just a lifeless desert. Nuclear power could provide the massive energy output needed to fuel oxygen generators, keep habitats warm without relying on inefficient solar batteries, and even kickstart the long-term, painstaking process of transforming Mars's atmosphere. Whether by artificially boosting CO2 levels to trap more heat, or eventually splitting water to build up reserves of breathable oxygen and hydrogen fuel. It's not a quick fix, not by a long shot, but it's the closest thing to a power source that actually scales up to the ridiculous levels needed to make Mars anything more than a cold, red tomb for overly ambitious spacefarers. Of course, nuclear comes with its own set of horrifying risks, because setting up high radiation power sources on a planet with no magnetic field and no natural protection from cosmic rays means that every single containment failure, every miscalculation, every small leak becomes an even bigger problem than it would be on Earth. Radiation shielding is already a huge issue for astronauts, and sticking nuclear reactors into the mix just adds another layer of potential disaster that needs to be controlled with extreme precision. But in the end, it's a trade-off. Either deal with the challenges of nuclear power, or accept the grim reality that every other energy source is simply too weak, too inconsistent, or too impractical to power anything beyond tiny, fragile outposts clinging to survival. Mars doesn't offer second chances. If we want to make it livable, or at the very least survivable, we're going to have to take the risks, because the alternative is just sitting around waiting for a solar panel to recharge while the cold slowly creeps in. But if nuclear power sounds like a high-stakes gamble that involves launching radioactive material across millions of kilometers of space and hoping nothing goes horribly wrong, then geothermal energy seems, at first glance, like the kind of low-maintenance alternative that could save everyone a lot of trouble. After all, if Earth can tap into the natural heat trapped beneath its surface to generate power, why not Mars? Dig deep enough, set up a system that can extract and convert that energy into something useful, and maybe, just maybe, there's a way to power a colony without relying on reactors or struggling with the miserable inefficiencies of solar. The problem, though, is that Mars isn't Earth, and the moment you start looking at the details, the whole idea starts to unravel like a bad sweater. The biggest issue is that geothermal energy depends entirely on how much heat is actually left inside a planet. And Mars, for all its dramatic landscapes and ancient volcanoes, is geologically dead in the worst possible way. On Earth, geothermal power works because the planet's core is still a raging inferno of molten iron, constantly churning and producing enough internal heat to drive volcanic activity, tectonic shifts, and all the lovely geothermal hotspots we happily exploit for energy. Mars, on the other hand, lost most of that internal heat billions of years ago. Its core is either entirely solid or only partially liquid, but either way, it's not active enough to generate anything close to the kind of deep heat reservoirs that make geothermal energy viable on Earth. Without a molten core feeding the system, there's no large-scale convection pushing heat toward the surface, no dynamic movement of the crust to bring up fresh energy sources, just a frozen, stagnant interior that holds on to its remaining heat like a dying ember buried under layers of insulating rock. That's not to say there's zero heat left inside Mars. Digging deep enough would still reveal some thermal energy, just nowhere near the levels needed to support anything ambitious. There's some hope in areas with volcanic history. Olympus Mons, for example, or the Tharsis region, where past activity suggests there might still be some lingering warmth trapped underground. But even if you find a location where subsurface temperatures are marginally higher, the question then becomes whether it's even worth the effort. Extracting geothermal energy requires extensive drilling operations, something that is already a massively complex undertaking on Earth, let alone on a planet where you have to haul every piece of equipment across interplanetary space. And if you somehow manage to drill deep enough to tap into what little heat remains, the returns are questionable at best. Unlike nuclear, which can provide a concentrated, controllable energy output, geothermal on Mars would be weak, inconsistent, and probably not worth the enormous effort it would take to set up and maintain. In the end, geothermal energy on Mars feels like one of those ideas that works beautifully on paper but collapses under the weight of reality. It's a tempting thought. Just use the planet's own internal warmth and skip the logistical nightmare of transporting fuel or relying on unreliable solar power. But Mars simply doesn't have enough geological activity left to make it practical. Maybe, in some distant future, with advanced drilling tech and a better understanding of the planet's internal structure, there might be ways to squeeze out a small amount of energy from the depths. But for now, trying to power a Mars colony with geothermal energy would be like trying to charge a spaceship with the warmth of a campfire. It's just not going to cut it. 16. The role of AI and robotics in terraforming. If geothermal energy turns out to be just another dead-end idea that sounds clever until you actually try to make it work, then the only real way forward is to stop thinking in terms of what humans can physically handle and start designing systems that don't rely on fragile, easily exhausted people in the first place. Terraforming Mars, or even just setting up the kind of large-scale infrastructure needed for a functional colony, isn't something that can be done with a handful of astronauts in bulky suits manually assembling habitats like a group of space-age construction workers. The sheer scale of what needs to be done, building power grids, mining resources, manufacturing life support systems, processing the atmosphere, and eventually even reshaping parts of the planet itself, is so far beyond human labor that it only makes sense if most of the work is handed off to machines. Not just simple, pre-programmed robots mindlessly repeating tasks, but a fully autonomous, self-sustaining system that can operate indefinitely, adapt to unpredictable conditions, and work without constant human oversight. The moment you introduce AI and robotics into the equation, everything changes. Instead of worrying about whether a small, underpowered human crew can keep up with the demands of survival while also building infrastructure from scratch, you shift the burden to machines that don't get tired, don't need food or oxygen, and don't care if they have to spend years operating in extreme conditions. AI-driven robotic systems could be deployed years, maybe even decades, before the first humans set foot on Mars, working around the clock to prepare the planet in ways that would otherwise be impossible. Fully automated mining rigs could extract raw materials straight from the Martian soil. Robotic assembly lines could construct habitats and power stations without waiting for human hands to put them together. And autonomous drones could constantly map and monitor environmental conditions, adjusting operations in real time based on shifting priorities. The entire point of AI in this scenario isn't just efficiency. It's survival, because if humans had to do all of this manually, the effort would collapse under its own weight long before anything meaningful was accomplished. And it's not just about construction. Terraforming, if it ever happens, will be a process so slow and complex that it might take centuries, and there's no way humans will be managing it step by step the entire time. AI-driven systems would be needed to monitor atmospheric changes, regulate gas production facilities, track temperature shifts, and optimize every aspect of planetary engineering with a level of precision and adaptability that no human-led operation could ever match. Think of it like this. If you wanted to melt the ice caps to release trapped CO2 and thicken the atmosphere, you wouldn't send people with flamethrowers. You'd deploy thousands of automated machines programmed to heat specific regions, monitor the effects, and adjust their approach dynamically. If you wanted to process Martian soil to extract volatiles and useful minerals, you wouldn't have astronauts digging with shovels. You'd have a vast, interconnected network of robotic mining systems refining resources long before the first human ever sets foot on the surface. But of course, none of this comes without its own set of problems. AI and robotics may remove human limitations, but they introduce an entirely new category of failure points. Every piece of hardware sent to Mars has to function in a brutally hostile environment, meaning durability and self-repair become non-negotiable. If a machine breaks down in the middle of an essential task, there's no one around to fix it. And if AI systems aren't designed with enough redundancy and adaptability, a single unexpected failure could cripple an entire operation. Then there's the risk of system malfunctions, communication delays, and worst of all, the possibility that an AI managing critical planetary engineering might make a miscalculation with catastrophic consequences. Terraforming isn't something you get to redo if it goes wrong, and an automated system that controls atmospheric processing, resource extraction, and planetary-scale climate adjustments needs to be programmed with an almost terrifying level of precision to ensure it doesn't end up creating conditions even worse than the ones it was supposed to fix. Still, despite the risks, there's no real alternative. Mars isn't going to be transformed by astronauts in spacesuits painstakingly assembling structures one panel at a time, and it definitely isn't going to be turned into a livable world by short human-led missions that barely last a year. If terraforming is ever going to happen, it will be machines, not people, doing the overwhelming majority of the work. AI-driven robotics won't just make the process more efficient. They'll make it possible in the first place, because without them, the sheer scale of the challenge is simply too much for humans to handle alone. Even if AI-driven robotics manage to build everything needed for a functioning colony and lay the groundwork for large-scale terraforming, that's still only half the battle, because transforming a planet isn't just about brute force construction. It's about control. You can't just dump greenhouse gases into the atmosphere and hope for the best, or melt ice caps without knowing exactly how much water vapor will be released and whether it will actually thicken the atmosphere or just refreeze elsewhere. Every single variable, from temperature shifts to atmospheric composition to the movement of dust and gases, has to be tracked, analyzed, and adjusted in real time. Because the last thing anyone wants is to accidentally push the Martian climate in the wrong direction and make everything even worse. That's where AI becomes more than just a tool. It becomes the brain behind the entire operation, constantly monitoring environmental changes and making adjustments on a scale that no human-led team could ever manage. Climate control on Mars isn't just about heating the planet. It's about precision. AI would have to oversee atmospheric processing plants, making sure they're producing the right balance of gases to gradually create a thicker, more stable atmosphere without triggering chaotic weather patterns that could disrupt everything. It would need to regulate massive solar mirrors or orbital reflectors if they were being used to increase surface temperatures, ensuring they were positioned correctly and adjusting them dynamically based on real-time climate data. And if humans ever manage to introduce water into the environment in a meaningful way, AI would have to predict and manage everything from the formation of clouds to potential precipitation cycles, preventing water from simply freezing into useless surface ice again. The sheer complexity of turning a frozen desert into a livable world is something no human-led operation could possibly keep up with, which means AI wouldn't just be a support system. It would be the only thing making sure the entire process doesn't spiral out of control. The problem is, climate modeling is already incredibly difficult even on Earth, where we have oceans, a magnetic field, and a well-established atmosphere to study. On Mars, everything is unpredictable, from the way CO2 behaves in such a thin atmosphere to the effects of dust storms that can last for months and throw temperature regulation completely off balance. AI-driven monitoring systems would have to account for every possible scenario, from localized temperature spikes that could lead to sudden atmospheric collapses to chemical interactions that might cause unintended consequences. And since it's not like there's a second Mars to experiment on, every decision would have to be based on a combination of simulations, real-time data, and an ever-evolving understanding of how the planet responds to artificial intervention. If the AI managing climate control miscalculates something as simple as the rate at which heat is being trapped by atmospheric gases, it could either slow down the entire terraforming process to a crawl or, worse, create a runaway effect where conditions become even more unstable than before. And then there's the long-term challenge, because even if AI successfully makes Mars slightly more habitable, the process wouldn't stop there. Terraforming is a centuries-long project, and the planet wouldn't just magically stay in the perfect Goldilocks zone once things started improving. AI systems would have to be designed for long-term climate maintenance, constantly balancing atmospheric composition, temperature, and even potential weather patterns to ensure conditions didn't revert back to the unlivable wasteland they started with. In a way, AI wouldn't just be managing climate change. It would be actively playing the role of an artificial planetary ecosystem, doing the job that Earth's natural cycles handle automatically. If humans ever want Mars to be more than just a collection of sealed habitats, they'll need AI to make sure the atmosphere doesn't collapse, the temperature doesn't drop back into lethal territory, and whatever fragile environmental stability they manage to create doesn't get wiped out by one unexpected shift. Without AI keeping everything in check, even the most ambitious terraforming projects would eventually fall apart, because the planet itself has no natural mechanisms to maintain a stable climate on its own. Even if AI is capable of monitoring and adjusting Mars' climate with near-perfect precision, the sheer scale of planetary engineering is so massive that relying on machines built and shipped from Earth isn't just inefficient. It's completely unrealistic. There's no way humans could launch enough equipment to handle every aspect of terraforming. And even if they tried, the cost and logistical nightmare would be beyond anything remotely practical. The only way to actually make this work is to let the machines take over their own production, creating a system where they can mine, refine, manufacture, and expand their own numbers without constant intervention. Self-replicating machines aren't just some futuristic fantasy. They're the only thing that makes large-scale planetary engineering even remotely possible, because without them, every single part of the process would be bottlenecked by human limitations. Instead of launching thousands of specialized robots to Mars, you start with a handful of highly adaptable ones. Machines that can extract raw materials from the Martian crust, process them into usable components, and then manufacture more machines in a cycle that keeps expanding exponentially. A single robotic assembly unit could build another identical unit, then both could build two more, and within a few generations, you'd have an entire automated workforce operating independently. They wouldn't just be mindless factories stamping out copies of themselves, though. AI would ensure they optimize their designs over time, improving efficiency, adapting to changing environmental conditions, and even creating specialized units for different tasks. Some for mining, some for construction, some for atmospheric processing, all working in coordination without needing direct human oversight. With a system like this, entire cities could be built without a single astronaut setting foot on Mars. Vast networks of energy infrastructure could be established automatically, and planetary-scale engineering projects, like thickening the atmosphere or heating the surface, could be executed with a level of efficiency that no human-led operation could ever hope to match. Of course, with self-replication comes the obvious concern. What happens if it gets out of control? If machines are capable of building more of themselves, and their primary objective is to expand and improve, there's always the risk that they keep going long after they should have stopped. In theory, AI should be able to regulate this, setting limits on growth and ensuring machines don't consume every available resource. But even the slightest flaw in that control system could turn Mars into a cautionary tale of runaway automation. Imagine a scenario where self-replicating machines strip mine vast sections of the planet without stopping, digging deeper and deeper in pursuit of materials, completely ignoring the balance needed for stable planetary development. Or worse, what if they start prioritizing efficiency above all else, breaking down human-built structures for raw materials because their programming sees them as unnecessary? The risk of something like this might be small with the right safeguards in place. But when you're dealing with an entire planetary workforce that can operate at a scale and speed beyond human control, even the smallest oversight could have massive consequences. Still, the alternative is worse. Without self-replicating machines, Mars colonization and terraforming would be locked into a painfully slow cycle of waiting for Earth to send more supplies, more machines, more infrastructure, constantly restricted by the limits of interplanetary transport. The whole point of making Mars livable is to create a system that doesn't need constant intervention from Earth, and that's only possible if the machines can maintain and expand themselves. If humans ever want a world that isn't just a series of isolated outposts struggling to survive, they need a way to build, adapt, and grow without relying on endless shipments from home. Self-replicating machines are how you break free from those limitations, creating an autonomous system that can reshape an entire planet, not in years or decades, but in generations. And once that technology exists, once machines can expand their own operations without human intervention, Mars might not be the only world that suddenly looks a lot more habitable. 17. Using asteroids and comets to modify Mars. The idea of using asteroids and comets to modify Mars is one of those grand, almost science fiction-like concepts that, if executed correctly, could drastically reshape the planet into something far more hospitable for human life. The process itself is not just a matter of brute force, of slamming rocks into the Martian surface, but a carefully orchestrated effort that requires an immense understanding of orbital mechanics, material composition, and the long-term atmospheric consequences of such an endeavor. It starts with identifying the right kind of celestial bodies, preferably water-rich asteroids or icy comets, ones that contain not just frozen water but also volatile compounds like carbon dioxide, methane, and ammonia, all of which could contribute to thickening Mars' thin atmosphere and increasing surface temperatures through the greenhouse effect. Imagine a team of engineers and scientists, not just sitting in a control room on Earth, but stationed in orbital habitats, or even small bases on Phobos and Deimos, working tirelessly to calculate the precise trajectory adjustments needed to bring one of these objects onto a collision course with Mars without creating an unmanageable disaster. It wouldn't be a process of simply nudging an asteroid with a rocket and hoping for the best. It would require years, maybe decades, of planning, using gravity assist from other planets, carefully timed burns from ion thrusters, or even nuclear propulsion systems attached to these spaceborne masses. The sheer scale of coordination would be staggering. People would be working across multiple teams. Orbital specialists calculating the asteroid's path down to fractions of a degree, materials scientists assessing the chemical makeup of the incoming body, planetary geologists determining the best possible impact zones, and of course, contingency teams running endless simulations to ensure that nothing goes catastrophically wrong. For the humans involved in this, there wouldn't just be the excitement of seeing the first successful redirection of an asteroid toward Mars, but also the weight of responsibility pressing down on them. One miscalculation could mean an impact in the wrong place, releasing too much energy at once, or worse, shattering the asteroid into countless unpredictable fragments that rain down in unintended locations. The tension in those final hours before impact would be something beyond anything experienced before. A mixture of anticipation, anxiety, and a deep awareness of just how much is riding on their work. And then, when the moment arrives, when the asteroid or comet finally plunges into the Martian surface, there would be that brief instant of silence, a collective holding of breath before the explosion, the shockwave, and the slow, billowing rise of dust and vaporized material into the thin Martian air. What follows wouldn't be immediate change, but a slow transformation. Gases being released into the atmosphere, ice melting into liquid, pockets of temporary warmth forming in the impact zones, and over time, small but significant increases in atmospheric pressure and temperature. The people monitoring from their orbital stations or from the surface bases would be watching these changes unfold, running constant measurements, observing how the new materials interact with Mars' existing environment, and determining the next steps. It wouldn't be just about brute force bombardment. There would be strategic refinements, redirecting additional smaller asteroids to specific locations, perhaps into the vast canyons of Valles Marineris to create subsurface lakes, or toward the poles to accelerate the melting of the ice caps. The process would take years, maybe centuries, but each successful impact, each incremental change in atmospheric density, each rise in temperature, would be a step forward in making Mars less of a barren wasteland and more of a place where people could eventually step outside without needing full-body pressure suits. The thought that future generations might one day walk through valleys where once there was only dust, where new rivers might carve their way through the terrain, would be what keeps these scientists and engineers going. Knowing that their work, their endless calculations, their relentless pursuit of a livable Mars, is laying the foundation for something far greater than any one lifetime could achieve. Of course, the idea of redirecting asteroids and comets to Mars isn't just about the sheer ambition of delivering water and gases to thicken its atmosphere. It's also about the delicate balance between control and chaos, the fine line between calculated impacts and unpredictable consequences. Even with the most advanced simulations, the most precise engineering, and the most skilled minds working to ensure that each impact contributes to a long-term vision, there is always the looming reality that things might not go according to plan. No matter how much control humanity exerts over these celestial bodies, once they are set on their final trajectories, there is an element of inevitability, a recognition that the moment of impact itself is beyond human intervention. It's a moment where everything rests on the accuracy of every prior decision, every adjustment made in deep space, every minute calculation that determined how much force was needed to shift an object traveling millions of kilometers through the void. For the people involved, the distinction between a controlled impact and an unintended catastrophe is more than just an academic one. It's the difference between success and disaster, between an elegant act of planetary engineering and an irreversible mistake that could set progress back by decades. The stress of making sure that everything aligns perfectly is something that can't be overstated. Picture a team of scientists huddled around screens, running last-minute trajectory confirmations, double-checking the expected dispersal of impact debris, ensuring that the kinetic energy of the asteroid won't eject too much material into space or create a dust cloud so thick that it plunges Mars into a temporary deep freeze rather than warming it. There would be constant discussions about risk mitigation, about whether an impact zone is truly as stable as their models suggest, about whether a slightly different approach might be necessary even when they're already months or years into a mission. Even when all the calculations suggest a controlled outcome, there are variables that no one can fully predict. The structure of an asteroid, for example, is never entirely uniform. An object that seems solid on the surface might be riddled with hidden cavities, causing it to fragment unpredictably upon entry. The Martian terrain itself, though mapped in exquisite detail, may still harbor unknown factors. Subsurface ice deposits that, when struck, release gases in unexpected ways, or deep fractures in the crust that amplify the impact shockwave more than anticipated. And beyond the immediate consequences, there's the long game. The question of how Mars' evolving atmosphere will behave as more impacts occur, whether the gradual buildup of greenhouse gases will follow the intended trajectory, or if unforeseen chemical interactions will introduce complications no one anticipated. For those living on Mars, whether in early research stations or, much further in the future, in domed settlements or even partially terraformed regions, each impact event would carry a mixture of excitement and unease. They would know that with each successful redirection, Mars inches closer to becoming a more habitable world, but they would also be acutely aware of the dangers. They would hear the low-frequency rumbles through the thin air when an impact occurs hundreds of kilometers away, see the plumes of dust rising on the horizon, feel the subtle tremors beneath their feet as the energy from each collision ripples through the crust. They would be living with the consequences in real time, witnessing the slow transformation of their world while also knowing that, despite all the planning, nature doesn't always conform to human expectations. Perhaps the most unnerving aspect of all is that even a slight miscalculation could turn an intended contribution to Mars' atmosphere into a setback, an impact that throws up too much debris, lowering temperatures instead of raising them, or one that releases toxic compounds that make habitation more difficult rather than less. The idea of controlled impacts is based on an assumption of mastery, of an ability to dictate the course of planetary change. But every person involved would understand that it is, at best, a form of guided chaos, a calculated gamble where the stakes are nothing less than the future of an entire world. The line between progress and unintended catastrophe is razor-thin, and the people making these decisions would live with the weight of that knowledge every single day. Even if every asteroid impact were perfectly calculated, every gas release precisely controlled, and every trajectory flawlessly executed, the fundamental challenge of terraforming Mars doesn't end with simply making it warmer. It's about making it warm enough without pushing it too far. The process of altering an entire planet's climate isn't a straightforward equation with guaranteed results. It's a complex, interwoven system where small changes can spiral into massive, unintended consequences. The very forces that could transform Mars from a frozen wasteland into a habitable world could, if pushed too aggressively or without the right checks, turn it into something else entirely. An environment that swings from unlivable cold to equally unlivable heat. A place where the progress meant to make it more Earth-like instead renders it chaotic and unstable. For the scientists and engineers overseeing this process, the fear of overheating Mars wouldn't just be an abstract concern. It would be a real, measurable possibility that would have to be constantly monitored with every atmospheric adjustment, every greenhouse gas introduction, and every major impact event. The early stages of warming the planet would likely be slow and difficult, requiring immense effort just to nudge temperatures a few degrees upward. But once the process gains momentum, once a self-sustaining greenhouse effect is established, there's always the danger that it doesn't stop where humans want it to. There's a tipping point where control could slip away, where instead of a steady rise toward habitability, Mars could overshoot into something more volatile, a planet where heat gets trapped too efficiently, leading to surface temperatures that spike beyond what early settlers could tolerate. The problem isn't just about rising temperatures. It's about the secondary effects that come with them. If the polar ice caps and subsurface ice reserves melt too quickly, they could release massive amounts of water vapor all at once, overwhelming the thin atmosphere and creating temporary storms of a scale never before seen. Dust-choked hurricanes of moisture and debris that could tear through early colonies before the atmosphere has even stabilized. If too many impact events release excessive carbon dioxide or methane in a short period, the warming effect could accelerate beyond what was intended, setting off a runaway process that scientists may struggle to reverse. The thin Martian crust, weakened by impacts and thermal expansion, could begin fracturing in unpredictable ways, triggering landslides and seismic activity in places where early settlers had assumed stability. For the people actually living on Mars, the experience of such an overheating scenario would be terrifying in ways that go beyond simple temperature readings. Imagine a research outpost built in a region that had once been stable, a place where early climate models had predicted mild warming over decades. But then, a series of unexpected shifts. Perhaps a slightly higher than expected release of greenhouse gases from an impact site, or an underestimation of how much energy the newly thickened atmosphere would retain, sends local temperatures soaring past safe levels. Dust storms that had once been predictable seasonal events become longer, more violent, more capable of burying infrastructure beneath meters of fine particulate. Underground ice reserves, once a promising water source, melt at a rate that floods entire lowland areas, creating unstable, shifting landscapes that make continued habitation a logistical nightmare. Colonists who had once imagined a slow and steady transformation of their world would suddenly find themselves fighting to survive in an environment that no longer matches their carefully planned projections. The idea of making Mars warmer has always been framed as a necessity, a requirement for making the planet livable without relying entirely on artificial habitats, but it's rarely considered how little room for error actually exists. The difference between a comfortably warmed Mars and one that becomes a new kind of inhospitable wasteland might only be a few degrees, a handful of miscalculations in gas release rates or atmospheric retention. And once the process has gone too far, there's no simple way to undo it. There's no quick fix for a planet-wide heat crisis, no easy solution for dialing back a runaway climate shift. The same people who once celebrated the success of warming Mars would instead find themselves desperately searching for ways to slow it back down, realizing too late that they had underestimated just how little control they truly had. 18. Potential for underground habitats. If Mars were to become too unstable on the surface, whether from unexpected atmospheric shifts, raging dust storms, or even just the sheer unpredictability of a still developing climate, there would be only one real refuge: beneath the ground. Even in the earliest stages of colonization, long before Mars became anything close to habitable, the safest and most logical place for people to live wouldn't be inside artificial domes exposed to the elements, but within the ancient tunnels left behind by long-extinct volcanic activity. The planet's vast system of lava tubes, some stretching for kilometers beneath the surface, offers something that no amount of surface engineering could match: natural protection from radiation, insulation against extreme temperature swings, and a level of structural integrity that no human-built habitat could replicate without enormous effort. For the people who would one day call Mars home, the decision to move underground wouldn't be just about practicality. It would be about survival. Even with a thickened atmosphere and some level of surface habitability, the dangers of radiation exposure would linger for centuries, perhaps longer. Mars lacks a strong magnetic field, meaning cosmic rays and solar radiation would still pose a significant threat, enough to make long-term surface living dangerous without extensive shielding. Inside a lava tube, however, meters of solid rock would serve as a natural barrier, filtering out deadly radiation in a way that no lightweight artificial structure ever could. The temperature regulation would be another crucial advantage. Unlike the Martian surface, where temperatures can fluctuate dramatically between day and night, underground environments remain relatively stable, reducing the need for excessive energy consumption just to maintain livable conditions. The process of transforming these tunnels into habitable spaces would be an engineering challenge unlike anything attempted before. These lava tubes, some of which may be as wide as city streets and as deep as skyscrapers, would need to be carefully mapped, structurally reinforced where necessary, and sealed to allow for pressurization. Picture teams of astronauts, their suits thick with Martian dust, carefully maneuvering through these darkened tunnels, scanning the walls for fractures, testing the composition of the rock, searching for sections that could be safely converted into living quarters. They would need to install massive airlocks, create inner chambers where breathable air could be maintained, set up water and power systems, and find ways to integrate artificial lighting that wouldn't just illuminate the space, but also help maintain a sense of time and normalcy for those living within. The first settlers who made their homes in these tunnels would experience Mars in a way few would ever imagine. Not as a planet of vast open landscapes, towering dust storms, or endless rust-colored plains, but as a world of shadowed corridors, rock-hewn walls, and an ever-present awareness that the sky above them is something they rarely see. Their lives would be dictated by the rhythms of an underground existence, waking not to the sight of the Martian sunrise, but to the glow of carefully regulated artificial lights, walking through tunnels where every structure, every sealed doorway, every reinforced ceiling is a testament to the sheer effort required to carve out a place for themselves on this hostile world. Yet, despite the isolation, despite the lack of open skies and the feeling of being buried beneath alien rock, these underground settlements could become something far greater than just shelters of necessity. Over time, they could evolve into self-sustaining communities, interconnected networks of tunnels and chambers that house laboratories, hydroponic farms, recreation areas, and even places designed simply for comfort. Spaces where people could gather, talk, and feel something resembling normalcy. The knowledge that they were living within the remains of ancient Martian volcanism, within structures shaped by forces that had long since faded from the planet's history, would only add to the weight of their experience. They wouldn't just be surviving on Mars. They would be adapting, finding ways to make this barren world not just livable, but eventually, in some way, home. Living deep beneath the Martian surface, surrounded by rock and darkness, would offer protection and stability, but it would also create a new kind of challenge. One that had less to do with survival and more to do with the simple, inescapable need for life itself to feel alive. A world of metal corridors and artificial lights, where every breath of air is carefully measured and every drop of water meticulously recycled, is not a world that can sustain the human spirit indefinitely. No matter how advanced the technology, no matter how well-designed the habitats, people would crave something more. Something green, something growing, something that reminds them that they are not just surviving in a void of rock and dust, but living in a place that can, in some way, be made to flourish. That's where subsurface greenhouses would become more than just a necessity for food production. They would become psychological lifelines, places where the sterile, artificial environment of Martian tunnels would give way to something softer, something that moves and breathes and changes with time. The process of building these ecosystems wouldn't be easy, not in a place where sunlight never reaches and where every ounce of warmth and moisture has to be carefully controlled. These greenhouses wouldn't be the sprawling, sunlit farms of Earth, but enclosed, carefully managed biospheres, sealed against the thin Martian air, relying on artificial lighting tuned to mimic the wavelengths plants evolved to use back home. The soil, at least at first, wouldn't be soil at all but hydroponic or aeroponic systems, designed to make the most of the limited resources available. For those working to make these greenhouses a reality, every breakthrough would feel monumental. The first successful sprout, the first edible harvest, the first moment when stepping inside one of these sealed environments meant feeling a shift in air, a difference in smell, the faint, unmistakable scent of vegetation growing where nothing should grow. It would be an effort that goes beyond engineering and biology, something that blends both with an almost artistic precision, because these ecosystems would need to function as closed loops, places where waste is broken down and converted into nutrients, where oxygen and carbon dioxide cycle in perfect balance, where even the smallest imbalance could mean the difference between a thriving greenhouse and a failed experiment. And yet, despite the challenges, despite the knowledge that a single mistake could set back months of work, the rewards would be undeniable. Imagine walking through an underground corridor, past the cold, metal walls of a habitat module, and stepping into a space where the air is thick with moisture, where the walls are lined with leafy greens, where the hum of machines fades beneath the quiet rustling of plants shifting in artificial breezes. Imagine the simple act of touching a leaf, of breathing in air that feels different simply because it has passed through something alive. Over time, these spaces would become more than just agricultural projects. They would become refuges, places where colonists could reconnect with something primal, something that ties them back to Earth in a way no amount of technology ever could. As the systems improved, as methods became more refined, the greenhouses might even begin to expand beyond the practical, growing not just food but plants chosen for beauty, for scent, for the way they make a place feel like more than just a shelter. There would be a day when someone walks into one of these underground spaces and sees not just rows of crops but a small tree, something planted not because it was necessary but because it was wanted. Because the idea of a home on Mars isn't just about surviving the environment. It's about shaping it into something worth calling home. As underground greenhouses gradually turn from fragile experiments into stable, self-sustaining ecosystems, the question shifts from whether humans can survive beneath the Martian surface to whether they can truly live there, not just for years but for generations. A colony isn't just a collection of sealed habitats or a network of tunnels reinforced against collapse. It's a place where life is meant to continue, where people aren't just visitors but inhabitants, where children are born and grow up never knowing anything other than the reality of a world that has never seen an open sky. The real test of underground colonization isn't about the technology or the infrastructure. It's about whether human civilization can take root in a place so fundamentally alien, whether a settlement can become more than an outpost, whether Mars can ever feel like home. For the first few decades, the challenge wouldn't just be survival, but adaptation. Living underground would mean reshaping every aspect of daily existence, from the way time is tracked to the way space is used. Without a natural day-night cycle, colonists would have to rely entirely on artificial lighting to regulate their internal rhythms, their sense of morning and evening dictated not by the rising and setting of a sun, but by a programmed schedule of brightness and darkness. Space would be at a premium, every square meter carefully planned, every piece of infrastructure designed with the understanding that expansion would be slow and difficult. There would be no wandering outside without a suit, no casual walks under an open sky, no natural weather beyond what the controlled environment allows. Over time, the effects of such an existence would become more than just physical. They would shape the very way people think about life itself, about what it means to exist in a place where the world outside is a vacuum waiting to kill you, where everything safe and familiar is carved into the rock, where the sky is nothing more than a concept passed down from those who once lived on a planet where it could actually be seen. The psychological toll of such an existence would be impossible to ignore. The first generation of settlers, those who remember Earth, would carry with them a constant awareness of what they had left behind, a lingering sense of comparison between the world they knew and the one they now call home. But for those born on Mars, those who have never stood beneath an atmosphere, never felt an unfiltered breeze, never seen an ocean stretch beyond the horizon, the underground colony would be the only reality they have ever known. Their concept of normal would be fundamentally different, shaped by a world where nature exists only in controlled spaces, where the idea of being outside is something done only in a suit, where the boundaries of their universe are defined not by the vastness of the sky, but by the limits of the tunnels they inhabit. Over centuries, the colony would evolve, its structures expanding deeper into the planet, its systems becoming more refined, its population slowly growing. The tunnels that once felt like confined corridors would become vast underground cities, spaces designed not just for efficiency but for comfort, with open chambers that mimic natural landscapes, artificial lakes, carefully cultivated biomes where people can gather, relax, and feel something other than the cold, hard edges of survival. The question of sustainability would shift from the short-term concerns of food production and resource management to the larger issue of culture, of identity, of what it means to be Martian. Would future generations still feel connected to Earth, or would Mars develop its own distinct civilization, one with traditions and perspectives shaped by the reality of a world where everything is built, where nothing is taken for granted, where life itself is something carefully maintained rather than simply allowed to exist? The long-term viability of an underground colony wouldn't be decided by a single breakthrough, a moment where everything is suddenly proven to work. It would be a slow, generational process, a gradual transformation from an outpost to a home. And as the years pass, as the colony grows, as its people learn to live not as visitors, but as inhabitants, the tunnels that once felt like shelters from a hostile planet would instead become something else entirely. The foundations of a world that, while different from Earth in every imaginable way, is still unmistakably alive. 19. Ethical dilemmas of terraforming. Imagine standing on the barren surface of Mars, the wind whispering softly over the red dust, beneath a sky that glows faintly with the pale light of a distant sun. You are part of the first generation of terraformers, a pioneer in humanity's most ambitious endeavor, to reshape an entire world. The air is thin, cold, and unforgiving, but there's a dream that drives you, a vision that one day, this desolate land could bloom with life, that rivers could flow, forests could stretch toward the horizon, and children could run beneath a sky where clouds form naturally. Yet, as you look out over this alien landscape, an unsettling question lingers in your mind. Should we be doing this at all? There's something profoundly human about the desire to transform and control our environment. It's written in our history, from ancient civilizations diverting rivers for agriculture to modern cities rising from the ground. But here, on a world that has never known life as we understand it, the morality of this act feels different. Terraforming Mars, or any other celestial body, is not merely about survival or scientific achievement. It's about fundamentally altering a world that has existed untouched for billions of years. And in doing so, we risk carrying with us the very same destructive tendencies that have pushed Earth's ecosystems to the brink of collapse. You can't help but think about the subtle beauty of Mars as it is now. A world shaped by ancient rivers that long ago ran dry, sculpted by winds and dust storms that have danced across its surface for eons. In its silence and stillness, there's a kind of purity that feels almost sacred. To terraform this planet is to overwrite that ancient history, to erase the story that Mars tells through its valleys and craters. It raises the question of whether a lifeless world has its own intrinsic value, one that should be preserved, not for profit or colonization, but simply because it exists. And then there's the possibility, however small, that microbial life already exists beneath the Martian surface. To terraform would be to disrupt and potentially destroy that fragile, alien ecosystem before we even understand it? What right do we have to extinguish life that evolved independently from Earth? Would we not be repeating the same mistakes we've made throughout human history when explorers and conquerors wiped out indigenous cultures and ecosystems in the name of progress? Yet, the other side of your mind whispers that this is who we are. We are wanderers and builders, driven by curiosity and survival. Earth is fragile, vulnerable to climate change, resource depletion, and the threat of global conflict. To terraform another world is to secure a future for humanity, to give our descendants a chance to thrive beyond the cradle of Earth. It's an act of creation, of hope, of ensuring that consciousness itself endures in the universe. But it's not just about survival. There's something deeply poetic in the idea of breathing life into a dead world. To see plants grow in Martian soil, to feel rain fall on alien ground, to hear the laughter of future generations beneath an artificial sky. Isn't that a kind of beauty worth striving for? Yet, that beauty comes with a cost, not just in resources and technology, but in moral responsibility. Once we begin, there's no turning back. The ecosystems we create will be shaped in our image, with our biases, our flaws, and our incomplete understanding of nature's balance. As you stand there, gazing at the rust-colored horizon, you feel the weight of all those who will come after you. The children who will call this place home, who will never know the raw, untouched Mars that exists today. You wonder if they will feel a connection to this world, or if it will simply be another extension of human ambition. Will they look back at this moment and thank us for giving them a future? Or will they curse us for stealing the untouched mystery of an ancient world? In the end, the ethical dilemma of terraforming isn't about technology or science. It's about what kind of species we choose to be. Are we creators, bringing life to barren worlds in the name of survival and beauty? Or are we colonizers, forever consuming and reshaping everything we touch until nothing remains that is not of our own making? Perhaps the answer lies not in avoiding the act of terraforming altogether, but in approaching it with humility, wisdom, and respect for the worlds we seek to change. Because once we begin, we won't just be altering planets. We'll be defining what it means to be human in a universe that is vast, ancient, and, until now, untouched by our hands. And yet, beneath the moral weight of reshaping an entire planet, there lies an even more unsettling possibility. That in our quest to make Mars habitable for ourselves, we might unknowingly destroy something ancient and profoundly unique. The thought lingers, quiet and uncomfortable, in the back of your mind as you move across the dusty Martian soil. What if, beneath this seemingly lifeless surface, there is something alive? Not in the way we understand life, not green forests or flowing rivers, but microscopic organisms clinging to survival in hidden, ancient aquifers or deep within the planet's crust, shielded from the harsh radiation and thin atmosphere that have long stripped the surface barren. The idea is almost too fragile to grasp. That somewhere, deep in the Martian subsurface, life could have emerged independently from Earth's evolutionary path. A separate biology, untouched by the history of our planet, evolving over billions of years in complete isolation. It wouldn't be the kind of life that fills science fiction stories, not complex creatures or alien civilizations, but something simpler, quieter, yet infinitely more profound. Microbes that could hold within their structure an entirely different genetic code, one that speaks of a second genesis in the universe, proving that life is not unique to Earth, but a phenomenon that arises wherever the conditions allow it. And here we are, arriving as explorers, scientists, and future colonizers, carrying not just the weight of human ambition, but the bacteria and microbes of Earth itself. With every step, every piece of equipment drilled into the Martian ground, we risk contaminating this untouched ecosystem with terrestrial life. We risk drowning out whatever fragile biology might exist here, overwhelming it with organisms that evolved in Earth's oceans and forests. What if, in the process of terraforming, we introduce Earth-based microbes that outcompete native Martian life, wiping out an entire evolutionary history before we even have the chance to study or understand it? There's something deeply unsettling about that. It's not just the scientific loss, the loss of knowledge, of understanding how life arises in the cosmos, but something more intimate. It's the idea that we would be erasing something ancient, something that existed long before we looked up at the stars and dreamed of touching other worlds. Life that struggled and adapted in conditions we can barely comprehend, surviving in silence for billions of years, only to be extinguished by the arrival of creatures from a distant blue world, who came not out of malice, but out of ignorance and ambition. It's a strange and deeply human fear that in our search for life elsewhere, we might be the very thing that destroys it. That we could become cosmic colonizers, not by force or violence, but through carelessness and the arrogance of believing that life must bend to our needs. And yet, how do we proceed? Do we turn away from Mars, leaving it untouched, forever wondering what might have been hiding beneath its surface? Or do we press forward with caution and reverence, hoping that our science and technology are advanced enough to detect native life before we unknowingly wipe it away? There's no clear answer, because this isn't just a scientific question, it's an ethical one. It forces us to confront not only what we want from the universe, but what kind of species we want to be as we step beyond Earth. Are we explorers, driven by curiosity but bound by responsibility? Or are we conquerors, destined to spread across worlds, regardless of what we leave behind in our wake? The terrifying part is that we may not know we've crossed that line until it's too late. Until the last traces of ancient Martian life have been buried beneath the ecosystems we create, lost forever in the dust we claimed as our own. And yet, beneath the moral weight of reshaping an entire planet, there lies an even more unsettling possibility. That in our quest to make Mars habitable for ourselves, we might unknowingly destroy something ancient and profoundly unique. The thought lingers, quiet and uncomfortable, in the back of your mind as you move across the dusty Martian soil. What if, beneath this seemingly lifeless surface, there is something alive? Not in the way we understand life, not green forests or flowing rivers, but microscopic organisms clinging to survival in hidden, ancient aquifers or deep within the planet's crust, shielded from the harsh radiation and thin atmosphere that have long stripped the surface barren. The idea is almost too fragile to grasp, that somewhere, deep in the Martian subsurface, life could have emerged independently from Earth's evolutionary path. A separate biology, untouched by the history of our planet, evolving over billions of years in complete isolation. It wouldn't be the kind of life that fills science fiction stories, not complex creatures or alien civilizations, but something simpler, quieter, yet infinitely more profound. Microbes that could hold within their structure an entirely different genetic code, one that speaks of a second genesis in the universe, proving that life is not unique to Earth, but a phenomenon that arises wherever the conditions allow it. And here we are, arriving as explorers, scientists, and future colonizers, carrying not just the weight of human ambition, but the bacteria and microbes of Earth itself. With every step, every piece of equipment drilled into the Martian ground, we risk contaminating this untouched ecosystem with terrestrial life. We risk drowning out whatever fragile biology might exist here, overwhelming it with organisms that evolved in Earth's oceans and forests. What if, in the process of terraforming, we introduce Earth-based microbes that outcompete native Martian life, wiping out an entire evolutionary history before we even have the chance to study or understand it? There's something deeply unsettling about that. It's not just the scientific loss, the loss of knowledge, of understanding how life arises in the cosmos, but something more intimate. It's the idea that we would be erasing something ancient, something that existed long before we looked up at the stars and dreamed of touching other worlds. Life that struggled and adapted in conditions we can barely comprehend, surviving in silence for billions of years, only to be extinguished by the arrival of creatures from a distant blue world, who came not out of malice, but out of ignorance and ambition. It's a strange and deeply human fear, that in our search for life elsewhere, we might be the very thing that destroys it. That we could become cosmic colonizers, not by force or violence, but through carelessness and the arrogance of believing that life must bend to our needs. And yet, how do we proceed? Do we turn away from Mars, leaving it untouched, forever wondering what might have been hiding beneath its surface? Or do we press forward with caution and reverence, hoping that our science and technology are advanced enough to detect native life before we unknowingly wipe it away? There's no clear answer, because this isn't just a scientific question, it's an ethical one. It forces us to confront not only what we want from the universe, but what kind of species we want to be as we step beyond Earth. Are we explorers, driven by curiosity but bound by responsibility? Or are we conquerors, destined to spread across worlds, regardless of what we leave behind in our wake? The terrifying part is that we may not know we've crossed that line until it's too late. Until the last traces of ancient Martian life have been buried beneath the ecosystems we create, lost forever in the dust we claimed as our own. 20. Terraforming Mars versus Venus, which is easier? And so, as humanity grapples with the ethical weight of transforming Mars, there's an inevitable question that lingers in the minds of scientists and dreamers alike. Why Mars? After all, if the goal is to make a planet habitable, why not turn our eyes toward Venus, Earth's so-called sister planet, with its similar size and gravity? Yet, despite its closer proximity to Earth and its more familiar dimensions, Venus remains a far more brutal and unforgiving world, one that seems to resist human intervention at every level. It's strange when you think about it. On the surface, Venus should be the more logical choice. It's closer to Earth, bathed in sunlight, and similar in size. But standing on Venus, if such a thing were even possible, would be like standing in a nightmare. The atmosphere is a crushing, toxic soup of carbon dioxide, thick enough to create pressures that would crush a human body within seconds. The surface temperature is hot enough to melt lead, not because Venus is close to the sun, but because of an unstoppable greenhouse effect that has turned the planet into a suffocating inferno. The clouds above are not made of water, but sulfuric acid, reflecting sunlight and trapping heat in a way that makes Venus the hottest planet in the solar system, despite Mercury being closer to the sun. You can't help but imagine what it would feel like to step onto such a world. The air so dense it feels like walking through an ocean of heat and poison, the sky permanently shrouded in thick, yellow clouds, with no glimpse of the stars or the sun. Even the very ground beneath your feet would feel hostile, baked and cracked by relentless heat, while above, lightning crackles through the acidic atmosphere. The sheer brutality of Venus makes any thought of terraforming feel almost absurd, not because we lack the technology, but because we would be fighting against a planetary system that is already in violent equilibrium. Mars, on the other hand, feels different. Cold, yes. Barren, certainly. A world that once had flowing water, riverbeds, and perhaps even lakes. The atmosphere is thin, but not non-existent. The gravity, though weaker than Earth's, is enough to hold an atmosphere if we could thicken it. And the planet's polar ice caps, rich in water and carbon dioxide, offer the raw materials to begin warming the planet and releasing greenhouse gases. Mars feels less like an enemy and more like a sleeping world, one that, with patience and effort, could be awakened. It's not that Mars is easy. It's that Mars, in its quiet stillness, is cooperative in a way that Venus never will be. On Mars, we can imagine slowly warming the planet, releasing carbon dioxide to create a thicker atmosphere, and eventually allowing liquid water to flow again. We can envision genetically engineered plants spreading across the Martian soil, producing oxygen, while future generations build habitats and cities beneath domes that slowly give way to open skies. It would take centuries, maybe millennia, but there's a path forward, one that feels like nurturing life on a world that once held the potential for it. With Venus, there is no gentle path. To terraform Venus would mean dismantling its entire atmosphere, somehow stripping away billions of tons of carbon dioxide, or finding a way to shield the planet from sunlight to cool it enough for water to exist. Some have proposed giant solar reflectors or seeding the upper atmosphere with reflective particles, but these solutions feel desperate, like trying to tame a storm that has raged for millions of years. And maybe that's why Mars calls to us in a way Venus never can. Because deep down, we're not looking for a planet to conquer. We're looking for a world that allows us to begin again. Mars is not a perfect world, but it's one that holds echoes of something familiar. Ancient river valleys, polar ice caps, and a day that lasts only slightly longer than ours. It's a world that feels quiet, waiting, almost forgiving in its emptiness. Venus, in contrast, feels like a reminder of what happens when a world spirals out of balance, a place where nature itself has turned hostile, not out of malice, but out of unstoppable chemistry and physics. And so, humanity looks toward the cold, red deserts of Mars, not because it's easy, but because it's possible. Because when you stand beneath the pale Martian sky and feel the thin wind brushing against your suit, you can almost imagine what it would be like to breathe there one day. To see plants growing in the soil, to hear the sound of water flowing through ancient channels, to watch children run across the dust that once belonged only to the stars. Mars allows us to dream, while Venus reminds us of how fragile and rare life truly is. And perhaps, in the end, that's what makes Mars the world worth fighting for. But the truth is, even as humanity turns its eyes toward Mars, there's an unsettling fascination with Venus that refuses to be silenced. A world that feels so close, so familiar in size and gravity, yet so utterly hostile that it seems to defy everything we understand about planetary habitability. It's almost ironic, really. Venus should be the paradise of the solar system. It orbits within what we call the habitable zone, where temperatures should allow liquid water to exist, and its size and mass are nearly identical to Earth's. And yet, something went horribly wrong there. Standing on the surface of Venus would be like standing at the bottom of a pressure cooker, where the atmosphere is nearly 100 times denser than Earth's, hot enough to melt lead, and thick with carbon dioxide. The planet's clouds aren't soft and white like Earth's, but composed of droplets of sulfuric acid, endlessly reflecting sunlight and trapping heat in a runaway greenhouse effect that turned the planet into a suffocating furnace. It's strange to even imagine what terraforming such a world would require. The very atmosphere is the enemy. A choking blanket of carbon dioxide that weighs down on the surface and traps heat with brutal efficiency. Unlike Mars, where the challenge is to build an atmosphere, Venus's atmosphere would need to be stripped away or fundamentally altered. But how do you remove billions of tons of carbon dioxide from an entire planet? How do you dismantle an atmosphere that's been building itself for billions of years? Some scientists have proposed wild, almost science fiction-like solutions. Giant solar shades placed in orbit to block sunlight and cool the planet, or massive chemical reactions that could bind carbon dioxide into solid carbonates and trap it in the ground. Others suggest seeding the upper atmosphere with reflective aerosols to reduce the planet's temperature, or even engineering massive microbial organisms that could survive in the acidic clouds and slowly convert carbon dioxide into oxygen. But these ideas, while imaginative, feel almost absurd when faced with the sheer scale of the problem. Venus's atmosphere isn't just thick. It's dynamic and aggressive, with hurricane-force winds and temperatures that can melt spacecraft within hours. Even if we somehow cooled the planet, the carbon dioxide would simply condense into liquid and form vast, toxic oceans, which would eventually evaporate back into the atmosphere once the heat returned. And yet, there's something deeply human about wanting to solve this impossible puzzle. To look at a world that seems utterly lost and wonder if there's a way to bring it back, to strip away the layers of suffocating heat and reveal the planet that might have once had oceans and gentle skies. But the deeper you think about it, the more you realize that terraforming Venus isn't just about technology or science. It's about time itself. Mars feels like a sleeping world, one that we can slowly nurture and awaken. But Venus feels ancient and broken, like a planet that burned itself out long before we arrived. And undoing that process would mean unraveling billions of years of chemistry and physics that have spiraled out of control. And that's what makes it so haunting. Because you begin to realize that Venus isn't just a hostile world. It's a warning. A reminder of what happens when a planet loses balance, when greenhouse gases spiral beyond control, and the atmosphere becomes a trap instead of a cradle for life. In a strange way, Venus feels like a reflection of Earth's own future, a glimpse of what could happen if we continue to push our own planet toward climate collapse. Maybe that's why Venus feels so unreachable, not because we lack the technology, but because it forces us to confront something terrifyingly familiar. So, as humanity sets its sights on Mars, there's an unspoken sadness in leaving Venus behind, a world that once might have been Earth-like, with oceans and skies and the potential for life, but now exists as a graveyard of what could have been. And perhaps that's the real difficulty of terraforming Venus. Not the physics, not the technology, but the quiet, uncomfortable truth that some worlds are not meant to be saved. Some are meant to remind us of how fragile life truly is, and how easily a planet can slip beyond the reach of those who once dreamed of calling it home. And yet, even as we accept the brutal reality of Venus, there's a part of the human mind that refuses to let go of the idea. The quiet, persistent thought that maybe we're looking at it the wrong way. Maybe the mistake isn't in trying to make Venus more like Earth, but in reimagining what it means for a planet to be livable in the first place. What if, instead of trying to strip away the atmosphere and cool the surface, we simply learn to exist within the world that Venus already is? You begin to wonder, what if the problem isn't the planet, but our own stubborn need to stand on solid ground? After all, the crushing heat and pressure exist only on the surface. But high above, in the upper layers of Venus's thick atmosphere, there's a strange and almost poetic balance. Around 50 kilometers above the surface, the temperature and pressure become surprisingly Earth-like. The air is still thick with carbon dioxide, but the conditions are far more survivable. Enough that, theoretically, floating habitats could exist there, drifting through the Venusian skies like cities suspended in an endless sea of clouds. It's an idea that feels surreal at first, almost dreamlike. Vast, balloon-like structures filled with breathable air, which would naturally be lighter than the surrounding carbon dioxide, allowing them to float effortlessly in the dense atmosphere. These floating cities could be powered by the relentless sunlight that bathes Venus, using solar panels to generate energy, while advanced filtration systems extract water from the trace amounts of water vapor that exist in the air. The sulfuric acid clouds, while hostile, could be neutralized with chemical reactions, allowing us to create protective barriers around these floating colonies. And as strange as it sounds, there's something oddly fitting about the idea. Humans, drifting through the skies of a world that burned itself long ago, adapting not by conquering the surface, but by learning to exist in the space where life can still find balance. It would be a world of perpetual twilight, with the sun casting an eerie orange glow through the thick, acidic clouds. The view from those floating cities would be unlike anything on Earth. An endless sea of swirling clouds below and a dim, alien sky above, with no ground beneath your feet, only the gentle buoyancy of the Venusian atmosphere holding you aloft. And in a way, it feels more honest than terraforming. Because this wouldn't be about forcing Venus to change, but about adapting ourselves to the reality of what Venus has become. It wouldn't be about undoing billions of years of planetary evolution, but finding the cracks in its hostile system where life can still exist. There's something humbling in that, in the idea that we don't always have to bend the universe to our will, but instead, learn to exist within its extremes. Of course, the challenges would be immense. Building self-sustaining habitats in an atmosphere filled with acid and carbon dioxide would require technology far beyond what we currently possess. The materials would need to be resistant to corrosion, the energy systems flawless, and the human psychology of living in an endless sky. With no solid ground, no oceans, no familiar landscapes, would push the limits of what we understand about isolation and adaptation. But there's also something undeniably beautiful about it. Because, in a strange way, living in the skies of Venus would be a reminder of how fragile and temporary we are. Tiny, floating creatures suspended between the crushing heat of a dead world below and the cold emptiness of space above. It would be a place where humanity would truly have to embrace humility, not as conquerors of planets, but as quiet, careful inhabitants of a world that doesn't forgive mistakes. And maybe that's the real path forward, not trying to force Venus to become Earth, but learning to meet it where it is, in the thin line between destruction and survival. Because if we can do that, if we can find life in the most unlikely of places, then maybe, just maybe, we'll prove that humanity's true strength isn't in reshaping worlds, but in finding beauty and survival in the places where no one else would dare to look. 21. Paraterraforming, an alternative approach. Paraterraforming is the idea of creating large, enclosed habitats on the surface of an otherwise uninhabitable planet rather than attempting to alter the entire planet's environment to make it Earth-like. Instead of the overwhelming challenge of transforming an entire atmosphere, stabilizing temperatures, and introducing an ecosystem that could take centuries or even millennia to fully develop, paraterraforming takes a more immediate and controlled approach by constructing vast, self-contained environments where humans can live comfortably. These domed structures would be designed to maintain stable atmospheric pressure, provide breathable air, regulate temperature, and recycle resources, allowing for sustainable human habitation without the need to wait for large-scale planetary engineering to take effect. Imagine a group of settlers arriving on Mars, not with the impossible task of changing an entire world, but with the mission of carefully constructing enclosed environments, each one designed to sustain life with Earth-like conditions. Instead of standing on a barren, radiation-blasted wasteland, they would step into a world of their own making, where artificial skies cast warm light overhead, plants grow in carefully maintained hydroponic farms, and clean air circulates through filtration systems that ensure survival in a place that was never meant for human life. Within these domes, people would live, work, raise families, and push the boundaries of human existence beyond Earth, all while standing on the surface of a planet that remains as inhospitable as ever just outside their protective walls. Rather than relying on theories of atmospheric modification that could take generations to show any real results, these enclosed structures would allow for a more immediate expansion of human civilization into space, with each new dome acting as a stepping stone toward a more permanent presence. Over time, interconnected domes could form entire cities, creating a network of habitable spaces that would allow people to move between them without exposure to the deadly conditions beyond their barriers. The psychological aspect of such an existence would be just as important as the technical, as living under a dome, separated from the hostile landscape outside, would demand new ways of thinking about community, freedom, and survival. For those born inside these domes, the idea of a limitless sky or an open horizon would be something they could only experience through images or simulations, a reminder that while they live on another world, they are still bound by the constraints of an artificial environment. They might see the rocky Martian landscape through reinforced windows, knowing that stepping outside without a suit would be fatal, yet within their sheltered world, life would go on. Children playing in artificial parks, scientists working in advanced laboratories, engineers maintaining the delicate systems that keep everyone alive. Over time, these structures would evolve, becoming more sophisticated, perhaps even expanding into underground sections to protect against radiation or incorporating advanced materials that make them more resistant to the extreme conditions beyond their walls. Paraterraforming is not about conquering a planet and bending it to human will. It is about adapting to an alien world with a pragmatic approach, recognizing the limits of our technology while still pushing forward into the vast unknown. Instead of waiting for the distant possibility of a fully terraformed Mars or another world transformed to mimic Earth, this method provides a realistic, achievable way to begin settling new planets within the lifetimes of those who dare to leave Earth behind. In the end, it is not about making these planets like Earth, but about creating habitable spaces within them, places where life can thrive even in the midst of a world that remains utterly indifferent to human existence. While paraterraforming focuses on creating enclosed habitats as a practical way to establish human settlements on uninhabitable worlds, localized terraforming takes this concept a step further by making targeted environmental changes to specific regions rather than attempting to transform an entire planet. Instead of enclosing humanity in domes indefinitely, this approach seeks to modify carefully selected areas, gradually expanding habitable zones that allow for more natural movement and interaction with the planet's surface. It is a middle ground between the daunting scale of full-scale planetary engineering and the confined existence of isolated habitats, offering a way to carve out livable spaces in a world that would otherwise remain hostile. Picture a settlement on Mars where, instead of relying solely on domed structures, engineers have begun altering the surrounding environment in controlled ways to make it more forgiving. They start with enclosed habitats, but over time, they deploy systems that generate heat, thicken the local atmosphere, and introduce controlled amounts of moisture into the soil, creating pockets of land where stepping outside does not require a full pressure suit. Perhaps just an oxygen mask and protective clothing rather than a cumbersome, life-supporting exosuit. With each new breakthrough, these patches of modified land expand, transforming lifeless dust into places where the sky is still thin but no longer entirely suffocating, where plant life begins to take hold in engineered soil, and where future generations might walk under an open but still alien sky, feeling at least a fraction of the freedom Earth once provided. Localized terraforming acknowledges the staggering difficulty of altering an entire planet's atmosphere and instead focuses on manageable changes, using targeted greenhouse gas release, underground heat generators, and soil enrichment techniques to transform small regions into microclimates that support human activity. Unlike traditional terraforming, which might take centuries before its effects are noticeable, this approach allows settlers to see and experience progress within a single lifetime, knowing that their work is actively making a difference in how they live. It also provides a level of safety. If an experiment fails, it does not threaten the entire colony but only affects a limited area, allowing scientists to refine their methods without catastrophic consequences. Over time, these transformed zones would connect, linking settlements with breathable corridors, making long-range travel on foot or by light vehicles possible without relying entirely on enclosed pressurized transports. The idea of isolation would slowly fade as humans gain the ability to move freely between locations without constantly fearing exposure to deadly conditions. Those born on this world might grow up watching their parents work to expand these patches of habitability, knowing that their future could include walking across a landscape that, while still not Earth, has been reshaped into something where life is possible beyond the confines of sealed walls. Localized terraforming offers something that neither paraterraforming nor full-scale planetary modification can provide on their own: a balance between feasibility and ambition. It does not demand that people live in artificial bubbles forever, nor does it require centuries of effort before any real benefits can be seen. Instead, it is a method of taking control of a hostile world in a way that is both immediate and scalable, ensuring that every generation of settlers experiences the rewards of progress rather than simply working toward a goal they will never see completed. It is not about making another Earth. It is about making the most of a planet that will never be Earth, shaping it into something survivable, something livable, something that can one day feel like home. As localized terraforming makes it possible to create small pockets of habitable land on otherwise unlivable worlds, the natural question that follows is whether these zones could be expanded over time, gradually transforming more of the planet into a place where humans can exist with increasing freedom. While an individual settlement might begin as a single cluster of domes or a carefully controlled microclimate, the long-term goal would be to extend these modifications outward, pushing back against the harsh planetary conditions inch by inch, decade by decade, until entire regions are no longer defined by their hostility, but by the life that has been introduced and sustained within them. Instead of simply surviving in an isolated colony, people could begin to think about shaping the world around them in a way that allows for real permanence, something that future generations might look back on as the first true steps toward making another world feel like home. In the early years of such an expansion, progress would be slow, with each new section of modified terrain requiring careful planning and resource management. Scientists and engineers would work to identify the most effective ways to alter the local environment, whether by thickening the atmosphere in specific areas to reduce radiation exposure, introducing engineered plant life that can survive in low-pressure conditions, or creating underground reservoirs that gradually release moisture into the air. Settlers would witness firsthand the transformation of their surroundings, seeing barren rock and dust slowly replaced with pockets of land where simple plant life begins to take hold, where the air is just a little easier to breathe, where stepping outside for short periods becomes possible without the constant fear of immediate death. The psychological impact of this would be profound. No longer trapped inside static structures, people would feel a growing connection to the land itself, knowing that their work is shaping it into something that future generations will one day take for granted. As technology advances and the understanding of planetary modification deepens, the pace of expansion could accelerate, with breakthroughs leading to larger-scale environmental changes that might allow entire valleys, craters, or low-lying basins to be transformed into stable, semi-habitable regions. Perhaps an early colony begins by modifying only a few square kilometers around a settlement, but within a century, a vast stretch of land has been altered enough that permanent outdoor infrastructure can be built, allowing for agriculture, recreation, and transportation without the absolute dependence on enclosed habitats. The moment when someone can walk outside with nothing more than a breathing mask, feeling the natural warmth of a sun that no longer burns unfiltered through a thin, ineffective atmosphere, would mark a true turning point. Proof that human ingenuity is capable of bending even the most unforgiving environments into something survivable. Over generations, the line between habitable and uninhabitable would continue to shift, with expanding zones of modified land making it easier to build new settlements, support larger populations, and even introduce ecosystems that do not just survive but actively flourish in these engineered conditions. The first children born on such a world might still live in tightly controlled spaces, but their grandchildren might grow up running through artificial forests, playing in fields of bioengineered crops, and watching distant dust storms from the safety of vast, interconnected habitable regions that stretch farther than their ancestors ever imagined possible. It would be a slow, relentless process, one that might never result in a fully Earth-like world, but could still create a reality where an increasing number of people live on a planet that once seemed utterly incapable of supporting life. The expansion of habitable zones is not about instant transformation or the illusion of conquering nature. It is about persistence. About the slow but undeniable reshaping of an environment in a way that favors life rather than erases what was there before. It is not about waiting for a distant future where an entire planet is magically made perfect, but about taking small, deliberate steps that each generation can witness, contribute to, and benefit from. And as those boundaries of habitability stretch outward, so too does the potential for human civilization to thrive beyond the limits of Earth, proving that survival is not just about endurance, but about the ability to reshape the world itself, one breath of altered air at a time. 22. Genetic engineering and terraforming. As humans slowly push the boundaries of habitable zones on distant worlds, expanding their reach beyond isolated settlements and into the surrounding landscape, the challenge of making these environments self-sustaining becomes more urgent. No matter how advanced technology becomes, relying entirely on artificial systems to regulate air, water, and food production is neither practical nor desirable in the long run. The key to true expansion lies in something deeper, something that has shaped life on Earth for billions of years: biology itself. Instead of merely engineering structures to protect life from an inhospitable planet, genetic modification offers the possibility of changing life itself to survive in conditions that would otherwise be impossible. By altering plants and microorganisms at a fundamental level, scientists could create living systems capable of thriving in the thin atmosphere, harsh radiation, and nutrient-poor soil of a place like Mars, setting the foundation for ecosystems that might one day take root and grow beyond human intervention. The process would not be as simple as planting Earth crops in Martian soil and hoping for the best. Every biological system on Earth has evolved to function within the dense, oxygen-rich atmosphere and stable climate of our home planet, conditions that do not exist anywhere else. But by modifying organisms at the genetic level, it may be possible to create life forms that can survive and even flourish in an alien world. Microbes could be engineered to process the toxic Martian regolith, extracting useful minerals while breaking down harmful compounds that would otherwise prevent plant growth. Certain bacteria might be designed to produce greenhouse gases in controlled amounts, thickening the atmosphere just enough to make the environment more forgiving. Fungi, capable of thriving in extreme conditions, could serve as early pioneers, breaking down rock and releasing organic material that future plant life could use to establish itself. Each of these organisms would be more than just a tool for survival. They would be the first step toward turning a barren world into one that can support more complex life. Once the groundwork is laid with microbial life, genetically engineered plants could follow, designed not just to endure the harsh conditions but to actively improve them. These plants might have the ability to extract nitrogen from the Martian atmosphere and store it in the soil, enriching it for future generations of crops. They could be altered to require far less water than their Earth counterparts, developing deep root systems that pull moisture from hidden reservoirs or waxy coatings that prevent evaporation in the dry, relentless winds. Some might even be bioengineered to produce oxygen in higher concentrations than any natural plant, slowly but surely contributing to an environment that, over generations, might become less hostile to human life. The sight of the first fields of genetically tailored crops growing beneath the dim Martian sky, their roots anchored in soil that was once lifeless dust, would be a profound moment. Proof that humans are not just visitors on this world, but active participants in its transformation. For those who would one day call Mars home, these advances would not just be scientific achievements, but necessities for survival. The food they eat, the air they breathe, the very ground they walk on would all be shaped by life that was never meant to exist there, but was carefully designed to do so. Entire agricultural systems would be built on plants that have never known Earth, crops that have been modified not only to withstand the Martian climate but to integrate with it, turning an alien world into something just a little more familiar. Over time, as these plants spread and adapt, and as microorganisms continue their slow but steady work beneath the surface, the first traces of something resembling an ecosystem might begin to emerge. Not one that mirrors Earth's, but one that is uniquely suited to its new home, growing and evolving alongside the humans who made it possible. Genetic engineering and terraforming is not about forcing Earth's biology onto a world where it does not belong, but about meeting an alien environment on its own terms and creating life that can exist within it. It is not an overnight transformation, nor is it a perfect replication of what was left behind, but rather a step towards something new. An ecosystem that begins with engineered survival and, if successful, might one day take on a life of its own. The future of Mars, or any other world that humanity seeks to shape, will not be built by machines alone. It will be built by living things, designed to thrive where nothing else could, growing in the shadow of a sky that has never seen green before, slowly rewriting the very nature of an uninhabitable world. If genetically engineered plants and microorganisms can be designed to survive on Mars, shaping the environment in ways that make it more livable, then it is only natural to ask whether humans themselves could be modified to better endure the planet's harsh conditions. While technology and biology can work together to make an alien world more habitable, there is also the possibility of shifting the burden of adaptation onto the settlers themselves. Altering human physiology at the genetic level to reduce dependence on artificial habitats and protective equipment. Rather than bending Mars to fit human needs, this approach asks whether humanity could be reshaped, even slightly, to exist more comfortably in an environment that would otherwise be lethal. It is not about creating a separate species or losing what it means to be human, but about making survival less fragile, about allowing people to step onto an alien world with bodies better suited to endure it. The challenges of living on Mars go beyond the lack of oxygen and cold temperatures. The lower gravity, about one-third of Earth's, would affect human biology in ways that are not yet fully understood, potentially leading to long-term issues with muscle atrophy, bone density loss, and even cardiovascular changes. Radiation exposure, far higher than anything experienced on Earth, would increase the risk of cancer and other cellular damage, as Mars lacks the thick atmosphere and magnetic field that protect life on our home planet. Limited access to fresh food, water, and medical care would place additional strain on the human body, making every minor ailment or deficiency a potential threat to long-term survival. Engineering humans for Mars would mean addressing these vulnerabilities at a fundamental level, not just treating their symptoms, but altering the body itself to resist them. Genetic modifications could be introduced to strengthen bones and muscles, counteracting the effects of lower gravity and ensuring that future generations do not grow up physically weaker than their Earth-born ancestors. Alterations to DNA repair mechanisms might help cells resist radiation damage, reducing the risk of cancer and extending lifespans in an environment where medical resources are limited. The ability to produce essential nutrients internally or to metabolize food more efficiently could be enhanced to reduce dependence on a carefully controlled diet, allowing settlers to thrive on a more limited range of available resources. Even something as simple as modifying skin to be more resistant to ultraviolet radiation or altering the way the body conserves water could mean the difference between struggling to survive and adapting to a life beyond Earth. For the first generations of Martian settlers, such modifications might be minimal, perhaps limited to medical treatments that reinforce bone density or reduce radiation sensitivity. But over time, as genetic engineering advances and as humans spend generations living away from Earth, more significant changes could emerge, whether by design or through natural selection. Children born on Mars might develop traits that make them naturally better suited to their environment. Longer limbs adapted to lower gravity, enhanced lung capacity to make use of thin, oxygen-poor air, or subtle metabolic changes that make them more efficient at processing food and water. If enough time passes, these adaptations could become permanent, creating a population that, while still human, is no longer identical to those who remained on Earth. The idea of altering the human body to survive on another world raises deep ethical and philosophical questions. Would these modifications be seen as enhancements, or as something that distances Mars-born humans from their earthly origins? Would they be a necessity for survival, or a choice that only some would make? And if future generations of Martians eventually become biologically distinct from their ancestors, what would that mean for their identity, their connection to Earth, and their place in the broader human story? These are questions that cannot be answered easily, but as humanity moves closer to becoming a multi-planetary species, they will become impossible to ignore. Ultimately, the decision to engineer humans for Martian conditions is not just about science or technology. It is about the nature of adaptation itself. If Earth is no longer the only home of humanity, then survival in new worlds may not be about forcing those worlds to change, but about changing ourselves. The settlers of the future may not be astronauts sealed in pressurized suits, forever dependent on artificial life support, but something different, still human, but reshaped by the demands of an unforgiving planet, not just surviving on Mars, but becoming part of it. If modifying the human body to survive on Mars presents a solution to many of the challenges of living in such a hostile environment, it also introduces questions that go far beyond science. While genetic engineering offers a way to strengthen bones, resist radiation, and enhance metabolic efficiency, it also forces humanity to confront the deeper implications of altering its own biology. The idea of reshaping humans for life on another planet is not just a matter of medical advancement. It is a fundamental shift in how people define themselves, raising ethical, philosophical, and even social concerns that have no simple answers. For some, the possibility of genetic modification represents the next logical step in human evolution, a necessary adaptation that allows people to thrive in environments that would otherwise be uninhabitable. For others, it is a step too far, an intrusion into the natural order, a risk with consequences that cannot be fully understood, or even a challenge to the very idea of what it means to be human. The most immediate controversy lies in the ethical implications of editing human genes, particularly when those changes could be passed down through generations. While medical advancements have already allowed for the treatment of genetic diseases, altering DNA to make future generations more resistant to radiation, better suited to low gravity, or more efficient at processing food and water moves into far more uncertain territory. Unlike traditional medicine, which treats individual patients based on their specific needs, genetic modifications designed for space travel could create lasting changes in the human genome, affecting not just one person, but entire lineages of people who never had a say in their own biological design. The thought of children being born with predetermined traits optimized for a world they did not choose to live on raises concerns about autonomy and consent, about whether future generations should be shaped by the choices of those who came before them, or whether they should have the freedom to live within the limits of an unmodified body, even if that means struggling to survive. There is also the fear that genetic modification could create divisions within humanity itself, separating those who have been altered for life on Mars, or any other off-world colony, from those who remain on Earth. If Martian settlers develop traits that make them physically distinct, even slightly, from their Earth-born counterparts, could that lead to social or political tensions in the future? Would engineered humans come to see themselves as superior, better adapted to the harsh realities of space, while unmodified humans are left behind as relics of an earlier era? Or would Earth-born populations view the modified as something unnatural, something separate from the shared history and identity of the human race? While these ideas may seem like speculation now, history has already shown how even the smallest perceived differences between groups can lead to division, mistrust, and conflict. The introduction of genetic engineering on a large scale, especially if it is used to create permanent adaptations to different environments, has the potential to redefine human society in ways that are impossible to predict. Beyond the ethical and social concerns, there is also the simple reality that genetic modification is still an imperfect science, one that comes with risks that are not yet fully understood. Even with advanced technology, altering DNA at a fundamental level carries the possibility of unintended consequences. Mutations that do not behave as expected, long-term health effects that only become apparent years later, or genetic changes that, once introduced, cannot be undone. A trait designed to help humans survive on Mars might have unexpected side effects that limit their ability to live anywhere else, locking future generations into a specific biological form that is suited for one planet but makes returning to Earth impossible. The more humans modify themselves for survival in alien environments, the more they risk creating a future where different branches of humanity are no longer compatible with one another, where the dream of space exploration leads not to a united species but to a divergence that separates one world from another in ways far more profound than distance alone. Despite these concerns, the allure of genetic modification remains undeniable. The ability to shape the human body to better endure space travel and planetary colonization could mean the difference between a fragile existence and a thriving future beyond Earth. It is a technology that, if used carefully, could allow humanity to spread across the stars, adapting not by forcing entire planets to change, but by changing ourselves instead. But the question remains, how far should this power be taken? Is it enough to make small, targeted modifications to counteract the dangers of radiation and low gravity? Or does true adaptation require something deeper, something irreversible? And if humanity does choose this path, does it risk creating a future where the people who leave Earth are no longer the same as those who remain? These are not questions that science alone can answer, because they are not just about genetics or survival, but about the very identity of the human race and the choices that will shape it for generations to come. 23. Psychological challenges of living on a terraforming Mars. The psychological challenges of living on a terraforming Mars would be unlike anything humanity has ever faced. Imagine waking up every day in an environment that is both familiar and completely alien, where the sky is a dull, rusty hue, and the air outside is still too thin to breathe. The vastness of the planet would feel oppressive in its emptiness, yet the actual living spaces would be claustrophobic, confined to small, artificial habitats designed to keep you alive but never truly comfortable. The sense of isolation would be overwhelming, knowing that Earth, the only home you ever knew, is millions of kilometers away, with communication delays making even the simplest conversations sluggish and frustrating. You could send a message to a loved one, but by the time they responded, hours would have passed, making real-time connection impossible. The knowledge that if anything went wrong, a major system failure, an air leak, or a food shortage, help would be months, if not years, away, would weigh on your mind constantly, creating a low-level anxiety that never truly fades. The mental health risks of such a life would manifest in different ways for different people. Some might feel a deep sense of loneliness, missing the casual interactions of Earth, the sound of strangers chatting in a cafe, the feeling of a gentle breeze on their face, the sight of birds flying freely in the sky. Others might develop a creeping paranoia, a nagging fear that something is about to go wrong, that the technology keeping them alive is too fragile, or that the people around them, forced into close quarters for months or years on end, might start to break under the psychological strain. The sheer monotony of life on Mars would be another challenge, as every day would feel eerily similar, the same corridors, the same tasks, the same small group of people, with no possibility of escape. On Earth, if you feel trapped, you can take a walk, go to a new city, or simply change your surroundings. But on Mars, you are stuck in a manufactured environment, where even a step outside requires a suit and careful planning. The lack of natural variety, no forests, no oceans, no changing seasons, could make life feel dull and unchanging, leading to feelings of depression and hopelessness. For some, the sense of purpose in being part of something greater, the transformation of an entire planet, the building of a new home for humanity, might be enough to counteract these struggles, at least for a while. But even the most resilient minds would find themselves grappling with the psychological toll of living in a place that is, by its very nature, hostile to human life. The smallest inconveniences would be magnified in an environment where survival depends on constant vigilance. A minor argument with a crewmate could spiral into deep resentment because there's no way to get space from one another, no chance to step outside and clear your head. A mistake in routine maintenance could be catastrophic, reinforcing the pressure that there is no room for error, ever. The dreams of Earth would linger in the minds of those who left it behind. Memories of open skies, fresh food, the simple pleasure of feeling rain on their skin. And over time, the nostalgia might turn into a painful longing, an ache for something they can never fully have again. Some might adapt, embracing the challenges as part of their new reality, while others might break under the weight of it, their mental health deteriorating in ways that no amount of preparation could have prevented. Even beyond the initial struggles of adapting to life on Mars, the psychological weight of knowing that this world is not just a temporary mission, but a permanent home would create an entirely different set of challenges. Unlike the early settlers who might still dream of returning to Earth one day, those born on Mars, or those who commit to living there for the rest of their lives, would have no such illusion, no sense that their time on this planet is anything other than final. The absence of a true homecoming would shape their identity in ways that might be difficult for Earth-born humans to understand. For those born on Mars, Earth would be a distant, almost mythical place, a world they would hear about but never truly experience, its gravity crushing, its air too thick, its biological world alien to their very physiology. They would grow up never knowing the feeling of a blue sky stretching endlessly above them, never running barefoot on grass, never swimming in an ocean, never feeling the pull of Earth's gravity shaping their movements. Over time, this fundamental separation from the rest of humanity would create a psychological divide, a sense of otherness that could manifest in loneliness, resentment, or even a redefinition of what it means to be human. The knowledge that they are part of an experiment, a multi-generational project to make Mars livable, would be both a source of pride and an inescapable burden. Every aspect of their existence would be shaped by necessity rather than choice. Their food, their routines, their relationships, all dictated by survival rather than freedom. Unlike humans on Earth, who can reinvent their lives, travel across continents, change careers, and seek out new experiences, a lifelong Martian would live within the boundaries of a world where every resource is rationed, where every breath is carefully managed, and where even the idea of escape is impossible. The psychological effects of knowing that there is nowhere else to go, that the planet itself will never welcome them without constant technological intervention, would weigh heavily on the mind. Social structures would develop in ways that might not align with Earth's, leading to generational friction as the first Martians grow up without the nostalgia that their parents carry. The stories of Earth might seem irrelevant, the warnings of its mistakes distant, the cultural and historical touchstones of humanity less meaningful to those who have never set foot there. Psychological resilience would be tested in ways that Earthbound psychologists might struggle to predict. Would lifelong Martians struggle with existential isolation, knowing they are physically cut off from the planet that birthed the rest of humanity? Would they feel abandoned, forgotten by those who remained in the cradle of civilization? Or would they embrace their unique status, seeing themselves as pioneers of a new branch of the human species? The reality of never being able to leave, never seeing new landscapes beyond the controlled environments of domes and underground shelters, never hearing the rustling of trees or feeling the rush of natural wind, might lead to a deep-seated restlessness, a psychological claustrophobia that no amount of technological advancement could erase. Even relationships and family structures would be shaped by the demands of Martian life, with partnerships and friendships formed under the unrelenting awareness that every person in the settlement is part of a fragile ecosystem where interpersonal conflicts cannot afford to escalate. The pressure to maintain harmony, to suppress frustrations, to always work toward the greater good of the colony, might create an emotional tension where genuine self-expression becomes difficult. The mental health challenges would not just be about isolation or monotony, but about a deeper existential question. What does it mean to be human when everything that once defined the human experience no longer exists? Over generations, the psychological consequences of knowing nothing but Mars, of having no memory of a world that was ever truly meant for humans, would create a new kind of consciousness, one that might diverge from Earth's way of thinking in ways that are impossible to predict. 24. Unexpected consequences of terraforming. As the psychological struggles of lifelong Martian residents unfold, another battle would be playing out beyond the walls of their settlements, one far less predictable and potentially more catastrophic. Terraforming, the grand ambition of turning Mars into a world capable of sustaining human life without domes or life support systems, would not be a smooth, controlled process. It would be a chaotic, delicate balancing act where even the smallest miscalculations could send the entire planet's climate veering in an unintended direction. The dream of a breathable atmosphere, flowing water, and lush landscapes could easily become a nightmare of extreme instability, where temperatures fluctuate wildly, creating conditions that are either unbearably hot or dangerously cold. Unlike Earth, where the atmosphere has been fine-tuned by billions of years of complex feedback systems, Mars would be undergoing an artificial, accelerated transformation, and with it, an entirely new set of problems that no human civilization has ever encountered before. For those living through the process, the unpredictability of the climate would be an ongoing source of fear and frustration. One year, temperatures might rise enough for liquid water to form, raising hopes that the transformation is finally working, only for the next year to bring sudden, deep freezes that lock everything in ice, undoing years of progress. Dust storms, already a major threat on present-day Mars, could become even more violent and prolonged as warming air interacts with the thin, unstable atmosphere. Sudden temperature swings could cause equipment failures, crippling power grids, and making even routine travel outside of controlled habitats a life-threatening risk. Colonists might wake up one morning to find that what was once a stable, livable environment has been transformed overnight into a hostile wasteland again, forcing them back into survival mode after years of believing they were finally building a true home. The psychological toll of never knowing whether the planet itself is going to betray them would weigh heavily, as every improvement could be undone by an unexpected shift in climate, forcing people to live in a constant state of vigilance, never truly able to trust the world they are trying to create. Even as the atmosphere thickens and temperatures rise, there would be no guarantee that Mars would stabilize at a comfortable level. If too much greenhouse gas is introduced too quickly, the planet could overshoot into a runaway heating phase, creating scorching temperatures that make outdoor survival just as impossible as before. The once dry riverbeds could flood violently, transforming into deadly, uncontrollable torrents as melting polar ice caps release vast amounts of water into the Martian landscape. If, on the other hand, warming efforts stall or fail to trap enough heat, Mars could remain in a state of permanent cold, where freezing temperatures make liquid water a fleeting occurrence, forming briefly before disappearing again into ice. Colonists would be caught in the middle of these extremes, their survival tied to the delicate, unpredictable shifts of a planet that is not naturally inclined to support them. With each unexpected turn, frustration and exhaustion would grow, as the dream of making Mars into a second Earth starts to feel like an endless struggle rather than an achievable reality. Some might question whether it was ever worth it, whether humanity should have accepted Mars for what it was rather than forcing it into something it was never meant to be. Others might refuse to give up, convinced that the only way forward is to keep pushing, keep adjusting, keep trying to control forces that might ultimately be beyond human influence. But no matter how determined they are, no matter how much science and technology they throw at the problem, the truth remains the same. Mars is not Earth, and the consequences of trying to make it one might be more unpredictable and unforgiving than anyone ever imagined. As the struggle to control Mars's climate continues, another force, far less predictable and perhaps even more uncontrollable, would begin to take shape. Terraforming isn't just about altering the atmosphere or warming the planet. It's also about biology, about introducing life where none has ever existed, about engineering organisms that can survive and thrive in conditions vastly different from Earth. But once life is introduced, it doesn't follow a script. It adapts, mutates, and evolves in ways that no amount of planning can fully anticipate. The bacteria, algae, and hardy plants designed to kickstart Mars's transformation would not remain in their intended forms for long. In the harsh, alien conditions of a changing world, evolution would take hold, shaping these organisms into something new, something unintended, something that could either accelerate the terraforming process or completely derail it. For the colonists watching this unfold, the realization that life on Mars is no longer under human control would be unsettling. The microbes engineered to produce oxygen might start behaving differently, mutating to prioritize survival over efficiency, consuming resources in ways that make them less useful for their intended purpose. Algae introduced to dark Martian caves could develop unexpected traits, spreading aggressively in ways that no one predicted, outcompeting other species, and throwing off the delicate ecological balance that scientists had tried so carefully to establish. The simple, controlled ecosystems designed for stability might begin to shift, with some organisms thriving beyond expectations while others struggle or disappear entirely. Over time, the life forms that humanity introduced to Mars might become unrecognizable, evolving into something uniquely Martian, something no one ever accounted for. The implications of this would go beyond just scientific curiosity. It would be a source of both wonder and fear. If these new life forms were beneficial, they could push Mars closer to habitability faster than expected, creating conditions that allow larger, more complex ecosystems to take hold. But if they evolved in ways that disrupted human efforts, consuming vital resources, producing harmful byproducts, or spreading uncontrollably, it could turn the dream of a terraformed Mars into a biological nightmare. Colonists might find themselves dealing with unexpected threats, with bacterial blooms that clog life support systems, with mutated plant life that spreads into fragile habitats, with microorganisms that behave in ways no one fully understands. The idea that humans were in control of Mars's future would quickly fade as the planet's own version of evolution begins to take over, shaping a world that is neither Earth nor the Mars that was originally envisioned. And then there's the most unsettling question of all. What if life on Mars, once unleashed, refuses to be tamed? What if the very act of introducing biology to this planet sets off a chain reaction that humans can no longer stop, creating an ecosystem that is fundamentally incompatible with long-term human survival? The irony would not be lost on those who fought to make Mars livable, only to realize that they might have created something that no longer needs them. The settlers would watch as their carefully designed life forms diverge into something unpredictable, something no longer of Earth but of Mars, evolving into forms that could shape the planet's destiny in ways no human mind could have ever foreseen. As Mars begins to change in ways that are no longer entirely in human hands, the consequences of terraforming might not remain confined to a single planet. The idea that altering Mars's climate could somehow affect Earth's might seem far-fetched at first, but the reality is that no major planetary-scale project exists in isolation. The materials, technologies, and sheer energy required to transform an entire world would create ripple effects that stretch far beyond the Martian atmosphere. The movement of vast amounts of greenhouse gases, the extraction of resources from asteroids or Earth itself, and the potential biological contamination between planets could all introduce unforeseen changes to the delicate balance that has kept Earth habitable for so long. For those still living on Earth, the first signs of these effects might be subtle, almost unnoticeable at first. If terraforming efforts rely on large-scale mining operations on Earth to supply the raw materials needed to warm Mars, the environmental cost could add up over time, accelerating the depletion of natural resources and increasing pollution. If carbon dioxide or other gases are redirected from Earth's atmosphere to Mars in an attempt to thicken the Martian air, it could have unintended consequences, shifting global temperatures in ways no one predicted. Even small changes in atmospheric composition could disrupt climate patterns, affecting agriculture, ocean currents, and weather systems in ways that are difficult to reverse. But the more significant risks might come from the potential spread of Martian life back to Earth. If microorganisms introduced to Mars evolve into something entirely new, something adapted to an alien environment, there's no telling how they might interact with Earth's biosphere if they ever made their way back. A single microscopic organism, shaped by the extreme conditions of Mars, could behave unpredictably in Earth's rich, diverse ecosystems, introducing new variables into a world that has spent billions of years finding balance. Even if strict containment measures were put in place, the possibility of accidental contamination would always exist, carried by returning spacecraft, dust particles, or even human settlers themselves. Beyond the physical and biological risks, the sheer scale of the effort to terraform Mars could shift global priorities on Earth in ways that destabilize economies and political structures. The redirection of scientific resources, financial investments, and even population migration toward Mars could lead to unforeseen consequences, with Earth's own climate and environmental issues receiving less attention as humanity becomes more focused on its interplanetary ambitions. If climate engineering technologies are developed to manipulate Mars's atmosphere, there's no guarantee they wouldn't eventually be used on Earth as well, leading to ethical and practical dilemmas about who controls the climate of an entire planet and what happens if those efforts go wrong. As Mars becomes more habitable and its own climate begins to stabilize, if that is even possible, Earth might find itself in a position it never anticipated, forced to deal with the consequences of playing with planetary systems on a scale never before attempted. What starts as an ambitious dream of making Mars a second home could end up altering the fate of the first one in ways that no one truly saw coming. 25. Political and economic challenges of terraforming Mars. Terraforming Mars would be one of the most ambitious undertakings in human history, requiring an immense level of international cooperation, technological innovation, and economic investment spanning multiple generations. The sheer scale of the project, involving altering an entire planet's atmosphere, temperature, and ecosystem to make it habitable for humans, would demand not only scientific breakthroughs, but also an unprecedented level of political and economic organization. At the heart of the issue, beyond the technical feasibility of such an endeavor, lies a more fundamental question: who would own and govern a terraformed Mars? And how would human societies function in a world that was, by all accounts, created rather than inherited? The moment humanity sets foot on Mars with the intention of making it a second home, we step into a political gray zone where traditional concepts of sovereignty, land ownership, and governance are challenged by the reality of a planet that does not belong to any single nation or entity. The Outer Space Treaty of 1967, which prohibits any country from claiming sovereignty over celestial bodies, was drafted in an era when space exploration was limited to a few governments with relatively basic technology, and it was never designed to address the complexities of large-scale colonization or planetary engineering. As private companies, international organizations, and perhaps even new spacefaring nations become involved, conflicts over resource rights, jurisdiction, and governance will inevitably arise. Would a terraformed Mars be owned collectively by humanity, managed by an international coalition similar to the United Nations, or controlled by the first settlers and corporations that invest in its development? The answer to this question would shape the entire future of Martian society, determining whether it follows a path of cooperation and shared responsibility or falls into the same patterns of territorial disputes and economic exploitation that have defined much of human history on Earth. Economically, the financial burden of terraforming Mars would be astronomical, requiring sustained investment over centuries, with no immediate return on that investment. Governments might be hesitant to commit public funds to such a project when pressing issues persist on Earth, leaving much of the responsibility to private corporations seeking profit. If companies were to fund and oversee the terraforming process, they would naturally expect something in return, whether in the form of land rights, exclusive access to resources, or control over infrastructure. This could create a corporate-dominated society where settlers live under company rule, working to maintain and expand the very systems that keep them alive. The history of colonial expansion on Earth offers a troubling parallel, where those who finance settlement projects often end up exerting disproportionate control over the land, labor, and political systems of the New World. The prospect of Martian company towns, where inhabitants have little autonomy outside of their roles as workers, is not just a dystopian fantasy, but a logical outcome of a system where corporate entities bear the risks and costs of making the planet habitable. However, even if Mars were governed by an international coalition rather than corporations, the challenge of establishing a fair and functional economic system would be immense. A self-sustaining Martian economy would take centuries to develop, and in the meantime, almost everything — food, materials, equipment, even breathable air — would have to be imported from Earth at an enormous cost. The settlers, regardless of their political affiliations, would be economically dependent on Earth for survival, which could create a power dynamic where terrestrial governments or corporations exert control over Martian affairs through financial and logistical means rather than direct governance. Would Martian settlers eventually demand independence, as so many colonies have throughout history, or would they remain tied to Earth's economic systems indefinitely, bound by the reality that their survival hinges on continuous shipments from their home planet? Beyond economics and governance, the human element in all of this cannot be ignored. The first generations of Martian settlers would have to contend with an environment that is both physically and psychologically isolating, where the struggle to survive takes precedence over any ideological debates about ownership and governance. Over time, as Mars becomes more habitable and its population grows, new cultural identities may emerge, shaped by the experience of living on a planet so fundamentally different from Earth. The idea of belonging to a nation or corporate entity might feel increasingly irrelevant to those who have never known life outside of Mars. And this cultural shift could fuel tensions between settlers and those on Earth who continue to view the planet as an investment rather than a home. If history is any indication, these tensions could eventually escalate into conflict, with Martian inhabitants seeking self-determination in ways that mirror independence movements on Earth, but in a context where warfare would be logistically and ethically complicated by the sheer fragility of Martian infrastructure and the necessity of cooperation for survival. The political and economic challenges of terraforming Mars are, in many ways, a reflection of deeper questions about how humanity organizes itself, distributes power, and defines ownership over land that has never belonged to anyone. While the idea of turning a barren planet into a thriving ecosystem is an inspiring testament to human ingenuity, it also forces us to confront the very flaws and contradictions that have shaped our history on Earth. Whether Mars becomes a utopian experiment in shared governance and sustainability or a battleground for corporate dominance and resource conflicts will depend not only on the technologies we develop, but on the political and economic systems we choose to bring with us. The process of making Mars habitable is not just about reshaping a planet. It is about reshaping humanity itself, and the choices we make in those early years of settlement will determine whether the red planet becomes a second chance at civilization or a repetition of the same mistakes that have defined so much of our past. All the political and economic uncertainties surrounding a terraformed Mars ultimately lead to one fundamental question: who is willing to pay for it? The transformation of an entire planet, one that lacks a breathable atmosphere, liquid water on its surface, or a self-sustaining ecosystem, would require investments so massive that no single government or corporation could realistically shoulder the burden alone. The cost wouldn't just be measured in money, but in centuries of labor, material resources transported across millions of kilometers, and the lives of those who would have to endure the harsh conditions of an unyielding world while slowly turning it into a place that could sustain human civilization. Terraforming isn't a single project with a clear endpoint. It is a process that could take hundreds, perhaps even thousands of years, demanding the kind of long-term commitment that no nation, company, or individual has ever been able to maintain over such a vast timescale. Unlike the early days of space exploration, where national pride and political rivalry between superpowers justified the immense costs of programs like Apollo, the effort to terraform Mars would need more than ideological motivation to attract funding. Governments could play a role, but the realities of modern geopolitics make it unlikely that any nation would pour significant public funds into such a venture when immediate concerns on Earth, climate change, economic inequality, political instability, constantly demand attention. Even if a coalition of space-faring nations agreed to share the cost, the sheer expense of maintaining human settlements, shipping equipment, and constructing infrastructure on a planet where nothing is readily available would strain even the wealthiest economies. Taxpayers, who ultimately fund government-led projects, may not be eager to support an initiative that would only benefit future generations while their own world still struggles with problems that feel more urgent and tangible. This leaves private corporations, investors, and the possibility of a commercialized Mars as the primary alternative. The logic behind corporate involvement is simple. If there's a potential profit to be made, the money will come. But the problem with terraforming is that the financial return on investment is almost impossible to quantify. Unlike space mining, where companies could extract valuable resources from asteroids and sell them on Earth, or satellite-based industries that already generate revenue, terraforming Mars is a long-term bet with no guarantee of success. It would require continuous spending on infrastructure, habitat construction, environmental modification, and life support systems without any immediate way to generate revenue. Some companies might fund early settlement efforts in hopes of securing future economic dominance, but a fully terraformed Mars could take centuries, far longer than the attention span of any business looking for short-term returns. One possibility is that corporations and billionaires would fund initial colonization efforts, with settlers essentially working under company contracts to maintain and expand the infrastructure necessary for future terraforming. This could create an economic model where Martian settlements operate like company-run towns, where workers exchange labor for necessities like food, water, and breathable air rather than earning traditional wages. The ethical implications of such a system are troubling, as it could create a society where survival is entirely dependent on continued employment under corporate rule. If resources are controlled by a handful of powerful entities, Martian settlers might have little to no autonomy over their own lives, bound by economic dependence on the very organizations that made their existence on Mars possible in the first place. Crowdsourced funding and individual investment could also play a role, especially in the early stages of settlement. Space tourism, scientific research grants, and public-private partnerships might generate some of the necessary funding, but these streams of revenue would only be able to support limited development rather than a full-scale planetary transformation. There's also the possibility that Martian settlers themselves would eventually bear the financial burden, either through taxation, labor obligations, or even debt systems that future generations would have to inherit. The history of human expansion has often relied on systems where those seeking a new life in an uncharted world must take on financial risk in exchange for land, citizenship, or opportunities that would otherwise be unavailable to them. A similar system could emerge on Mars, where those who wish to live there must commit to years or even lifetimes of labor to pay off the cost of their passage and survival. The other question is whether economic incentives could be created to justify the cost of terraforming in the first place. If Mars offered unique resources, rare metals, scientific discoveries with direct applications for industries on Earth, or even the potential for new energy sources, then investment might come more easily. But Mars, as it exists today, has no obvious financial value beyond its role as a stepping stone for future space exploration. Terraforming, therefore, would have to be justified as something more than just an economic endeavor. It would have to be seen as a necessary expansion of human civilization, a safeguard against existential threats to Earth, or an ideological commitment to securing a multi-planetary future. Convincing people to pay for something that might only bear fruit centuries down the line requires more than just economic reasoning. It requires a vision compelling enough to inspire generations of investment, sacrifice, and long-term planning. No matter who ends up funding the effort, the reality is that the cost of terraforming Mars isn't just about money. It's about who is willing to take the risk, who is willing to endure the hardship, and who ultimately controls the future of a world that doesn't yet belong to anyone. Whether it's governments pooling their resources, corporations bidding on long-term dominance, settlers paying with their labor, or some entirely new economic system emerging to support the endeavor, the process of transforming Mars into a livable world will be shaped as much by financial realities as it is by scientific challenges. The dream of a second Earth is not just a technological challenge. It is an economic gamble, and those who pay for it will, in one way or another, decide the fate of Mars itself. The question of who pays for terraforming Mars inevitably leads to the issue of control. Whether the planet's future will be shaped by international cooperation or dominated by corporate interests. The sheer scale of turning an uninhabitable wasteland into a thriving ecosystem demands a level of organization that humanity has never attempted before, and the way that organization is structured will determine everything from the laws that govern Martian society to the daily lives of those who settle there. If the endeavor is driven by nations working together, it could become a shared human project, where no single country or entity lays claim to Mars but instead manages it collectively for the benefit of all. If corporations take the lead, Mars may not be a new frontier for humanity as a whole, but rather a privatized world, where every aspect of life is dictated by the interests of the companies that invested in making it habitable. Neither approach is without its challenges, and the way Mars is settled will likely depend on a combination of both, shaped by economic pressures, political realities, and the choices of the people who actually live there. An internationally coordinated effort, potentially modeled after organizations like the United Nations or the International Space Station, could ensure that Mars remains free from nationalistic conflicts and economic exploitation, treating the planet as a shared endeavor rather than a prize to be claimed. A system like this would require agreements between nations on everything from funding and governance to resource management and environmental protection, ensuring that no single power dictates the future of Mars. In theory, this approach would prevent territorial disputes, guarantee fair access to Martian resources, and prioritize scientific and humanitarian goals over profit. However, cooperation on this scale has rarely lasted for long in human history, and even the most well-intentioned treaties tend to unravel when economic interests, shifting political landscapes, and unforeseen challenges come into play. On the other hand, if private companies are the ones to establish the first permanent settlements, build the infrastructure, and fund the long and costly process of terraformation, they will naturally expect control over the outcome. Unlike governments, which can justify their involvement through public interest and long-term strategy, corporations function under the necessity of profit, meaning every investment in Mars must eventually translate into economic returns. This could result in a world where access to land, resources, and even basic survival necessities like oxygen, water, and food are dictated by market forces rather than collective governance. Settlers might find themselves living in a corporate-controlled society, where employment is directly tied to survival and where laws are shaped not by democratic representation but by company policies. History has seen this kind of structure before, from company-owned mining towns to colonial enterprises where corporations exercise control over entire regions, and in every case, the result was a population that was dependent on the very system that governed it, with little power to shape their own future. Yet, while corporate dominance over Mars may seem like a dystopian scenario, it could also be the only realistic way to sustain long-term settlement in an environment where survival depends entirely on infrastructure and supply chains that must be continuously maintained. Private companies could provide stability where international bureaucracy might falter, ensuring that the resources and technological advancements necessary for terraforming continue without disruption. The trade-off, however, is that Mars would no longer be a new world for all of humanity, but rather a business venture, where those who can afford to invest or participate in corporate-led missions would have access to opportunity, while those without financial backing would be excluded. Over time, this could lead to a form of social stratification, where early settlers and corporate stakeholders establish control over key industries and infrastructure, leaving later generations in a position where they must either work within the system or struggle to survive outside of it. At some point, conflicts between these two visions of Mars, one as an internationally governed shared human project and the other as a corporate-driven expansion, would become inevitable. Settlers themselves might begin to question the legitimacy of corporate control, demanding self-governance and independence, much like colonial populations on Earth eventually sought to break free from the powers that initially funded their expansion. If Mars is treated purely as an investment, those who live there may one day resist the idea that their lives and land are subject to distant investors who have never set foot on the planet themselves. The challenge, then, is whether a balance can be found between economic pragmatism and the human need for autonomy, between the necessity of corporate funding and the long-term goal of building a society that isn't just a business operation but a true home for those who live there. Regardless of which path Mars takes, the people who will experience the consequences firsthand will be the settlers, the workers, and the generations born on a planet that their ancestors struggled to make livable. Whether Mars becomes a corporate colony or an international endeavor, the reality is that the individuals who build its future will eventually have the power to reshape the systems that control it. In the end, it may not be governments or corporations that decide what Mars becomes, but the people who wake up every day under its rust-colored sky, breathing air that was once unbreathable, and building a world that, for better or worse, will belong to them. 26. The role of private companies versus government agencies. As the debate over whether Mars will be shaped by international cooperation or corporate control unfolds, the reality is that both government agencies and private companies are already deeply involved in paving the way for human settlement. Organizations like NASA, the European Space Agency, and China's CNSA approach Mars with the mindset of long-term exploration, scientific discovery, and public interest, while private companies such as SpaceX, Blue Origin, and others are driven by the promise of innovation, efficiency, and the eventual commercialization of space. These different motivations influence not only how Mars will be reached, but also how it will be developed, who will have access to it, and what kind of society will ultimately emerge there. The question is not whether governments or private companies will lead Mars colonization, but how their roles will intersect, complement, or conflict with each other as the first permanent settlements begin to take shape. NASA, with its history of space exploration and its role as the leader of robotic missions to Mars, has spent decades laying the scientific and engineering groundwork for future human missions. It operates under strict regulations, public oversight and a budget that fluctuates based on political priorities, making its approach slower and methodical, but also grounded in long-term planning. A government agency like NASA has no direct financial incentive to colonize Mars. Its focus is on research, planetary protection, and ensuring that space exploration benefits all of humanity rather than just those with the means to invest in it. However, because government agencies rely on public funding and international collaboration, their ability to push forward major projects is often constrained by bureaucracy, changing political administrations, and budgetary limitations. NASA may develop the technology and scientific knowledge needed for Mars colonization, but without sustained financial and political support, it may never be able to lead a full-scale settlement effort on its own. Private companies, on the other hand, are not bound by government bureaucracy in the same way and can make rapid advancements driven by competition, investor funding, and ambitious goals set by their leadership. SpaceX, for example, has fundamentally changed the landscape of space travel by developing reusable rockets, significantly reducing launch costs, and aggressively pursuing the goal of establishing a human presence on Mars within a single lifetime. Unlike government agencies, companies like SpaceX can operate on their own timeline, take financial risks that bureaucracies cannot, and focus on cost-effective solutions to problems that might otherwise take decades to address through traditional government programs. However, their motivations are ultimately tied to financial sustainability, whether through contracts with government agencies, space tourism, resource extraction, or other economic models that will make Mars missions profitable. If a private company is the first to establish a permanent settlement, the structure of Martian society may be shaped more by corporate interests than by democratic governance, raising concerns about workers' rights, access to resources, and the long-term independence of Martian settlers. Other space players, such as Blue Origin, Lockheed Martin, and international agencies like CNSA and Roscosmos, add further complexity to the situation. Blue Origin, with its focus on building space infrastructure and long-term human habitation in space, may contribute to Mars colonization in ways that complement government efforts. But it is also a private entity that ultimately needs to sustain itself financially. Meanwhile, China's rapidly advancing space program could challenge Western-led efforts, potentially leading to competing settlements on Mars, each following different political and economic models. If multiple governments and private companies establish separate bases, the planet could become divided not by natural borders, but by economic and ideological ones, creating a fragmented Martian society where cooperation is necessary for survival, but political tensions from Earth still shape interactions between settlements. At some point, the roles of government agencies and private companies will need to be clearly defined, or conflict will emerge over jurisdiction, ownership, and authority. Governments may try to regulate private space activity, enforcing rules that ensure ethical and fair development, while corporations will push for as much autonomy as possible to avoid legal restrictions that could limit profitability. The balance between these forces will determine whether Mars becomes a free and open society, a corporate-run world, or a patchwork of settlements governed by different rules depending on who funded them. Regardless of who leads the charge, the people who ultimately live on Mars will have to find ways to navigate these systems, ensuring that their world is not just a business venture or a geopolitical pawn, but a place where humanity can truly build something new. As private companies push forward with the technology and infrastructure needed for Mars colonization, while government agencies provide scientific research and regulatory oversight, the question of who should control the planet's transformation becomes unavoidable. Terraforming, an undertaking that would require an immense amount of resources, coordination, and long-term commitment, is not just about changing the landscape of Mars. It's about deciding who has the authority to shape an entire world. If governments lead the effort, Mars might be developed as a shared human endeavor, with international regulations ensuring that its resources and land remain accessible to all. If private corporations take control, terraforming could become a commercial enterprise, where access to breathable air, water, and land is dictated by financial power rather than collective human interest. The decision to privatize terraforming is not just a question of efficiency or funding. It is a question of whether a new planet should belong to those who can afford to develop it or to the generations of settlers who will ultimately live there. The argument for privatizing terraforming is based on the reality that governments move slowly, struggle with long-term commitments, and often lack the funding or political will to sustain projects over centuries. Private companies, driven by competition, innovation, and the need to turn a profit, might be more efficient at developing the technology and infrastructure necessary for planetary transformation. If corporations have a financial stake in making Mars habitable, they have a direct incentive to ensure that it happens as quickly and effectively as possible. Investors willing to fund such an enormous endeavor would expect ownership rights over the land, resources, and potentially even the atmosphere itself, meaning that those who live on Mars might have to pay for access to basic necessities in a system where survival is tied to economic status. In this scenario, terraforming becomes less of a shared human project and more of a business model, where the first companies to invest control the very air that people breathe. But the idea of privatizing terraforming raises ethical concerns that go far beyond economic efficiency. If corporations own the rights to Martian land and resources, they can dictate who has access to them, effectively turning Mars into a company-run world where settlers must work within corporate structures to survive. Unlike Earth, where people can at least rely on natural resources to sustain themselves outside of government or corporate control, Mars offers no such freedom. Without access to oxygen, food, and water provided by those who control the infrastructure, independence becomes nearly impossible. Over time, settlers might find themselves in a situation where their lives are entirely dependent on companies that own not just their homes, but the very conditions that make life possible. This could create an economic system where Martian society is built around corporate contracts, employment-based survival, and limited personal freedom, making it difficult for future generations to break away from the structures established by those who financed the planet's transformation. A publicly managed, internationally coordinated terraforming effort could prevent these issues, ensuring that Mars remains a place where resources are distributed fairly, laws are created through democratic governance, and future generations are not forced into economic dependence on corporate entities. But without financial backing from the private sector, the process would be painfully slow, requiring decades of political negotiations, shifting government priorities, and unstable funding streams that could easily collapse if interest in Mars wanes. Without the promise of profit, governments may not have the long-term motivation to maintain a terraforming project that will take centuries to complete, and without the efficiency of private industry, the dream of a habitable Mars might never move beyond theoretical planning. In the end, whether terraforming should be privatized is not just about economics, but about the kind of world Mars will become. If the process is entirely in the hands of corporations, Mars might develop into a planet where access to life itself is something people must earn through financial means or labor. If it is controlled by governments and international organizations, it could remain a publicly managed human endeavor, but at the risk of inefficiency, bureaucracy, and slow progress. Most likely, the future of terraforming will be shaped by a mixture of both approaches, with private companies funding and executing much of the work while governments attempt to regulate and maintain some level of public oversight. But once a world is in the hands of those who built it, reclaiming it for the people who actually live there may not be easy. The choices made in the early years of Martian colonization will not just determine how Mars is terraformed, but who gets to call it home and under what conditions they are allowed to live. If terraforming Mars is driven primarily by corporate investment, then the fundamental structure of Martian society will be shaped by those who hold financial and technological control over the process. Ownership of infrastructure, land, and life-sustaining resources would naturally give corporations an unprecedented level of power, not just over economic activity, but over the very existence of those who live there. The ethical implications of such control are unavoidable. What happens when the necessities of life are not guaranteed as a basic right, but instead distributed based on financial status, employment, or corporate policy? Unlike Earth, where governments can intervene in markets, regulate industries, and provide social services to maintain balance, a company-run Mars would lack external oversight, creating a situation where those in charge of the planet's survival infrastructure could dictate nearly every aspect of daily life, from housing and food to governance and personal freedoms. The very nature of corporate structure raises concerns about how decisions would be made and whose interests would take priority. Businesses, by definition, exist to generate profit, and while some may genuinely pursue long-term sustainability, their primary responsibility is to their investors rather than the general population. If corporations control Martian settlements, laws and policies would likely be shaped not through democratic representation, but through internal corporate decisions made by executives and shareholders who may never even set foot on Mars. Workers and settlers would have little say in governance if corporate policies dictated everything from workplace regulations to living conditions. Over time, this could create a rigid hierarchy where wealth and corporate loyalty determine one's status in society, and those without financial resources or valuable skills would find themselves in increasingly vulnerable positions, reliant on company contracts just to access the air they breathe and the water they drink. Even if corporations claim to prioritize fair treatment and worker rights, the reality of an isolated, resource-dependent colony means that any form of dissent or organized resistance would be difficult. Unlike Earth, where labor movements, legal protections, and independent economies allow people to challenge unfair working conditions, a Martian settlement controlled by corporate entities would hold absolute leverage over its population. If all food, water, oxygen, and transportation off-planet are controlled by a handful of companies, settlers would have no realistic option to simply leave or create independent communities without access to life-sustaining infrastructure. This creates a situation where corporate leadership would have near-total authority, able to set wages, enforce working conditions, and determine who gets access to resources with little to no external accountability. Beyond economic concerns, the ethical issues extend to fundamental human rights. Would corporate-controlled Mars recognize universal freedoms such as free speech, labor protections, and the right to self-governance? Or would it function more like a company town, where everything from laws to daily life is dictated by policies designed to protect corporate interests? The first settlers may be willing to accept strict rules in exchange for the opportunity to build a new world, but as generations pass, resentment and demands for independence would inevitably grow. History has repeatedly shown that people will not tolerate indefinite control by distant rulers, whether they are governments or corporations. If Martian settlers ever push for greater autonomy, corporate leaders may resist, fearing that loosening their grip would threaten their financial control over the planet. This could lead to deep conflicts, with companies using their control over resources as leverage to maintain authority, forcing settlers to choose between submission or rebellion in a place where survival depends entirely on infrastructure that they do not own. On the other hand, some may argue that corporate-led development is not inherently unethical, provided that companies act with responsibility and foresight. If a company creates a sustainable, thriving Martian society with fair access to resources and opportunities for all, then the practical outcome may be no worse than any other human civilization shaped by economic forces. But history suggests that corporate control, without oversight, rarely remains benevolent for long. Power, once consolidated, is difficult to challenge, and if Mars becomes a corporate-controlled world, undoing that structure may be far harder than preventing it in the first place. The settlers who build Mars will ultimately be the ones who live with the consequences, and whether they find themselves as free citizens or as employees of a planet-sized corporation will depend on the choices made in the earliest stages of colonization. Ethics will not be debated in corporate boardrooms. They will be lived, tested, and fought over by the people who wake up every day under an artificial sky, knowing that every breath they take is owned by someone else. 27. Terraforming and the search for alien life. Terraforming Mars is often imagined as humanity's grandest experiment, a long and arduous process of transforming a barren, frozen desert into a world teeming with life, one that future generations might call home. It is a vision fueled by a mixture of necessity and ambition, a response to the fragility of life on Earth and the innate desire to expand beyond our planetary cradle. But buried beneath the optimism of such an undertaking is an unsettling ethical dilemma, one that forces us to confront the possibility that in our efforts to make Mars habitable for ourselves, we might unknowingly or carelessly destroy something far more profound: the last remnants of alien life, struggling to persist in the planet's hostile landscape. For centuries, Mars has been a subject of speculation, an enigmatic world that has invited theories ranging from intelligent civilizations to mere illusions of life. The reality, however, lies somewhere in between the extremes of fantasy and desolation. If microbial life still clings to existence beneath the surface, hidden within salty brines or sheltered from radiation and subterranean ice, then any large-scale attempt to terraform the planet could be catastrophic for these unseen organisms. Life, in all its stubborn persistence, does not announce itself loudly. It adapts, it endures, and sometimes it survives in places we least expect. If life exists on Mars, it may be fragile, operating on a biochemical framework unfamiliar to us, one that evolved separately under conditions vastly different from those of Earth. And yet, with all our scientific advancements, we remain uncertain whether our own biological footprint could overwhelm and erase such life before we even confirm its presence. Imagine standing on the barren Martian plains, looking up at a sky tinted in pale rust, knowing that every human step, every released molecule of oxygen, every engineered shift in the atmosphere is an intervention of immense consequence. The introduction of Earth-based microbes, intentionally or otherwise, could rapidly contaminate an ecosystem that has remained untouched for billions of years. The very act of altering Mars, of thickening its atmosphere, of flooding its surface with water, could spell the end for native organisms that may be perfectly adapted to their current environment but utterly incapable of surviving in the world we are trying to create. If life on Mars is dependent on conditions that we consider uninhabitable, then in our eagerness to bring warmth and moisture to the planet, we may inadvertently engineer an extinction event. The ethical weight of such a possibility is not easy to bear. It forces us to reconsider what responsibility means when it comes to worlds beyond our own. Humans have an extensive history of reshaping ecosystems, often with unintended consequences, whether through deforestation, invasive species, or industrial pollution. The difference with Mars is that the stakes are not merely about conservation or environmental damage in a conventional sense. It is about the possibility that we may be wiping out the only known example of a second Genesis, another tree of life entirely separate from our own, a discovery that would not just change science, but our entire understanding of existence. And yet, the drive to terraform, to establish a human foothold, to ensure our species' survival, remains just as pressing. It is not an easy balance to strike. If Mars is lifeless, then transforming it into an Earth-like world could be a triumph of human ingenuity, a second chance for a species all too aware of its own vulnerability. But if Mars harbors life, however microscopic, then the moral implications are staggering. Do we proceed, knowing we might be writing the final chapter of an alien biosphere before we even get the chance to read its first page? Or do we exercise restraint, choosing instead to become caretakers rather than conquerors, observers rather than engineers, accepting that not every world is meant to be remade in our image? The answers are uncertain, tangled in scientific unknowns and philosophical debates, but one truth remains inescapable. Our presence on Mars, no matter how careful, will change it forever. If the thought of accidentally erasing an alien biosphere before we even confirm its existence is unsettling, then the only responsible path forward is to understand Mars in its entirety before we even consider altering it. The urge to terraform, to modify, to make Mars a place where humans can one day walk without a spacesuit is undeniably strong, but that ambition cannot come at the cost of knowledge. There is something deeply irreversible about planetary engineering, a transformation that, once set in motion, cannot simply be undone. And so, before we warm its surface, before we release greenhouse gases or introduce terrestrial microbes, before we make a single irreversible decision, we must first learn everything Mars has to teach us about itself, its past, its present, and its potential for harboring life. Mars is not just a barren rock waiting to be remade. It is a world with a history stretching back billions of years, a planet that once had rivers, lakes, and possibly even an ocean. The mere existence of ancient water-carved valleys and dried lake beds tells us that Mars was not always as it is today, that something changed, and that by understanding what happened to Mars, we might better understand the fate of planets, including our own. It is a kind of forensic investigation, one that requires patience and precision, an unraveling of geological and atmospheric clues that could reveal whether Mars was once home to life, whether it still harbors life in some hidden refuge beneath its surface, or whether it is, and always has been, lifeless. These are not trivial questions, nor are they ones we can afford to rush. It is easy to think of Mars as a place waiting for us, a land that exists only in relation to human ambition. But that is not how science works, nor should it be how we approach an entire planet. Mars has existed for over 4 billion years without human interference, and in that time, it has written a story in its rocks, in its atmosphere, in the thin ice that lingers in its shadows. To study Mars properly is to listen to that story rather than overwrite it prematurely. It is to drill into its depths and analyze its subsurface chemistry, to send probes capable of detecting not just water, but the faint chemical traces of past or present life. To piece together the puzzle of why Mars transformed from a place with liquid water to the dry, cold world we see today. These answers will not only reshape our understanding of Mars, but will also provide insights into how planets evolve, what makes them habitable, and whether Earth's future could one day mirror Mars' past. There is also a more human reason for restraint, one rooted not in scientific caution, but in the very way we view the universe. If we rush to terraform, if we make Mars an extension of Earth before we truly know what it is, then we lose something intangible yet profound, a chance to encounter a world on its own terms. There is a kind of humility in acknowledging that not everything is meant for us, that not every place needs to be transformed to suit human needs. Mars is a place that has never known life as we do, a place that has existed in a state of profound isolation for longer than we can truly comprehend. If there is life there, even in the form of a few surviving microbes clinging to existence beneath the regolith, then that life is not ours to displace. And if there is no life, if Mars is sterile and empty, then its emptiness still holds lessons, still contains echoes of a time when it might have been alive. To study Mars before altering it is not an act of hesitation or weakness, it is an act of respect, not just for the science, not just for the possibility of life, but for the reality that we are not entitled to remake everything we touch before we even understand what it is we are changing. There will always be time to terraform, to build, to shape the planet into something more familiar. But there will never be another chance to see Mars as it is now, to study it before it is changed forever, to learn from it before we claim it as our own. The idea of taking Mars as it is, studying it before making irreversible changes, seems like the most logical approach, yet it stands in direct conflict with the relentless human drive to push forward, to transform, to turn something uninhabitable into something familiar. The question that lingers beneath it all is whether terraforming would help or hinder our search for extraterrestrial life, not just on Mars but beyond. The answer is not simple because it is not merely a scientific dilemma but a reflection of how we prioritize exploration over preservation, progress over patience, and human expansion over the possibility that we may not be alone. If life exists on Mars today, even in the most extreme and hidden environments, then terraforming is a direct threat to its survival. Microbes that have adapted to the planet's current conditions, enduring the cold, the radiation, the scarcity of liquid water, might not survive the sudden introduction of a thicker atmosphere, rising temperatures, and the presence of Earth-based organisms. In changing Mars, we could be smothering something ancient and fragile, contaminating it beyond recognition before we even confirm that it exists. There is a tragic irony in the idea that in trying to make Mars more suitable for human life, we might be erasing the most valuable discovery in human history: the existence of a second, independent genesis of life beyond Earth. But there is another perspective, one that suggests that terraforming could actually enhance our ability to search for life rather than destroy it. If Mars were warmed, if its frozen reserves of water were melted, if its atmosphere became more hospitable, then the conditions for life detection might improve. Right now, the planet is a hostile place for both native organisms, if they exist, and for the tools we use to search for them. Radiation bombards the surface, breaking down organic molecules, making it difficult to find clear chemical signatures of biological activity. Subsurface drilling, a promising method for detecting life, is slow and technologically limited by the extreme environment. A warmer, wetter Mars might allow for easier exploration, more accessible water sources, and environments where any existing life could flourish, revealing itself in ways it never could under the current conditions. But the risk of contamination overshadows this possibility. Even the most well-sterilized spacecraft we send to Mars today carry traces of Earth-based microbes, and a fully terraformed Mars would inevitably become home to a vast ecosystem of terrestrial life. If we were to find life after the planet had been transformed, how would we ever be certain that it was Martian and not something we had introduced? The presence of Earth's microorganisms would complicate every discovery, casting doubt on whether any biological evidence was truly native to the planet or merely the inevitable result of human contamination. There is also the broader question of what terraforming Mars would mean for the search for life elsewhere in the universe. Mars is unique in that it is both accessible and ancient, a planet that once had liquid water and conditions similar to those of early Earth. If life arose there once, it might still persist in some form, providing the first evidence that biology is not a rare anomaly but a natural outcome of planetary evolution. If we alter Mars before we have definitive answers, we lose a critical point of comparison, a case study in how life might emerge under different conditions. And if life did not arise on Mars, then that absence is just as important, offering clues about what factors might be essential for life and what conditions might suppress it. By changing Mars prematurely, we risk losing the chance to understand what makes life possible, not just on a single planet, but across the universe. Terraforming is not just a scientific endeavor. It is a statement about human priorities, about whether we see other planets as places to be studied or places to be claimed. The search for extraterrestrial life is, at its core, a search for meaning, for an answer to one of the oldest and most profound questions humanity has ever asked. If we transform Mars too soon, we may never know whether the answer was right in front of us all along, buried beneath the dust, waiting to be found. 28. Terraforming Mars as a stepping stone to interstellar travel. If there is one thing the debate over terraforming Mars makes clear, it is that altering a planet is an undertaking far more complex than simply engineering a new atmosphere or introducing water to a barren landscape. It is a process that forces humanity to reckon with questions of ethics, biology, and planetary evolution, questions that extend far beyond Mars itself. Whether we ultimately choose to terraform or preserve, whether we find Martian life or confirm its absence, the lessons we learn from attempting to reshape a world will extend far beyond the boundaries of our own solar system. Mars is not just a destination, it is a proving ground, a place where we can test what it truly means to make a world habitable. And if humanity ever hopes to venture beyond our own planetary neighborhood, to reach the vast and distant exoplanets orbiting other stars, then the knowledge gained from Mars may be the key to making interstellar travel something more than a distant dream. There is an undeniable appeal to the idea that Mars could be our first great experiment in planetary engineering, the place where we take our first steps toward turning uninhabitable worlds into places that can sustain life. Right now, the prospect of interstellar travel exists mostly in theory, limited by the immense distances between stars, the technological challenges of propulsion, and the biological limitations of human bodies surviving for decades or centuries in deep space. But even if we solve the problem of reaching another star, there remains the question of what awaits us when we arrive. The vast majority of exoplanets we have discovered so far are not Earth-like in any meaningful way. They are too hot, too cold, too irradiated, or covered in thick atmospheres of toxic gases. The odds of finding a perfect second Earth, a world that requires no modification, no adaptation, no engineering, are vanishingly small. If humanity ever hopes to exist beyond our solar system, we will not be searching for planets that are already habitable. We will be searching for planets that can be made habitable. That is where Mars becomes more than just a destination for exploration. It becomes a test case, a place where we can understand what it takes to transform a hostile world into one where humans can live. Every challenge Mars presents, its thin atmosphere, its lack of a magnetic field, its scarcity of liquid water, forces us to think beyond short-term survival and toward long-term planetary adaptation. If we can create a stable environment on Mars, even on a small scale, we begin to understand what is possible elsewhere. The techniques we develop, whether through atmospheric modification, controlled ecosystem introduction, or artificial magnetospheres, could be the very tools that allow us to one day take barren exoplanets and turn them into homes. Mars, with all its challenges, may be the training ground for something far greater, a place where we learn how to manipulate planetary systems in ways that could one day allow human civilization to expand beyond the confines of our solar system. Yet there is a danger in seeing Mars only as a stepping stone, as something to be used rather than understood. The success or failure of terraforming Mars will not simply be a matter of scientific achievement. It will be a reflection of our ability to act with foresight, with patience, with an understanding of the consequences of planetary-scale interventions. If we rush into terraforming without fully grasping the complexities of planetary ecosystems, we risk turning Mars into an example of failure rather than progress. A poorly executed attempt at terraforming could teach us the wrong lessons, could lead us to believe that planetary engineering is impossible rather than difficult. It is not enough to prove that Mars can be changed. We must prove that it can be changed in a way that is sustainable, that does not destroy something valuable in the process, that does not leave us with a half-transformed world unable to support either its native state or the one we try to impose upon it. If we fail on Mars, it is not just Mars that suffers. It is every world we may one day attempt to terraform, every future colony that might depend on the knowledge we gain here. Interstellar travel, at its core, is not just about speed or distance or propulsion systems. It is about survival, about the ability to take an environment that is not suited for human life and reshape it into something that can sustain us. It is about the difference between arriving on a distant planet and truly being able to stay there. Mars may be our first real test of this challenge, a world that sits close enough to reach but distant enough to remind us that survival beyond Earth is never guaranteed. If we can learn to transform Mars carefully, wisely, without recklessness or short-sighted ambition, then we will not just be preparing for the future of Mars. We will be preparing for the future of humanity itself, wherever we may go next. If Mars is our first attempt at understanding what it takes to survive beyond Earth, then the lessons we learn there will not stay confined to a single planet. Every challenge we face in trying to adapt to Mars, its thin atmosphere, its lack of a magnetic field, its limited resources, mirrors, in some way, the struggles we will encounter as we push further into deep space. The process of learning to live on Mars is not just about making a single planet habitable. It is about preparing for the reality that, outside of Earth, every environment is hostile. Every resource must be carefully managed, and every failure to adapt could mean the difference between survival and extinction. Mars is not just a test for planetary colonization. It is a test for our ability to endure the vast emptiness of space itself. The first and most obvious lesson Mars offers is that survival beyond Earth is an exercise in extreme resourcefulness. Unlike the Moon, which is close enough for supply missions, Mars forces self-sufficiency. Everything needed for survival, water, oxygen, food, shelter, must either be brought from Earth at an immense cost or extracted from the planet itself. Learning to mine Martian ice for water, to generate oxygen from the thin atmosphere, to grow food in regolith that was never meant to sustain life. These are not just problems for Mars. They are problems for any long-duration mission into deep space. A spacecraft traveling for decades between stars will face the same constraints, needing to recycle air and water to generate food in closed-loop ecosystems, to repair itself without relying on shipments from home. Mars provides a controlled environment to refine these systems, to test the limits of what is possible, to find the weaknesses before they become fatal in the middle of interstellar space. Beyond resource management, Mars teaches us the psychological and physiological realities of prolonged space travel. A mission to Mars already pushes the limits of human endurance. A months-long journey through deep space, cut off from real-time communication with Earth, trapped in a small, isolated environment where even the smallest error could be catastrophic. The mental strain of such a journey, the need for self-reliance, the ability to function under extreme isolation. These are the same conditions astronauts will face on a generation ship traveling to another star. If humans cannot endure the psychological burden of a Mars colony, then the dream of deep space travel collapses before it even begins. The conditions on Mars, though harsh, offer a chance to study how people cope with long-term extraterrestrial habitation, how they adapt to the alien, the unfamiliar, the relentless feeling of being far from home with no simple way back. There is also the matter of technology. of radiation shielding, of artificial gravity, of energy production. Mars, with its thin atmosphere and lack of a magnetic field, exposes its surface to high levels of cosmic radiation, forcing us to develop better ways of protecting human bodies from deep space exposure. The reduced gravity, though not as extreme as microgravity, still poses unknown risks for long-term human health, teaching us how the body adapts, what countermeasures must be developed, and whether artificial gravity will one day be necessary for deep space missions. Power generation, too, becomes a lesson. Solar panels weaken with distance from the sun. Nuclear reactors offer a more reliable solution but require careful management. And any alternative energy sources we develop for Mars could become essential for spacecraft traveling far beyond the reach of solar energy. Every challenge Mars presents is a preview of what deep space will demand, a chance to refine technology in an environment that is still, at least, reachable if something goes wrong. But perhaps the most valuable lesson Mars offers is perspective, an understanding of just how difficult space colonization truly is. The idea of deep space exploration is often romanticized, seen as an inevitable step for humanity, a natural expansion of our species into the cosmos. Mars forces us to confront the reality that space is not just empty distance. It is danger, it is isolation, it is an environment that does not care if we live or die. If we struggle to survive on a planet that already has gravity, already has some accessible water, already exists within the sun's habitable zone, then what does that say about our chances in the far harsher conditions of interstellar space? Mars is a reminder that survival is not a given, that progress is not automatic, that every step forward must be earned through ingenuity, perseverance, and an acceptance that failure is always a possibility. If we can learn to survive on Mars, to turn a hostile world into something livable, then we take one step closer to the reality of deep space exploration. Every system we refine, every mistake we correct, every breakthrough we make on that small red planet will carry us forward, shaping the future of human expansion beyond our solar system. But if we fail, if we prove that even Mars is beyond our ability to sustain long-term human life, then the dream of interstellar travel remains just that, a dream, a vision of the distant future that humanity is simply not yet ready to reach. Mars is our first great test, and the way we rise to meet its challenges will determine whether we are truly meant to leave Earth behind. If Mars is the first step and deep space exploration the proving ground, then the question that lingers beyond both is whether humanity will ever truly exist beyond the confines of the solar system. Every lesson learned from surviving on Mars, every breakthrough in propulsion, life support, and artificial ecosystems, every psychological and technological challenge we overcome in deep space. All of it builds towards something far greater than a single mission or a single colony. The real question is not just whether we can reach another star, but whether we can establish something permanent, something self-sustaining, something that ensures that humanity is no longer bound to one fragile planet orbiting a single star. The future of civilization beyond the solar system is not just about exploration. It is about permanence, about transformation, about whether the human race can become more than what it has always been. The first challenge is simply getting there. No matter how much we refine our spacecraft, how advanced our propulsion systems become, the reality remains that interstellar distances are vast beyond ordinary comprehension. The closest star system, Alpha Centauri, is over 4 light-years away, a distance that would take thousands of years to cross with current technology. Even with nuclear propulsion, even with theoretical breakthroughs like fusion or antimatter drives, even with concepts as radical as warp travel, the journey would still be measured in decades, perhaps centuries. Sending a single crew on a one-way trip is not enough. If humanity is to move beyond the solar system, it must be in a way that allows entire generations to live and die in deep space before ever setting foot on a new world. A civilization that expands beyond the solar system must be one that accepts the journey as a way of life, not just a temporary challenge to be endured. And then there is the question of what happens when we arrive. No two planets are alike, and even if we discover an Earth-sized world in a habitable zone, it will not be Earth. Its atmosphere may be toxic, its gravity too strong or too weak, its biosphere, if it has one, entirely incompatible with human biology. The search for an exoplanet that is not just habitable in a scientific sense, but truly livable for human beings is a search that may never end. More likely, we will find planets that can be modified, altered over generations to become something close to home. But that process, terraforming on an interstellar scale, would take not just decades or centuries, but perhaps thousands of years, reshaping entire ecosystems, altering climates, building a new world from the ground up. It would require patience on a scale that human civilization has never known, a commitment to a project whose completion may only be seen by descendants who will never know the world their ancestors left behind. The psychological and cultural shift required to become a truly interstellar civilization may be the greatest challenge of all. Humans, as they are now, are still bound to the rhythms of Earth. The cycle of day and night, the seasons, the gravity, the familiarity of a sky that always looks the same. But a civilization that exists in deep space, that lives on generation ships or scattered across distant worlds, will not be the same species in any meaningful way. It will evolve, not just biologically, but socially, technologically, philosophically. Time will be different when measured in the lifespans of stars rather than the rise and fall of empires. Language, culture, even the very concept of what it means to be human may fracture and diverge as distance creates separation, as adaptation to alien environments changes both body and mind. 1,000 years from now, the descendants of the first interstellar travelers may not recognize Earth as home, may not even think of themselves as the same species that once lived under a single sun. And yet, for all the challenges, for all the uncertainties, the urge to reach beyond the solar system may be the most defining trait of human existence. From the moment the first people walked beyond the lands they were born into, from the first ship that sailed into the unknown ocean, from the first step onto the moon, the pattern has always been the same. Curiosity, necessity, ambition, and the knowledge that staying in one place forever is simply not in our nature. Whether it happens in 100 years or 1,000, whether it is driven by desperation or by the simple desire to see what is out there, humanity will not remain confined to one star. The universe is vast, indifferent, hostile, but it is also full of possibility, full of worlds waiting to be found, full of futures waiting to be written. The only question left is not whether we will go, but when, and who we will become when we finally leave the solar system behind. The idea of terraforming Mars exists in this strange space between science fiction and scientific possibility, a concept that feels both thrillingly close and impossibly far at the same time. It's easy to imagine a future where Mars has been transformed into a second Earth, where blue skies stretch above vast plains of alien soil, where rivers flow and crops grow, and where humanity has finally broken free of its dependency on a single planet. But when you pull back from the dream and look at the sheer scale of what it would take to make that happen, reality hits like a brick wall. Mars isn't just another version of Earth waiting to be unlocked. It's an entirely different beast with its own brutal set of rules. The atmosphere is almost non-existent compared to what we need. The temperatures are too low to sustain liquid water. The magnetic field is weak enough that radiation exposure would be a constant threat. And even the soil itself is loaded with toxic compounds that would need to be dealt with before anything could grow in it. Every part of terraforming Mars would require not just technology that we don't yet have, but a level of patience and commitment that spans not just decades, but centuries. It's not a project for one generation or even 10. It's a challenge that, if we decide to take it on, would define humanity's place in the universe for thousands of years. Even if we assume that one day, far in the future, we'll have the knowledge and resources to turn Mars into a habitable world, the question of how long it would actually take is something that no one can answer with certainty. Some theories suggest that with the right level of technological advancement, we could start seeing real change within a few hundred years, while more realistic models suggest that fully terraforming Mars, creating an atmosphere, warming the planet, introducing ecosystems, could take thousands, maybe even tens of thousands, of years. This isn't like building a city or even colonizing a new continent. It's a process that would require a slow, steady transformation of an entire planet's environment, something that has never been attempted before on this scale. There are ideas, of course, ranging from releasing greenhouse gases to trap heat and warm the atmosphere, to redirecting asteroids rich in water ice to impact the planet and release water vapor, to engineering microbes that could start the process of altering the chemical composition of the soil and air. But each of these methods comes with massive technical, logistical, and ethical challenges, and even the most optimistic projections acknowledge that this isn't something that happens within a single human lifetime. If anything, the first people who set foot on Mars might not even live to see the very early stages of terraforming take effect. They would just be laying the foundation for something that future generations, centuries down the line, might finally see come to life. The most realistic steps within the next 50 to 100 years won't be grand, world-changing projects that suddenly make Mars habitable, but rather small, deliberate moves toward making long-term human presence on the planet possible. The first real steps are already happening. Robotic missions mapping out potential resources, experiments like MOXIE proving that oxygen can be extracted from the Martian atmosphere, early discussions of how underground or domed habitats could protect humans from radiation while a more permanent solution is figured out. In the coming decades, we might see the first human settlers living in enclosed, controlled environments, testing out agriculture in specially designed greenhouses, experimenting with ways to produce energy and store water, and beginning the long process of figuring out whether Mars can ever be more than just a place we visit. The real turning point would be the moment when we successfully create some form of sustainable ecosystem on Mars, even if it's just in a small, contained environment. That would be the first true sign that Mars isn't just a place where humans can survive, but a place where life can take hold. But then there's the deeper, more complicated question that lingers beneath all of this. Not just can we terraform Mars, but should we? It's easy to say that having a second Earth would be a good thing, that ensuring the survival of humanity by expanding beyond our home planet is the logical next step. But there's an ethical dimension to this that can't be ignored. Mars, as far as we know, is a dead planet, but there's always a chance that microbial life exists there, hidden beneath the surface, waiting to be discovered. If we push forward with terraforming, do we erase whatever native Martian life might exist, effectively colonizing a world that was never ours to begin with? And even beyond that, do we have the right to reshape an entire planet just to suit our needs? Some argue that instead of changing Mars to fit us, we should focus on adapting ourselves to fit Mars, whether through technology or even biological modification. Others believe that Mars should remain untouched, a scientific outpost rather than a second home, a place where we learn about the universe rather than try to force it into something familiar. The debate isn't just about engineering and physics. It's about what kind of future we want to build, about whether our expansion into space should be one of conquest or coexistence. The dream of a second Earth is one that has captivated humanity for as long as we've looked up at the stars and imagined what might be out there. It's a dream that represents everything we are: our ambition, our ingenuity, our desire to push beyond our limits, our need to explore and conquer the unknown. But it's also a dream that forces us to confront the reality of what it means to be human, to ask ourselves whether our survival is more important than preserving the natural state of another world, to consider whether our reach should always exceed our grasp, or whether, sometimes, there are places that should remain beyond our influence. Maybe, centuries from now, Mars will be transformed, its deserts replaced with oceans, its thin air thickened into something breathable, its empty landscape dotted with cities where people live their entire lives without ever knowing what it was like before. Or maybe it will remain as it is now, a reminder that not everything in the universe was made for us, that some worlds exist not to be changed, but to be understood. Either way, the journey toward answering these questions isn't just about Mars. It's about us, about what kind of species we want to be, about whether our destiny is to remake the universe in our own image or to find our place within it as it is. After everything we've explored, from the bold dreams of terraforming to the brutal reality of Martian conditions, one thing is clear. Reshaping an entire planet isn't just a scientific challenge, it's a test of human ambition, patience, and ingenuity. Whether Mars will ever have blue skies and flowing rivers, or if it will remain a barren, red enigma, is something only time will reveal. But the fact that we even dare to imagine it, to plan, to theorize, to push the limits of what's possible, says something about us. It's not just about Mars. It's about who we are as a species, about whether we're meant to stay bound to one world or if we're destined to carve out new homes among the stars. So, as we wrap up this journey into the future of Mars, I hope it's given you something to think about, whether it's the science, the ethics, or just the sheer scale of what it would take to transform a world. And hey, if you enjoyed this deep dive into the possibilities of terraforming, make sure to hit that like button. It won't heat up Mars, but it does help this channel grow. And if you want to keep exploring the mysteries of the universe with me, go ahead and subscribe. Who knows, maybe one day we'll be watching videos like this from a colony on Mars. Until then, thanks for watching, and I'll see you in the next one.